Welcome to APEC. It's July 6, 2024, and I'm your moderator, Tim Ventura. I want to thank everybody for joining us on today's call, along with everybody watching us on YouTube. So today, Al Baur will discuss levitation and propulsion in electrostatic field. Nathan Inan discusses classical coupling of gravitation and electromagnetism. He's going to be talking about the Meissner effect also. Shiva Meucci will be discussing the experimental record of neoclassical interpretation. Jarod Yates will be talking about arts parts and reported UFO crash recovery samples. And Gerald will be presenting on electromagnetic coils and transverse gravitational waves. So a couple of quick notes about what we've been up to, because this has been a crazy busy summer, and it's all in a good way. A couple of weeks back, I flew down to Florida and I did interviews and took photos with the Exodus team in Orlando. So that is Andrew Arigma and then Dr. Charles Bueller, and I did in depth with both of them. I was so excited. And then Mark graciously drove me up the coast. We went up together to Todd Desiato's lab, and we helped him get some stuff organized and in play. And then from there, we went up to Falcon Space. At Falcon Space, we had the opportunity to analyze arts parts, the reported UFO crash recovery material with Jarod Yates. And Mark also put together, he has an amazing dynamic nuclear polarization setup. And so this, again, just tremendous, tremendous stuff. We also stopped up at Massachusetts to see everybody up there, and I got photos of the whole thing. So that is all online, and I will tell you guys about that later. So that is kind of what we've been up to. But let me give you quick updates before we begin. Today's event is on StreamYard. We're broadcasting through the Alt Propulsion YouTube channel. If you haven't subscribed to Alt Propulsion, please do so now. You can ask questions during this live cast using the live chat feature on the right-hand side of the page, and we will ask them to our presenters depending on time constraints and if we see them, because those questions kind of scroll up really fast. So we will give that a try. You can also view conference replays, details, and speaker info on our website at altpropulsion.com. That recently had a makeover, and I am going to be adding more to it as well. So definitely take a moment to visit altpropulsion.com. So I want to get started here. We are a little bit behind schedule. Let me apologize for that. I haven't used this computer in a month, and so it all of a sudden forgot the microphone and the camera and all the settings. Interesting how that works. So now that we are rolling for today, I want to bring on Al Baur, who's going to be talking about levitation and propulsion in electrostatic field. Al, welcome, sir.
Thank you.
And if it's okay, can I bring up, should I start you with this?
Yes.
Wonderful.
I will start with this.
Wonderful. Well, thank you so much for joining us today. What I will do is, again, about an hour to present. I'm going to take myself right out of the studio, and you take it away, sir. And let me know. There is a back and forth button for the slides if you put your mouse over it. If you need to switch slides, because I see a couple of videos, just let me know and I can put those up for you.
Okay. Okay. What I'm going to explain is about electrostatics. Electrostatics is a family of electromagnetics. And electromagnetics is the second strongest force in nature. One of the things that is related to electrostatics is that it is believed to be a very weak force, which I want to show that it's not. Okay, the electrostatic levitation started around 300 years ago when somebody put a young guy up on ropes and was charged with electricity and was able to move gold leaves. from that point on, a lot of things happened, but not in electrostatics. The main new things that happen in electrostatics is in electronics, especially in chips, making of ionic thrusters in space. What I'm going to do here is to show that it's possible to make levitation with a self-propulsion only by electrostatic field, which shouldn't be possible according to Earnshaw. And he showed this mathematical in 1842. Now, the reason why he came to this conclusion is that he didn't use ionization as part of his considerations, and this system can work without PID loop or other feedback systems. So I consider this an exception of the Earnshaw theorem and the new branch in electrostatics. This system is not able to work in vacuum. So the characteristics: no aerodynamics, no visual propulsion, can stand still, can move fast, self-level control is self-propulsion, self-stabilizing and auto-centering. And at low voltage, that means that it's low voltage is the voltage where the levitation stops or partially stops. It starts to react as an animal, wobbling and jumping. And when you have 4 ionizers, I call it a horse, and 1 ionizer, I call it chicken, because the behavior is like that. With the too high voltage, it acts as a Russian soldier marching in a Moscow parade. Now, this is the basic shape of the levitator. What do we have here? Here we have a large surface which looks to the upper plate, which is charged negative and is attracted. This will go to a point, and here you have ionization. This leaf is made from metal, and it should be conductive, but it's also possible to make from paper or other materials. But then you have to coat on the outside, you have to coat it with some aluminum foil or carbon that is electrical transport the current. So here we see I use negative in the upper plate. The body is attracted. If it would be a circle, it will be attracted totally to the upper plate. It will get the same charge as the upper plate, and it will move down, and the charge will change. It will start to be positive, and then it will go up and down. So it will be like the bells of, what's the name? The bells of, okay, bells of $100 bill. Okay, whatever. Yeah, forgot. Okay, the levitator is made from 14 micron aluminum, or non-conductive non-conductive with a 0.5 millimeter material in the rim. So here in the rim, I put or a PLA of 0.35 or a half millimeter of what's it called? Nylon wire. Okay. This is for to make it more robust. Okay. Okay. The force on the levitator. We have electrostatic force up, attraction, gravitational force down, and an ion wind that can, dependent on the way the point is directed, it will go up or will go sideways. Here I have a sample of trajectory. It's between 110 millimeter, and the width is about 60. What you see here below is the mirror. It can work on wood, it can work on water, it can work on everything except a plastic table. Here is an extreme example of what happens. We see here the corona, that is the attraction force, and here we see the ionization on the point. Okay, by turning the levitator in one direction, the attraction will be this direction and the ionization will be the other direction. And this is what moves the levitator in the opposite direction. Single levitation. Okay, it's possible to make a single levitation by putting a counterweight on the leaf, and then it will go to the opposite direction. Okay, here you have an example. This is the counterweight. And if this is in the field, it will turn to the right and move to the right. Here I have a sample of chocolate paper. It will do the same, it will work. This is a chocolate paper which has really paper and aluminum foil. Okay, the weight is from LDPE foam, low density polyethylene, and this I call the chicken levitator. Here are other samples of chicken levitator. Here you see one with a 4 millimeter neon. This will light up when it moves inside the field. Now all of them are about 45 degrees. You can do it until 90 degrees. You can move it, and when it moves more, then it's not stable. This is what I call the horse. It's made from 4 leaves. And this, for example, this is straight, and this will not move, it will stay in the field. Here we have 2 leaves, and both are bent 22.5 degrees. And this will move. And here you see also a needle. What is convenient with LDPE, that you can push needles inside, which other materials it's more difficult. Okay, here you can see what happens. You see the levitator is hanging inside the field. So the corona is pulling on both sides, but ionization is pushing in one direction. Okay, now one of the things that influence is pressure, humidity, and temperature, of which humidity is the most strong influence. And I give you an example here. Let's say I have here on 60, humidity on 60, I have an input power of around 2 watt. Okay. Now at 65, it's already 4 watts. So from a difference of 5 in humidity, the power goes up twice. And the levitator that is with a weight of 65 millimeters, this will not work above 65 humidity. Okay, for larger levitators, the trajectory is also larger, and the sensitivity of the humidity is less. And the strongest influence on the strongest negative influence on the humidity is the trajectory and not the levitator. The levitator, never mind if it's low humidity or high humidity, the amount of energy that he needs to levitate is nearly the same. Okay, between 48 and 53 is the lowest power consumption, but I believe that this should be more elegant, this line, but I didn't use the consideration of pressure and temperature, which didn't change that much in the time that I make these measurements. Okay, this is to show what happened with the voltage on the trajectory in relation to humidity. So for to make a levitation at low humidity, 10 kV is enough, but if you go to higher humidity, you need like 50. Lifting capacity. The maximum weight of a single levitator can lift depends primarily on the strength of the lifting force it generates and the surface area of the object upper face in parallel with the levitator plate. And if I want to have more upwards force, I need to make the upper part of the levitator larger, and which is possible through a little bit of bending. Okay. Okay, combining multi-levitators, the lifting capacitor will be significant increase. Each levitator contributes in lifting force. Maybe I will show. I don't have. Okay. Always having objects. Okay. Okay. Here we have a comparing of weight to power. If I have a weight of 1 gram, and this means the best case, a low humidity, I have nearly a half watt, and basic levitator is 1. Okay, worst case, it will be 1.5 watt. If the weight is 4 gram, it will be 0.83 watt. Worst case, nearly 3. And the amount of basic levitators is 4. Now, this is related to scaling. In principle, it's we dealing with, when we scale, we work in 3 dimensions. But electrostatics is 2 dimensions. I'm not totally agree with that. I think it's 2.5, because electrostatics works also on the side. Okay, here I have calculated, if I want, for example, I want 1 kilogram, what will be needed? I need 450 watt. For 10 kilogram, I need 4,000. For 100, I need 45 kilowatt. This is an estimate, and I believe this could be true or better. This is a comparing of energy to 1 horse levitator. These are test results. And you see different sizes here. This is the height of the levitator, and it's a horse that has 4 collectors and 4 ionizers. The length is, let's take this one. This is a quarter meter height with a length of 400 millimeter, a weight of 10 grams, and the energy that is needed is 13 watt on a humidity of 60%. The input voltage on the low side, it's 8.5. The calculated output voltage in kilovolt is 70 kilovolts. And I want to explain this. This is not the real measured value, because the impedance of the whole system reduces the voltage on the trajectory. The trajectory will need to be 800 millimeters. Okay. So, for what is useful? First of all, the system is against shock and fire. And as far as I know, is the lowest cost for levitation with propulsion in compared to other systems. The low energy enables it to work with batteries. In education, it could make a strong motivation for young people to learn physics. Experimental devices for testing floating objects. So let's say you want to have a floating object and you want to see the influence on by sound or ultrasound or electromagnetics, high frequency. This is a good device in making experiments. And also the measurement effect include principle. Then there's games. I can show a game from 2 ghosts that are fighting together. And if in the moment that one touches the other one of them will die or will fall down. Inventing interesting and new levitators like UFOs and things like that. The most interesting thing that are working on this in this moment is medical. It has the ability to eliminate viruses and bacteria and allergies, and this is a byproduct. It was not intended, but when I made the experiments, 2 things happened. First of all, I'm a heavy smoker, and the lower part, so the grounded part of the trajectory got golden. But this is from the electrostatics that attracted the smoke and put it on the lower part of the trajectory. The second thing, my son has psoriasis, and he came one day and say, from the time that you make experiments, the psoriasis went down. So I'm looking for a company that's able to check the ability of the system to eliminate viruses and bacteria and all of different kind of things. Okay. So it cleans also the air in smoking area, like when you are in an airport and you go in the smoking area, it smells terrible. It will be able to clean the air there. Okay, for sure. Okay. Okay, data. The largest that I tested was 250 millimeters height. The fastest speed recorded is 4 meters a second. The limitation is centripetal force, which is related to the diameter of the trajectory. It works without grounding plate on water, sand, wood table, plastic table need grounding plate like aluminum foil or metal. The highest weight I tested was 6 grams. I think it was higher. Okay, minimal requirements. A good high voltage power supply between 10 and 50 kilovolt. The power supply that I used can go up to 100 kilovolt. A mini digital scale with a resolution of 0.01 gram. A good humidity meter, aluminum foil, nylon or PLA, LDP packing material, contact glue, 3D printed template for Levitation. This is 3D printed and makes it faster to make the levitators. Okay. This is a short, simple explanation of electrostatic levitation. For more information, you can look on YouTube, WEPRC. And if you have questions, you can send me by email. Now, there is another thing that I like to discuss. It calls the critical disruptive voltage. It's the voltage that happens between charged objects, and it is used by engineers in high voltage transmission lines. And what is important to see here is not so much the value that comes out from this, but the different, the environment influences the critical disruptive voltage. So this is the voltage that you, in principle, get jumping of electricity. Okay, let's see, we have here the atmosphere, okay, temperature, T, and T is below. So if the T goes high, then the value here goes low. So in principle, if you work with high voltage, you want to have a cool environment. Atmospheric pressure, B. If this value goes lower, let's say vacuum, okay, then this value will go low. So that electricity jump over will go more critical. And so, okay, now the humidity is for some reason in high voltage transmission line, they keep 30 kilovolt per centimeter, so it's 3000 volt per millimeter, which in high humidity, it's more like 2000 volt millimeter. And I hope to adjust this formula more to my requirements in the future. Okay, now I'll show you a few videos, if I can. Tim, are you able to show some videos?
Yes, absolutely. So Al, why don't I put this, I'll take this one out. Let me put up that video. There we go.
Okay, here we have a controller, and I stop it for a moment. Okay. Okay, we have here a controller that is able to change the voltage, the current, and the power. It's possible to limit the voltage, to limit the current, and to limit the energy. It has also an oscilloscope inside. So this is very important if you want to see leakages, unwanted leakages, and the behavior of in general. Okay, the levitator that you see here, okay, it takes about 2 watts. This is 120 millimeters height and 200 millimeters width. Okay, so here you can see the values. And in the moment, it's working as a voltage control. Mostly I work in current control. So, okay. You can put the next video. Okay, this is a sample of what I want to use in measuring the influence on the surroundings. What you have here, the negative plate, and here this is grounded, but this is open. This is how you call it? Open. Here, what you get inside here, you get the ions pushed down, and they push air molecules down there through the well, this here, I don't know how you call this. Tim, what's the name?
So let me see. So you should have an emitter, and then you have your collector underneath, it looks like.
Yes, but it's not closed, it's open. It's wow. Russian. Okay, you know, okay, I forgot. Okay, whatever. Okay, next video.
Okay, and I think this is our final video that we have for you.
Yeah. It's only possible to upload the 3 videos. Okay, here you have a levitator with 2 leaves, and Below is a mirror. Okay.
Now, Al, is this connected to the track using a string?
No. The upper part is connected to a negative output. You see the white wire?
So it's just levitating then. There's no string holding this up?
No.
Oh, that's
It's
amazing.
you see it two dimensional, but if you see it in 3 dimensions, it's real magic. It's real magic.
Yeah, that's absolutely amazing. I thought that it was being suspended from a string, but
No.
amazing,
It's
amazing.
there are no tethers here. I hope I was able to explain how it works, because if you look, the two leaves are bent sidewards, so the ions push on the backside of it.
Well, and Al, if you're open to it, at the end of your presentation, if you're open to having people do replications of this, I think that this is straightforward enough. It looks like it's something that a lot of people could at least try and build themselves. It would be exciting to have experimenters try and do this.
I'm looking for somebody that can help me with writing a book of all that is related to this. In the whole process of years that I made this, and I wrote a lot, but it has to be organized.
Okay. Well, and if you put some contact info, you may have it already in the end of your presentation. Why don't I go back to? Is that your final slide? No, you have more
No,
slides.
there's another one, but
Oh, okay.
um, there's a physical critical voltage. It's important for everybody that works with high voltage that this exists, and that if you look up in the on the internet, you will find um, different formulas, because there are things like the smoothness of the wires and things like that. So for to make this a useful tool, it has to be adjusted to the situation of the equipment that I use. Okay. Here there are nice toys. They're all wireless except this one. Okay, this is a Franklin bell. It has an antenna and it charges up the plate here. And on the other side, the plate is grounded with aluminum foil on the bottom. And this goes to left and right. This is electrostatic rotor. It's difficult to see here. This rotates by electrostatics. This is ionic rotor. This is different. So ions pushed this is from a bottle. Okay, this is pipe ball. Okay, here this is electrostatic swing. So you see here a circle, and there's also antenna here that receives the charge of the trajectory, and this starts to be negative. And when this comes up, this will be attracted and comes up and start to be also negative, and that will be pushed to the other side and comes here with discharge and moves up and down. Okay. Then I have an EMP detector. What happens is the system is in principle DC, but because the ionizator is inside the field, you get the AC component, and you can see this with the EMP detector. So this is electrostatic indicator. So you can see it's positive or negative. And this is the controller, which in principle is a buck controller. And there is an oscillator inside, which a B-class sinus generator. Okay. I want to see. Come. Presentation. Video. Come.
And it looks like that's your final slide. You're doing a calculation right now for us, right?
I have another video. I uploaded another video.
Oh, okay.
You see?
I think I do.
Okay. Now here you see a different levitator. It's made from two circles, and you can say that this is a simulation of the Tic-Tac cube, because the Tic-Tac cube had also this kind of strange things below. And this, you can see this is the pushing force by ions of this levitator. And as now it's totally free moving. Okay, that's all. I don't hear you, Tim.
Sorry. The fact that you're able to make it go in circles like that, and the other one, the fact that you're able to make it follow the track, is absolutely amazing. That is so cool.
It's yeah, and it works automatically. It's a part of the field. The field wants to keep everything inside and regulates it.
Yeah.
So I'm ready to hear questions.
Well, let me do this really quick. When this thing finishes playing, again, this is so cool. I love watching that video. So I'm gonna take the video out. Let me bring everybody in though. We need to give Mr. Al Baur, and let me see. We need to give Mr. Al Baur an enormous applause. Al, thank you so much. Thank you so much. Oh, and I missed Mark. Mark, I'm sorry about that. I was looking for you and I couldn't find the window.
Oh,
yeah,
no worries.
Al, thank you for presenting that. It was a great presentation, and when you put the videos up, I remember you sending those to me. It just blew me away. I was like, "Where's the string?" And then Jarod was texting. He's like, "There's no string. It's floating." I'm like, "Whoa, okay." So, well, do you guys have any questions for Al?
I think we have a lot of questions.
Yeah.
So if I understand this correctly, you have the plate on top, the plate on bottom charged. That's where the energy is entering the system, right?
Yes and no. I used the lower plate is grounded, okay? And I use them because I want to make measurements, but it's not really needed. You can do it without with the ground plate. You can, I can show you, it moves over water. It can move over a wooden table. The whole idea is that the levitator needs to get rid of his ions. As long as he gets rid of his ions, he will move and he will levitate. Okay, so it's possible to make it levitate without the ground plate. Okay.
Okay. Well, eventually, wouldn't you have a buildup of ions in the air to a point where they're kind of equalized and be less efficient without a ground plate?
Say again?
If you don't have a ground plate, wouldn't you eventually build up an amount of ions in the air that would make the craft less?
Yes. The current will go higher. Well, will be a little bit higher. But it works, and works stable.
How heavy can the samples be? Can the craft be?
Say again?
How heavy? How many grams can they be?
I didn't get it.
Oh, he's asking about weight. I think this is like lifters. I think these are very light, like milligram sized.
No. It's grams.
Oh.
Grams, yes. But I believe it's possible to go to the kilograms. Only it will be a large device. I will elevate the weight, but I'm limited in my place. Okay. But okay, very important. Let's say I have a levitator of 60 millimeters height, and I compare this to a 120 millimeter. So I make the same, but I make it twice the size. Okay. Then the weight goes up 4 times, but the power only twice. The power goes only up twice.
Okay.
So this works better in small scale.
Well, I'm not sure about that. It's easier because you need lower voltage, but I'm not sure about it.
Wonderful. Well, does anybody else have questions for Al? Oh, Jarod, go for it, sir.
So in that very last one where you had the tic-tac kind of thing with the "we come in peace" on the side, first off, I love your little artistic touches on that. I was laughing very hard. It was wonderful. I had a question though. On the center base there, you had foil around there. Was that foil causing any interaction on it, or because you had the other one floating around the track without anything to pull it around those corners?
You have in principle, you have 2 cylinders which are interconnected with low density polyethylene. Okay. But if you would put the polyethylene on the upper part, the attraction will be very high and it will go to the upper plate. So you need to not, if you want, I try to make it like tic-tac. So by closing the upper part, and I didn't get it to work. I believe when it make it larger, one day I will succeed so to cover it totally with non-conductive material, okay? But it has to be lower than the conductive material. If not, the charge will, it will be attracted too strong to the upper plate.
I do have one follow-up question as well. So taking this to the craft that we observe flying, those things, if they are having some kind of electric track like you have, that track has to be to the surface and like the ionosphere, right? It has to be really, really far away and really, really strong electric fields. Have you done any calculations for that to try to estimate how they're doing that Earth ionosphere waveguide lifting?
I contacted a person that's supposed to be a professional in the ionosphere. And I want to know which kind of voltages are there. And if there's information, I got the idea that there's very little knowledge about it. Okay. So I have no idea how to relate to this.
Thank you.
Okay.
Awesome. Yeah. Al, thank you so much. Thank you so much. It is truly, truly a pleasure. Truly a pleasure. I mean, those videos just blew me away. I didn't realize that you could do so much just using ions. I mean, I used to work with lifters, but you know, we had tie downs, we had wires, we had all that stuff. You were doing so much without any of that apparatus that I used to need. So.
I was going to ask. I came in a little bit late, and so I was noticing like the one that was on the track. There's like a black portion, and then there was the the foil portions. And is that a different material than the like for instance the one that was going around the track?
If I understand the question correctly, you asked me the connection between the levitators.
I'm just asking what kind of materials you're using. In other words, I'm just trying to figure out if the principles are the same as lifters, because it seems like the way in which it's just staying in one place instead of having a constant ion flow and something keeping it in one place. It seems as though there's some other effect that is going on there. And so I was just curious about the material. Like for instance, you had a black material with the two foil things that were the foil things were what were giving it the movement to the side, but then the black portion seemed to be what was holding it, what was making it stay in place underneath your whatever the apparatus was there. And so I figured those are two different materials, and I'm just curious what the black material is.
Okay, the black material, maybe you go back, Tim, to the
I can put this one.
Okay, you see here white. Okay, the connection between the two cylinders is white. This is packaging material, so low density polyethylene. Okay, it's also exists in black. It's the same. So it has no. It's an isolator.
Just insulating plastic. Okay, well, we are just about at the top of the hour, so let me do this. I'm going to take this down, and Al, let's put our hands together again one more time for Mr. Al Baur. Al, thank you again. This is the coolest stuff I've seen in a long time. The fact that it levitates, it follows the track on its own. You've got no wires, no strings. I mean, that's truly amazing. So thank you so much. And when you have more videos to showcase for us, I'd love to have you back in the future. So
I have a lot of videos.
Okay, well, I will reach out to you then. We'll see if we can bring those in. Maybe we could do lab updates or something like that.
Okay.
Okay.
And Malik, the next time I want you to help me because my English is not good enough.
I think
so. You can translate me some words from Hebrew to English.
Yes, I can act as a translator for you.
Oh, okay. Well, Mark could. Okay, well that would work then. Okay, so Mark.
You know, I'm original from Holland, so if you don't know Dutch, it's also okay.
Yeah, well, Mark can translate from Hebrew, so we can make that work.
Okay.
Wonderful. Okay, well, thank you so much. So I'm going to take everybody out except for Dr. Nathan Inan. And let me see, Nader, welcome, sir. Thank you. It is awesome to have you back. It is awesome to have you back. Let me apologize again for the technical issues. Today's been a little bit of chaos, but so you're going to be talking about the Meissner effect.
Yes, that is right. In fact, I'll go ahead and share screen and see if you're able to see my screen here. There we go. Allow.
There we go. Okay.
We good?
Perfect. Yeah.
All right. Should I take it away?
Yes, yes, sir. Thank you very much.
Absolutely. So thank you, Tim. Thank you, all of APEC community. I am super excited to share this talk with all of you. So I had the pleasure of giving a talk for APEC some number of months ago. It was my first time. Tim kindly invited me back, and that's just because I have too many things to say to squeeze it all into one talk. In fact, I was hoping over time I can just kind of share a multitude of talks that are all kind of connected. So you'll see some remnants of the last talk in here. If you saw my first talk, I do a little refresher, and then I move us into a new topic on, as you can see the title, superconductor Meissner effects for gravitomagnetic fields. So as Tim stated, my name is Nader, or I commonly go by Nathan Inan. I am full-time at Clovis College where I teach. I also am associated with Fresno State and UC Merced. And in particular, I'm associated with Texas Space, which is a company that was founded just at the end of last year. We're focused on cutting edge research, propulsion, gravitational wave communication, quantum cryptology, basically a whole assortment of quantum systems that we hope can revolutionize human technology. So this is one more topic that would be kind of under the umbrella of what Texas Space does. So as I was saying, I have a multitude of topics that I'd love to share. Last time I got into classical coupling of electromagnetism and gravity. So I looked at gravitational Faraday-like flux rules and some applications, and in particular, new formulations of gravito-electromagnetism, often abbreviated GEM. So there's some other items under that general category of classical coupling of electromagnetism and gravity that I won't be touching on today, particularly transduction between electromagnetic and gravitational waves. That's a favorite in particular of my advisor, Raymond Chow, under whom I did my PhD and with whom I still continue to collaborate. And so I hope at one point we'll be able to share more on that. And he, in fact, gave a talk for APEC on that topic. But today I'm going to focus on quantum coupling of electromagnetism and gravitation. In particular, I'm going to talk about London theory and curved spacetime and gravitomagnetic Meissner effect in a superconductor. I hope that maybe in a future talk, I could continue on and talk about a few more topics under that category, namely quantization of the gravitomagnetic flux by a superconducting ring, the possibility of gravitationally induced propulsion of a superconducting ring, and Ginzburg-Landau theory in curved spacetime. So those are two major categories. There's a bunch of other major categories I hope I can talk on later, particularly gravitational wave detection, generation, and transduction, quantum effects associated with gravitational waves, Aharonov-Bohm effects is another favorite, fluctuation dissipation theorem, coupling gravity, the gravitational field of the expanding universe. This is stuff that's associated more with for instance, things that Jim Woodward has worked on and my colleague Lance Williams. I'd love to share some of that down the line. And most recently, I've been working a lot on dark energy, dark matter, quantum gravity, and the cosmological constant problem. In fact, just a couple days ago, one of our papers was published on this topic and another one was just accepted. So I hope to be able to come back to APEC and share more on that. But for today, this is the particular paper that I'm going to focus on, which is superconductor Meissner effects for gravito-electromagnetic fields in harmonic coordinates due to non-relativistic gravitational sources. Now, I apologize. I know I'm kind of notorious for long titles. It's kind of like a mouthful right there. But there is a reason. It's because I want to revisit this topic with other aspects, namely visiting this topic when we are not in harmonic coordinates and visiting this topic with relativistic gravitational sources versus non-relativistic gravitational sources. So sort of in advance titling this paper the way I did so that later I can write other papers and the change will be obvious. So this paper was published in a special section on Frontiers. The section was called Interaction Between Macroscopic Quantum Systems and Gravity. And it was really just such a blessing to be invited to submit a paper to this, because that category is like exactly what I work on, which is macroscopic quantum systems and gravity. So in that section of Frontiers, which if you're interested, you can check out the link later. The paper is available. It's also on the archive. One of the editors is Modenese, who I believe also has given a talk here for APEC, and is unquestionably an expert in these topics. So he was on the editorial board, and there was 11 authors who submitted papers, Modenese being one of them. Giorgio Papineau is also a major figure, almost like a legend in this area of physics. Martin Tajmar also did an experimental paper, all submitted to this section of Frontiers. And so I'll be sharing about half the content of my paper during this talk that was submitted and accepted here for that section of Frontiers. So here's the kind of the abstract for this talk, so you kind of know where I'm going to go with this. So as it states, there's much discrepancy in the literature concerning the possibility of a superconductor expelling the gravitomagnetic field, just as it expels electromagnetic fields in the standard Meissner effect. There's contradicting results found in at least 18 papers written collectively by more than 20 authors and published over the course of more than 55 years. So this is a long-standing issue, and I decided to just sort of like delve in, almost like write a review paper and come to my own bottom line mathematical conclusions that would be, I hope, kind of give the final result. So the primary purpose of this talk is to explain the reasons for the discrepancy. So I don't want to just put my 2 cents in. I want to explain why there are issues with the other results that others have come to. Now, I will tell you up front, bottom line of what I found, which is that, as it states, the key result is that the gravitomagnetic field is expelled from a superconductor with a penetration on the order of the London penetration depth, which is the penetration depth for the magnetic field, when an appropriate magnetic field is also present. So there's this like coupling that has to happen, as I'll show you mathematically. So my hope is that this effect could lead to some of the first experimentally observed interactions between the gravitomagnetic field and a quantum system. As I wrote here, the associated Meissner-like effect may also lead to gravitationally induced levitation, maybe even propulsion, just as the Meissner effect allows for magnets to levitate. So there's not a whole lot of experimentally observed manifestations of the gravitomagnetic field. And in fact, there's, to my knowledge, none in a laboratory setting. So that's my hope, is that this could be a mechanism for us to do that. All right, so let me give you a little bit of historical context of where this all came from, because as you can see, this is a long-standing topic. Some of you might be familiar with the Gravity Research Foundation. So you can see all the big guys in there, Einstein and Maxwell and Newton and so forth. And so what this Gravity Research Foundation does is they offer awards for essays. And as it states, the main purpose of the Gravity Research Foundation is to encourage scientific research and to arrive at a more complete understanding of the phenomenon of gravitation through its annual awards for essays on gravitation, with the expectation that beneficial uses will ensue. So this essay competition has become very well known among gravitational physicists. Roger Babson was essentially the founder of it. I think this paragraph is really funny. I'm not going to read the whole thing, but it cracks me up because he's a businessman, but he uses like the laws of physics to analyze business. So he uses like Newton's third law of action and reaction, to talk about financial effects or the stock market crash. What goes up will come down, right? So nonetheless, so he put his money into physics, which is pretty cool. And he has a very unusual story. And now this, I think, is worth stating what his intentions were. So it says here, his views were reflected by the wording in the announcement of the first essay competition that said the awards were to be given for suggestions for anti-gravity devices, for partial insulators, reflectors, or absorbers of gravity, and for some substance that can be rearranged by gravity to throw off heat. Although not specifically mentioned in the announcement, he was thinking of absorbing or reflecting gravity waves. So this has gone on since 1949 all the way up to the present year. Awards have been given out year after year after year. And the closest I ever got to getting an award, I never did, but they have this honorable mention that they do. And so basically they choose like the 5 best, and then everyone else is sort of like not the 5 best, but they'll take from those people who didn't win, and they'll select like maybe like 15, 20 people, and they'll give them an honorable mention. And kind of the nice thing about it is you get an automatic publication in Modern Physics D, usually anyways. So this is a topic that I'm not going to talk on today, the gravitational waves coupling to the 0-point energy, the photon modes of the superconductor. I'd love to share on that again later. But I do want to highlight really how competitive these awards are. I mean, look at some of the names. So first of all, Doug Singleton, who I have the pleasure of being associated with from Fresno State. He won second prize a couple of years ago, and he was stoked. Now, Robert Wald basically wrote a textbook on general relativity. Frank Wilczek, Nobel Prize winner. Robert Wald wrote a textbook, as I said. Hoof, Nobel Prize winner. Lawrence Krauss, Frank Wilczek, there again. Lee Smolin. And so if you go down the line, Sean Carroll, you find all these names, Bekenstein, of people who are well known in physics for good reason, right? I want to highlight that Peng and Tor one, by the way. Though they are not nearly as prominent as some of the other names, their work in their winning essay is connected to what I'll be talking about today. Now, Papini, notice there, is also 5th place winner back in '89. You got Unruh, Wald, Bekenstein again. And I want to highlight these, Anandan and Chow. Chow was my prior advisor, and that paper also was on gravitational wave antennas. So kind of going down the line, you can see there's a lot of really interesting people who have won, Hawking and Penrose and Sciama and Misner, going down the line. And the reason I'm going down the line is because all the way to 1953, that's the one that I want to focus on right now. Like I said, it goes all the way to 49, but I'm going to stop at 1953 with DeWitt's essay. So DeWitt wrote an award-winning essay for the GRF competition, New Directions for Research in the Theory of Gravitation. And I think only DeWitt would start a paper like this. He says, before anyone can have the audacity to formulate even the most rudimentary plan of attack on the problem of harnessing the force of gravitation, he must understand the nature of his adversary. Very poetic, actually. Now, the interesting thing is there's no equations in this essay, which definitely doesn't happen nowadays. All the essays are much more math heavy. And he expresses a pessimistic view on the possibility of harnessing the force of gravitation. So he says, maybe I'll kind of go to the main thing. He says in bold there, the weakness of this coupling has the consequence that the schemes for achieving gravitational insulation via methods involving fanciful devices such as oscillation or conduction would require masses of planetary magnitude. And that's pretty much been the standing belief for a long time, that gravity is just so weak that you can't really do anything with it. Now, interestingly, fast forward to 1966, that's DeWitt right there, by the way. He looks like a pretty intense guy. And I don't know if you can recognize who the cool long-haired guy is. That happens to be Kip Thorne. So in 1966, DeWitt wrote a groundbreaking paper on superconductors and gravitational drag. So that's what I'm going to kind of camp on here a little bit and discuss. So it only had 11 equations. It was a letter, but the paper has been referenced by authors hundreds and hundreds of times. It's a founding paper on this topic. So this is kind of the starting point for everybody. And what DeWitt does is he starts with a Lagrangian that is well known for relativistic charged scalar particles in covariant form there. And he just immediately writes down a Hamiltonian. And it's a little bit overwhelming, like where in the world did that come from? So I spent quite a bit of time really studying where this Hamiltonian came from. But I'm going to cut to the chase with what DeWitt found. So he reduced it to first order in the metric perturbation and first order in velocity. And he claims that this is that first order Hamiltonian. And you can see there's like a extended minimal coupling rule there. The usual minimal coupling rule is, as many of us know, is just simply P minus electron charge times vector potential. But there's this extra piece that involves the mass of the electron times the gravito vector potential. And so DeWitt then claimed that it is not just the magnetic field, but it's the sum total of the magnetic and gravitomagnetic field that vanishes in a superconductor. So he concluded that there's this new Meissner effect that involves not just the magnetic field being expelled, but also the gravitomagnetic field being expelled. So if that's to be the case, then it's like game on with all the stuff you could do with superconductors. I mean, quantum trapping and flux pinning and all of that would apply directly to the gravitomagnetic field, just as it does with the magnetic field. In fact, you could levitate things with the gravitomagnetic field. You could have all kinds of interesting manifestations of the gravitomagnetic field. You could, I suppose, maybe even make something like the maglev train, even upside down air train like they have in China. So kind of all bets are off and you can go wild with this, right? But before we get too excited, not so fast, there are contradicting results for the gravitomagnetic Meissner effect found in at least 18 papers, as I mentioned, written collectively by 20 authors, published over the course of more than 55 years. So, question, can the gravitomagnetic field be expelled from a superconductor? And what you'll find is some say you can, some say you can't, some say maybe if you have special conditions. So I really wanted to attack this issue. And so I started from the top. I wanted to derive everything from scratch to see exactly what assumptions are made and what is the bottom line on this. So a little bit of quick background. I'll try to move through this math relatively quickly, but just so that you kind of know where I'm going with this, here's our Minkowski flat spacetime metric. You can see the signature I'm using, introducing the perturbation. As you know, the perturbation could be thought of as like a gravitational field in flat spacetime. So it basically characterizes how flat spacetime could expand or contract or be warped and distorted and such. And this is my general relativity in a nutshell slide. So you start with the metric, you develop the Riemann tensor, the Ricci tensor, the Ricci scalar. We all know you build the Einstein tensor, throw in a stress energy tensor, and voila, you have general relativity. The cosmological constant will be ignored in this talk because it's not relevant to the types of experiments I'm going to talk about. Now, I'm going to go to linearized GR, which is exactly what DeWitt does and which is realistic for lab scale type experiments. So the Riemann tensor, you got to get rid of your second order Christoffel symbol terms, introduce a weak perturbation, and then move down the line, develop your Ricci tensor, your Ricci scalar, and your Einstein tensor for linearized GR. Now, often what's done is harmonic coordinates are used. DeWitt doesn't state that explicitly, but it's fairly evident from his paper. So standard procedure, it's like textbook stuff. You start with your linear coordinate transformation. You apply that to the metric perturbation. You get something that looks kind of like the gauge-Friedman electromagnetism. You introduce a gauge condition, which looks a lot like Lorentz gauge. You apply it to the trace reversed perturbation. And then the Einstein equation cleans up very nicely. It becomes just a wave equation. Now, because of that, it's very common in the literature to continue moving in the direction that's very analogous to electromagnetism. Define like a gravitational 4 potential with your gravitoscalar and gravitovector potentials. You can write a Maxwell-like field equation now, and you can define gravitoelectric field and gravitomagnetic field in a fashion that looks a lot like electromagnetism. Now, just to make sure we're all on the same page as far as this gravitomagnetic field, sometimes called the Lenz-Thirring field, sometimes called frame dragging. That's why, by the way, DeWitt's paper was called Superconductors and Gravitational Drag. So Earth drags space-time in a sense in the direction of rotation about its axis. Technically, any spinning mass does so. It's just very weak. Now, it has been detected in an astronomy context. Gravity probe B detected deviations in line of sight towards stars due to this frame dragging. So we know it's not just a mathematical prediction of general relativity, but it has actually been measured. It just hasn't been ever measured in a tabletop lab or a terrestrial lab. And it's most definitely never been used to manipulate anything in the way of like how the magnetic field and the Meissner effect has been. Okay, so we're going to talk about non-relativistic sources. We start with the ideal fluid stress tensor. In the non-relativistic limit, basically you only keep your 0, component and your 0I component, basically kind of like your energy density and your momentum density, and you get rid of the stress. You can define a mass 4 current density. And now I did explain in quite a bit of detail in my last talk that in this non-relativistic approximation, the time variance of the gravitovector potential vanishes. And so I won't go into the details on that because I'd be kind of repeating much of my last talk. I'll just mention that you lose that Faraday law. Okay, so in other words, there won't be a gravitational Faraday law in this approximation. Now, don't forget we need the equation of motion. So you start with the geodesic equation of motion, use that metric, that perturbation that I just described that has the scalar potential in the diagonal and the vector potential on the off diagonal there. Okay, so you arrive at the typical Maxwell-like equations for gravito-electromagnetism. I just remind you, of course, and you've got your Lorentz-like force. It does look a little different from the Lorentz force in electromagnetism because you can't force the analogy. If you just walk through the math, those additional two terms are there, and the magnetic force has a factor of 4. It just all comes out naturally. Now, as I mentioned, you lose the Faraday law, and you also lose that additional term in the force equation. And now, for the purposes of studying what DeWitt did, where he's looking at like, something that rotates at a constant rate, so it's a stationary mass current, as we call it, then you find that the displacement current's not relevant. It's 0. And you lose that last term on the force equation. So basically, you end up kind of like in a magnetostatics approximation, where you basically just have Gauss's law, Ampere's law with the current density, and then your Lorentz-like force there. Now, notice on the right side the constants there. So we all know that gravity is very weak, and it's because of those constants. So the 4 pi g is 10 to the minus 10, or maybe closer to 10 to the minus 9. That's Earth's gravity, basically, compared to flat spacetime. Super, super small. Flat spacetime being 1. So this is like 1 apart in 10 billion or whatever it is. So the gravitomagnetic field is even much weaker than that. And that's because of that 10 to the minus 27 for the gravitational magnetic permeability constant. That's what makes it so difficult to measure and manipulate in the lab. It's that mu sub g there. Okay, now let's back up and start with DeWitt's Lagrangian, which is, like I said, a standard Lagrangian. You could even find it in Jackson. And we know it's a legitimate Lagrangian because if you apply the Euler-Lagrange equation of motion, you arrive at the Lorentz force in curved space-time. So in other words, you got your geodesic equation and your Lorentz force all in curved space-time, comes out naturally from that Lagrangian. So we know the equation of motion is sort of like your litmus test of whether a Lagrangian is legitimate. So we know that Lagrangian is legitimate. It gives us the right equation of motion. So if we proceed to find a canonical form momentum with the usual procedure, take the derivative of the Lagrangian with respect to the 4 potential. So this is like a covariant form. Then we get this covariant minimal coupling rule. Looks very nice. Kind of matches the usual coupling rule that we get in non-relativistic Lagrangian mechanics. Now, here's the weird thing. You go to apply a Legendre transformation in the usual fashion, and the Hamiltonian is 0. It's like, wait, what? Sorry, I had to throw that in, right? I wonder if I could grow my hair like that one day. Sideburns are pretty cool too. Anyways, so it's like 0? Why? Now, it's not new information, by the way. If you look in Jackson looks at this in flat spacetime, because Jackson's not a book, of course, on general relativity and curved spacetime. But even in flat spacetime, this covariant Hamiltonian or Legendre transformation vanishes identically. So it's kind of a known thing. And Jackson, as you can see here, references another author, Barut. So this kind of led me down a little bit of a rabbit trail. Like, okay, what does Barut say about this? So I looked at what Barut says, and Barut says, well, you can actually define a Hamiltonian tensor, which I thought was unusual. I haven't come across that before. And the interesting thing is this: the canonical equations give you the right equations of motion. So you get back to where you should be as far as the equation of motion. Remember, that's the litmus test. But clearly this is not satisfactory because the Hamiltonian is not a scalar quantity. So you can't interpret it as energy. So how are you going to move into quantum mechanics and promote it to time derivative operator and all of that? Okay, so as I looked more deeply into this, I found out the Lagrangian is singular. And if you go into this topic of symplectic manifolds, and you find out that the reason the Hamiltonian vanishes is there's this constraint. It's a relativistic 4-velocity constraint that's behind why this happens. And another way of looking at it is that there's the so-called Hessian matrix vanishes. And that's characteristic of a singular Lagrangian. All right, so how do we find our way out of this to get a Hamiltonian like DeWitt did? Well, it turns out you have to reparameterize your Lagrangian. So the Lagrangian we were working with is parameterized, as you can see here, in terms of proper time d tau, integrated between two proper times tau 1 to tau 2. But if you play with the math a little bit and you factor out a Lorentz factor dt d tau, and you bring it outside, then your action is now parameterized in terms of dt, the coordinate time. So notice it's integrated from coordinate time 1 to coordinate time 2. And now that Lagrangian, it's still covariant, but it's parameterized in terms of coordinate time. That's the one we want to play with. And I guess DeWitt had insight in this because that's actually where he starts, interestingly. Now, some complain about this because they're like, uh-oh, you're breaking up space and time. We don't like that because relativity is all about unification of space and time. But I've already explained why we kind of have to go this route. Okay, so moving forward, we got our Lorentz factors defined in the usual way, but we break it up into space and time pieces. And now our canonical momentum is found by the derivative, the spatial derivative, or I should say the derivative with respect to the 3 velocity, not the 4 velocity anymore. Now you find that this now becomes your canonical momentum. And so now we get this new minimal coupling rule. And this I never saw in the literature anywhere. And I have like, I think 110 references in the paper. I have scoured the literature exhaustively. And evidently, perhaps just nobody has taken the time to really develop the math very carefully. So this is, I argue, the true minimal coupling rule you have when electromagnetism and gravity, to first order in the perturbation, are coupled to a quantum system. And you can see from that first term on the right side, you got your canonical momentum picks up that minus E vector potential. That's standard. You know, if you got rid of gravity, everything else will be gone. But then you have all these other terms that involve metric perturbation terms. That's the coupling of gravity coming in there. Okay, so you can now show, it's a lot of yucky math, I'm most definitely not going to do it, that if you now apply a Legendre transformation in terms of 3 canonical momentum and 3 velocity, you do arrive at a Hamiltonian that very much matches DeWitt's. I say very much because there is one little extra detail here that does kind of matter. You notice that the G, the inverse metric here, the G subscript ij, has a tilde on it. That's sometimes called the spatial inverse metric. DeWitt wrote his Hamiltonian without the tilde, and he actually even just says that he has his Gij is the inverse metric. But it turns out you can show that those are not equivalent unless you're first order in the metric. Minor detail, but worth mentioning because some of the other papers actually harp on this quite a bit. Now, interestingly, as I scoured the literature, I found a lot of different Hamiltonians that came from that Lagrangian. Papini and his colleagues come up with this one. These 3 authors come up with that one. Birchinger came up with this one. And I'm like, what's going on? Why are there all these different Hamiltonians? They all look so different. All right, well, which one is the correct one? The answer, interestingly, is all of them. Why? This shall tell us. One ring to bring them all into the darkness and bind them. Got to quote Gandalf the Grey. In other words, turns out you can unify all of them. You have to play with a lot of math, and you have to use those 2 metric relationships to show it, but they're all unified. I felt really good about that, by the way. Kind of reminded me like a very, very low-level version of unifying physics, you know, kind of like, I don't know, Ed Witten unifying string theories into M theory. Not that I even remotely compared to that, but it just feels good to see everything unify. So we're on the right track. We got the right Hamiltonian. Now I want to make some physical predictions. What do we get numerically? Is it actually possible to get the expulsion of the gravitomagnetic field? So I searched for what I thought could be the most substantial source of a gravitomagnetic field in a terrestrial scenario. And the world's largest flywheel to power storage system using a superconducting magnet bearing, it's in Japan. And this bad boy is 2 meters in diameter. So it's like larger than the average human being. It weighs 4 tons and it rotates at 6,000 RPM. I mean, personally, I would not want to be around this thing while it's spinning. So that's a lot of mass spinning very fast. Hopefully that can give us a pretty strong gravitomagnetic field. Because remember, the Earth is the only gravitomagnetic field that we've measured at this point. But we want something we can do in the lab. So crunch some of the physics, start with the gravito-ampere law to figure out what we're going to get for the gravitomagnetic field. Apply Stokes' theorem. We have basically a mass current. And I find this is the expression for a cylindrical, symmetric, revolving mass, which is what this is. Find the flux that this would have through some cross-sectional area. From there, use that flux to make our way over to the gravito vector potential using Stokes' theorem and arrive at a gravito vector potential of 10 to the minus 21. Obviously, extremely small. In fact, by comparison, I did a separate calculation for a low Earth orbit satellite. And if you have a low Earth orbit satellite, it's got the benefit of being really close to the Earth, because obviously the closer you are to the Earth, the stronger the field. And you're, spinning as fast as possible, at least for satellite, as far as I'm aware. And there you get like 10 to the minus 3. Obviously, way, way, way better. But you have to be in a low Earth orbit satellite when you do your experiment. And I'm not sure if that's something that's practical. So if we're talking about what DeWitt was talking about, which is in his paper, he's referring to a terrestrial-based system. He talks about a ring. He even throws in some numerical values that are clearly just talking about a ring that's circled around like a cylinder, and that cylinder is spinning and such. So that's what we got going on here. Okay, so if we go back to the Hamiltonian now and we expand it out to first order in the metric perturbation, then I get this, right? Now, it was interesting to compare this to what DeWitt said he had. Some observations. First of all, DeWitt's missing all the terms I have after this this ECA not here. All these other terms are not there, and they're all first order in the perturbation. Okay. It can also be shown that terms involving H00 and Hij, those are hiding in there, are many orders of magnitude larger than this coupling of the gravito vector potential to the canonical momentum. But if you look at DeWitt, he kept that. You see how he has like a squared binomial here? If you square out that binomial, you basically get the capital P vector multiplying the H vector. So he kept that in a sense there. So he dropped stuff that's larger and kept stuff that's smaller. Yeah, I'm not trying to pick on him, but I'm just trying to be very meticulous about the analysis. He also has a term. Now, this is where it does get into a little bit of the physics that you don't want to have a prediction that's not correct. So DeWitt's Hamiltonian predicts that there's a coupling between the magnetic vector potential and the gravito vector potential. But you can actually show that that term is not there when you multiply everything out properly. It cancels. So that coupling doesn't occur. And one more thing. You notice there that if you square out if you square out these parentheses, you're going to get the H vector squared, which is technically second order in the perturbation. So you can't even really call that first order. In fact, I did the legwork. It's really nasty. There's actually 24 more terms in the Hamiltonian that are higher order magnitude than that one. So if you're going to keep that one, you got 24 other terms that you're supposed to keep in there. Okay. And then lastly, this is arguably the most important part of the DeWitt Hamiltonian analysis, which is that his Hamiltonian implies a minimal coupling rule of the form P goes to P minus EA minus MH. But you saw that the coupling rule I arrived at was much more complicated, or it involves several more terms. So it has the one he has there. It's kind of buried right here. It's this gamma MCH H0I. So it's there, but there's other terms. So interestingly, this incorrect Hamiltonian and incorrect coupling rule appear in at least 21 papers. So I felt it's really important to kind of set the matter straight. Now, if we state a second order in the metric perturbation, because that's kind of what DeWitt did inadvertently, it's nasty, not going to lie, okay? I did list the terms from largest to smallest. Obviously, the rest energy, MC squared is largest, all the way down to the smallest. I grouped together terms that are of common order, and I did find, interestingly, there are terms that are second order in gravity, like they involve phi squared, that's the scalar potential squared, that are actually larger than some terms that are first order in gravity, like the one that involves the coupling of the gravitational vector potential and the canonical momentum. So it's just a mess. You got to be careful about all that. Now, I tried really hard to get to DeWitt's Hamiltonian, and I found the only way to get there was a rather artificial condition, which is to have really small electric scalar potential and magnetic vector potential, but not zero, just really small. That allows you to keep certain terms and eliminate other terms. And so you get something that's really close to DeWitt has, but still there's issues. Now you'll notice that, as I said, there's a lot of papers that have the DeWitt Hamiltonian to first order in the perturbation. All these papers have it. And so, like I said, I felt like we got to get the record straight on this one. Now, I'm not going to pick on other people's papers, but I'm going to pick on mine or one that I was a part of. So this paper from 2014 or 2013 was a paper that I assisted with my advisor, Raymond Chow, and some of our other colleagues. And admittedly, we had that Hamiltonian. Now, it's so interesting because this journal, which is this quantum theory, a 2-time success story, the Yakir Aharonov Fishrift, has a lot of heavy hitters who wrote in this Fishrift. David Gross, Leggett, Aharonov himself, Leonard Susskind, Davies, Hartle, Carroll, Barry from Barry's phase. All right, but I'm going to focus on our paper. So in our paper, there we have it, the minimal coupling rule that was borrowed directly from DeWitt's work, the Hamiltonian that was borrowed directly from DeWitt's work, and then here it is. The claim that there's a coupling between the magnetic vector potential and the gravito vector potential that would allow some sort of mediation between electromagnetism and gravity via the quantum system. In reality, doesn't actually appear in the mathematics. So it wouldn't actually occur physically. Okay, so enough harping on that. Let me move on now to figure out whether we can get a gravitomagnetic Meissner effect. So if you're dealing with, say, Cooper pairs in the zero momentum eigenstate, standard procedure when you're dealing with superconductors, then you can show that the supercurrent velocity ends up being this expression. And normally, what you end up having when gravity is not there is this last parentheses isn't there because the H vector is not there. And in this first parentheses, that gravitational scalar potential is not there. In other words, you just get that the supercurrent velocity is dictated by the vector potential. That's standard London theory. So we know it reduces correctly. Now we can pop that into the charge current density and the mass current density, because remember, we're going to play with both electromagnetism and gravity. So we need both of those. So we drop the velocity into both of those, and we get these two current densities where I define some quantities. Capital lambda L is sometimes called the London constant. I didn't make that up. It's in standard London theory. Alpha is essentially just a correction factor due to the gravitational scalar potential. So since you have the scalar potential of the Earth, the gravitational scalar potential, which causes the Newtonian gravity that holds our feet to the ground, you can't get rid of that, right? That's a correction that's going to have to be there. Now, beta involves a term involving the rest energy and any electric scalar potential. And notice that both these current densities have the gravitovector potential in there. Okay, so now take those and let's look at the two cases, the magnetism case and the gravitomagnetism case. Let's just isolate them each independently first. So for the magnetic case, this is standard textbook superconductivity. You basically have your London constituent equation, as they call it, where your current density is proportional to your vector potential. Drop that into Ampere's law. You get a Yukawa-like equation, and it leads to an exponential decay solution for the magnetic field, where it decays on the order of the London penetration depth. Standard Meissner effect right there. Now let's go over and do the gravitomagnetic case. So with the gravitomagnetic case, you're going to start now with the gravito-Ampere law, which has the mass current density. You're going to drop in there this London-like constituent equation that only has gravity. See, we're leaving magnetism out of the mix for now. Now, notice that both those equations have minus signs, whereas on the left side, only one of them does. That matters because once you then put them together, you get a plus in there. That's what we could refer to as a Helmholtz-like differential equation. It does not have an exponential decay solution. It has sinusoidal solutions. So there is no gravitational Meissner effect if all you have is the gravitomagnetic field. Okay, that was not discussed by DeWitt. He didn't look at the case where you have just the gravitomagnetic field. Now, what is most interesting is what happens when you have both the magnetic field and the gravitomagnetic field. So now you end up with coupled differential equations. See, on the left side, that's your standard equation for the magnetic field, but it's got an additional term on the right side that's got the gravitomagnetic field. On the other side, the Einstein equation gives us the gravitomagnetic field equation, but the magnetic field also plays a role. So they're coupled, right? So you got to decouple them. And sometimes decoupling requires that you go deeper into derivatives. So if you take an additional Laplacian of both sides, so now you got like this fourth order derivative, but they're now decoupled. Pure magnetic on the left, pure gravitomagnetic on the right. And this k squared, interestingly, is the same for both of them. Now, what you can show is that the first term in your k squared, the one that has this alpha mu naught capital lambda, is absent if there's no magnetic field. And so that's what led to the Helmholtz equation that gave us no gravitomagnetic field, Meissner effect, if there's no magnetic field around. Okay, so now we're recreating what we just saw on the previous slide. I did the previous slide as a warm-up so we could see what happens now when we have the coupled system. So we just recreated the fact that you don't get a gravitomagnetic Meissner effect if all you have is a gravitomagnetic field. Now, on the other hand, though, if you do have a magnetic field, you can show that the first term of this k squared is larger than the second term. Now, that then leads to a Yukawa-like equation for the gravitomagnetic field equation. And so we do have expulsion of the gravitomagnetic field. So the magnetic field needed to be there to assist this process. And the way that I interpret this from kind of like a physical point of view, you know, my advisor, Raymond Chow, always challenges me to think intuitively, think physically, not just mathematically, which I appreciate that very much. And it occurred to me that what's happening basically is that if you have the gravitomagnetic field come in, it couples so weakly and with the wrong signs that you get no expulsion. What happens though is if you also have the magnetic field there, then what it does is it drives the supercurrent in a direction needed to generate a gravitomagnetic field that cancels the gravitomagnetic field that you have externally. So it acts as like an additional mechanism that produces the cancellation you need so that you get expulsion of the gravitomagnetic field. That's probably the best I could put into words what's going on there as far as I understand it. So the bottom line I end up with here is that the supercurrent in the presence of only a magnetic field, you get the standard Meissner effect. Nothing new there. The supercurrent in the presence of only a gravitomagnetic field, you get no gravitomagnetic Meissner effect. But if you have both the magnetic and gravitomagnetic field together, then you get a Meissner effect for both of them, of course. And interestingly, it turns out that the penetration depth for the gravitomagnetic field ends up being the London penetration depth. So it's not like it's a huge depth that would be unmeasurable. It, in principle, from the mathematics, should be comparable to the magnetic field's penetration depth, the London penetration depth. All right. So as far as acknowledgements, I'd like to thank Professor Raymond Chow, as I mentioned, for helpful discussions, as well as Professor Douglas Singleton, Professor Gerardo Munoz. Both of them are at Fresno State. Dr. Ahmed Farag Ali, a very close colleague of mine, Dr. Lance Williams as well. I'd like to thank Texas Space for their support. Check out the logo and be ready for some cool stuff coming out of Texas Space, hopefully in the near future. And lastly, I'd like to thank Tim Ventura and the APEC community for the opportunity to present this research. Thank you.
Awesome. Well, Nader, thank you, man. Thank you. Jim Woodward was writing me. I just emailed him back. He's like, "It's such an amazing presentation." I was like, "Yes, Nathan Inan classes us up. He classes our organization up. So thank you for presenting."
Yeah,
and
absolutely.
I would love to have you back in the future if you're open to it. If you have more stuff
Absolutely.
you want to share on, that would be super cool. So let me do this. I'm going to bring the guys in, and let's put our hands together for Nader, Dr. Nathan Inan, thank you so much. Thank you so much.
Sure.
I'm genuinely so thankful and appreciative to have like real serious theoretical physics, that's mathematically based. And I mean,
Thank
you
you.
are one of the few people out there who's really doing great work in this area. So,
Thank you. I really appreciate that.
oh yeah. Well, do you guys have any questions? Let me see. Do you guys have questions for Nader? Ah, okay. Let me start with Drew this time. Drew, go for it, sir.
Hey man, way over my head. 99.9% of it, I like recognize some alphabet stuff. But if you could just, if you could just dream up a test, and we could build it or something, somehow manage to build an actual test of this. I kind of got lost. What is it we're trying to see? What's the net result of this? We build something, it spins or it doesn't spin, or does it float? Does it sink? What's the effect we're trying to confirm or
That's
deny?
That's a really good question, Drew. So, we want to see a manifestation of the gravitomagnetic field expelled. Now, I think what the challenge is that because, at least from what I found, you need both the expulsion of the magnetic and the gravitomagnetic, then the magnetic tends to dominate the system. And so if you don't have sensitive enough equipment, you're just going to see the same thing you normally do for the Meissner effect. So I imagine what you would be looking for is a levitation that would be slightly different than you would have for just the magnetic field. Like, for instance, the object perhaps depends how much levitation. I mean, like with superconductors, as we know, it can levitate in such a way that the entire weight of the magnet is levitated, right? But if you had an additional extra little force, maybe it would drift up, for example. Like, let's say you fine-tuned a system where you have perfect levitation. It doesn't go up, it doesn't sink, it's just levitating. But then you have the gravitomagnetic field present as an additional expulsion. Maybe it would drift very little. And this is me just attempting to picture visually what the manifestation would look like. Does that kind of give a sense of?
Yeah, I mean, so the net result is this is a form of levitation?
Yeah, you could say that.
Anti-gravity or whatever?
I tend not to use the word anti-gravity only because we're not eliminating gravity, or we're not introducing a gravitational field that propels. We're just simply using the gravitational field to reduce the weight of something, for instance, right? And so I realize that the word anti-gravity obviously carries a lot of baggage, unfortunately, as you probably know. There's been a lot of sort of fringe science on that. So I would like to just simply say, if you're asking like, why would we bother with this? Like, why would we care? I would suggest it's because up to this point, as far as I know, we've never observed anything gravitational in the lab besides just literally dropping a pencil. Like, there's never been a manifestation of anything gravitational from general relativity that would put us in the right track toward truly harnessing the gravitational field. Is that a little too abstract still? You'll have to forgive me because theorists have trouble coming down to earth sometimes.
Dude, I got lost an hour or 56 minutes ago. So anything you say now is just, okay, that's cool. No, I loved it. Absolutely loved it. Yeah. I'm going to make sure Charlie watches this thing because I know he's not watching it right now. So I'm going to make sure he watches it, and then I'm going to find out what the hell it is that just listen to.
Well, Drew, thank you. Let me go to Jarod next, and then I think I can go to Shiva after that. Jarod, go for it, sir.
It was awesome Presentation. I had a question regarding the flywheel that you were going for. Now I recognize that was a rotating mass, but
yeah,
I half expect you to go into superconducting magnetic energy storage, which is, instead of a rotating mass, you have a stationary superconductor that's really big, and you run this huge current through it, and the current doesn't lose any, of its momentum. So
yes,
were you ever looking into those to be able to apply any of your not anti-gravity ideas?
You know what? I think what you're alluding to is the fact that this thing runs on superconducting magnetic bearings.
Well, the superconducting No. So the superconducting magnetic bearings were just a way to translate that angular momentum into, energy again, right? That was the conversion aspect. SMES, SMES, superconducting magnetic energy storage, doesn't rely on actual like moving parts, right? Superconducting magnetic energy storage, as far as I understand it, is just a big old huge toroid of superconductor that you're storing up a bunch of current in, and that current flows continuously without resistance, right? And so then when you want to extract that, you can put an inductor next to it and you can extract that current from the thing, right? So
I think I get what you're,
for what you're describing, right? Rather than try to make gravitational waves or try to manipulate the metrics somehow with something moving, which seems insane for the amount of, energy required. If you don't have to actually move something other than charge, right? That's a lot easier to do, and you can get a lot higher energy density by just moving charge rather than by moving, the whole nucleus of the atom.
Okay, I think I see maybe what the issue is. By the way, are you able to see my screen again?
You are not presenting at the moment.
Oh, here. Let me put it back up. There we go.
Oh, cool. Thank you. I think maybe the issue that we're discussing, at least kind of implicitly, is the fact that you have to have a source of gravity, and then you also have to have a superconductor that is in the presence of that gravitomagnetic field. So in other words, do you see the diagram I have right here?
Mhm.
So
Yes.
I believe that when you're talking about the superconductor, it would be like, for instance, that ring right there, which could be very light. It's got to be a superconductor, and then you'd have some supercurrent in there. But then you have to have a source of a gravitomagnetic field, and that's the challenge because it's so weak. So ideally, like if you have something as massive as the Earth rotating, that would be great. But then you have to be off of the surface of the Earth. Otherwise, you're not going to observe the relative rotation relative to your lap. So I think it sounds to me like your question, in a sense, is addressing that there's two aspects to the system. There's the superconducting ring that experiences the field, but then there has to be a source of the gravitomagnetic field, and that's where that storage device, that flywheel, that ginormous flywheel, was my best shot at what DeWitt is talking about as having a massive spinning system. Does that make sense?
Yes.
Yeah, so I'll point out over here, for instance, this is DeWitt's paper that I was discussing at length, obviously. If you check it out, basically, it's right where he says that you're going to basically pretend you've got this like really massive, here it is, suppose the mass initially at rest is set in motion or until a constant final angular velocity is reached, right? And then down here he says, assuming the dimensions of the ring to be a little larger than the rotating mass, then he goes on to get an order of magnitude for the supercurrent that would be produced in the superconducting ring. So, but the thing is that DeWitt doesn't put any numbers in the way of what capital M would have to be, what the rim velocity of that rotating mass would be. So there's no engineering aspects. It's almost like just a pure theory paper in that sense. And that's where I attempted to go a step further and figure out, is there anything on Earth that exists that could actually be used? And if so, what numbers do we get out of that? Does that help a little?
Yes, it does. Thank you.
You're welcome.
Awesome. Thank you so much. Let me go to Shiva next. Shiva had a question. Shiva, go for it, sir. You know what, Shiva? I can't hear you.
Yep, there we go. Sorry,
okay.
Mike was physically muted. Yeah, okay. So just following up on what Jared was saying there, I think he was just basically presuming, mass energy equivalence. Got a bunch of energy rotating that would be, similar to mass rotating, and I think that's what he was getting at there. But going back to, are you familiar with all of the various rotating superconductor experiments that were done that showed a reduction of weight? Some of them were actually performed at the European Space Agency, and they, showed a reduction of weight, and there was never any adequate falsification of those results. There were actually replications of those results in a variety of labs. And then it sort of fell off. I know Tim actually did a lot of work in tracking down one of the major researchers in that area, because she kind of disappeared for a little while, and then, finally found her again after she was, found working in, kind of the private sector, which is probably why she had gone dark. So I'm just curious how much you have looked into this, because it seems as though you're trying to provide a theoretical grounding for why these rotating superconductors might actually have a weight reduction effect.
That's a great question. Honestly, actually, I hear a little feedback. I am not nearly as knowledgeable about the experimental tests that have already been done. I mean, put it this way, I definitely have never come across a paper where anybody has ever said we detected or observed or measured a gravitomagnetic field in the lab. Is that what you're implying, by the way, that has actually happened?
Yes, it was the weight reduction is what they specifically reported. I can find the it's kind of hard to find now, but it was something by the European Space Agency. So they were one of the early ways in which I was first exposed to this back in the aughts. That there was a real result from the rotating superconductor experiments, and it wasn't just some of the other. There are a lot of the ones that were a little bit more well known because of little anti-gravity communities and things like that. But there was there's Dr. Ning as one of the.
I wondered if that's who you're talking about. Is that who you're?
She's one of the people I'm talking about. That's the researcher that disappeared.
I thought so.
Yeah.
Yes.
The European Space Agency has there's a report by them. I can find that for you, I'm sure, again.
I would appreciate that. Yeah, I would love to know more about that, because I'm not aware of any actual concrete numbers that have ever come out where anything, but it sounds like from what I just heard you say, it's still being sort of debated anyway. So maybe there was never an official declaration of we've measured it, like for instance with LIGO measuring gravitational waves.
It was very official that they measured it. They replicated it numerous times. They could find absolutely no, they could not eliminate anything that would get rid of the effect that they were seeing, and the fact that just kind of dropped off is weird. But yeah,
it is weird. And what I'd be curious about is to see the match between the experimental data and the theoretical framework that was used to determine the experimental data's characteristic. Is it gravitomagnetic, or is it something systemic to the experiment? I'd be really curious to know about that.
That's the thing. I'm not sure that they had good theory. They were just running experiments based upon reports of effects. And you just like when there was all those tests of the EM drive that they eventually, there were a lot of replications of it, but they eventually found that there might be some reason why that they're getting that effect that is not what it was initially reported as. I'm sure you're familiar with that. So yeah, like I said, I'll just have to find the thing and shoot it off.
I would appreciate that. Thanks so much.
Awesome. Well, we've got just about 2 minutes left. So I think, and actually Shiva is up next. Why don't I do this? If nobody has any other questions, let me see, I'll take down that, and why don't we go over to Shiva? But before we do that, guys, please put your hands together one more time for Dr. Nathan Inan.
Thank you.
And Nader, you are more than welcome to come back and present anytime, man. I know that you have you earlier you rattled off a list of 10 more topics, and I was rubbing your hands together. I'm like, yes. So yeah, no,
I'd love to.
It's so cool to have rigorous mathematically based theory. That's something that you're doing, and then Dr. David Chester is doing that as well, and it's really exciting.
Thank you.
Wonderful. Okay, well, I'm going to take everybody out except for Shiva Meucci. Shiva, thank you so much, man. Thank you so much. So you're going to be doing a presentation on the neoclassical interpretation, and so you have a lot of stuff. Actually, I've been begging you for the audience. I've been begging you to come back and present more, because
I really appreciate it.
You've been talking about a modernized aether theory in some ways, kind of an interpretation of what people are describing as the quantum vacuum foam and things like that, as well as vortex dynamics and cymatics. And these things resonate so strongly with research that I've done in the past and what other people have seen. I'm just like, he has something. You guys have to listen. So I keep begging you to come back on and present.
Yeah, I really appreciate that. Yeah, I think it's one of those things like, hey, even Frank Wilczek recently put out a book mentioning the ether. So, you go back to 1951, Dirac saying that we have to have an ether, or 1920, Einstein saying space without ether is unthinkable. Yeah, there's just a lot of ways in which it's disappeared. So that is a great lead in to this presentation.
Absolutely. Well, thank you again. I'm really excited. And again, I should apologize to everybody. I had a really nasty cold this week, and so my brain is kind of halfway there, and so
yeah, I didn't sleep very well myself.
Well, yeah, it's part of it's that time of the year, right? It's hot as heck out there, but
oh yeah.
So let me put that up, and I will remove myself from it. And thank you yet again, sir.
Thank you. All right, so I'm going to, I guess I'll do a little bit of a recap. And the funny thing is, to lead from the previous to this one, that we will actually get to a reason why you should separate space from time, as he mentioned in his presentation. So to just kind of recap where we were, because this is, I'm trying to keep things concise, and there are just so many different ways in which I could go with this, and so trying to keep it down to just 1 hour has really been teaching me to get small bite-sized pieces here. But going back to my previous presentations, basically what we're looking at is the fact that there was this basis of relativity, that relativity existed for 15 years before Einstein. There was basically in 1889, George Fitzgerald is who gave us the first publication of the change factor, in its earliest form, and there were people who developed an ether version of relativity, and understanding how they came to the idea of relativity, what's the mechanical reasoning, is going to be something that will lead a thread up through all of modern physics. Now, whenever we talk about ether, a lot of times people are going to immediately think that is, the ether and relativity they don't go together. And that is the problem that I've been working 20 years to solve, that belief that is complete falsehood. There's absolutely no reason to believe that whatsoever. Relativity persists with an ether, and we're talking about a luminiferous ether, a light-bearing medium, a physical reason for waves, and that sort of thing. So let's get to my first slide here. I need to switch over to that screen, and let's see. All right. So starting with John Stuart Bell, he is when it comes to scientists who actually remembered and demonstrated that they actually understood this subtle differentiation that occurred right there at that historical point. John Bell, with this quote, is the very most recent scientist that is a well-known name in physics, etc., that actually demonstrated an understanding of this. And so he says basically is that we need to go back to relativity as it was before Einstein, when there was an ether and a preferred frame, and that a lot of our ideas come from this sort of optical illusion. Now, when he states these things, a lot of people, if they are brought up in the typical teaching regime that teaches you something that is based upon Minkowski's presumption of isotropic constancy, his words here are going to sound strange, and I want to clear that up, and that's what we're going to work on today. Is we're going to talk about a little bit. I'm going to give you a little bit of theory beforehand, because you have to understand that I want to use the experimental record we already have to show you something that is a new way of understanding what those experiments are telling us. And that is what John Bell was talking about at this point. So the experiments we're going to start talking about is going all the way back to the Fizeau experiment, and it's going to lead up to Michelson-Morley, Sagnac experiments, round-the-world Sagnac, half-field heating, and Ru-Yang-Wang. So this is just kind of a quick overview of some of the things I want to touch upon. And basically, Fizeau proved proved Fresnel's prediction of partial ether drag. Michelson-Morley was not a null result. That when you use the partial drag that was proven by the Fizeau experiment. It actually predicts the Earth's motion. The Sagnac experiment, it utterly contradicts the idea of constancy, the one that you can find 5 different quotes from Einstein saying that you have to abandon constancy because there's 2 types of constancy. There is the illusory, well, there's the perspective illusion that we are treated to by the mechanics of the universe type of constancy, which is a 2-way effect. And then there is isotropic constancy, which is this 1-way effect that was presumed by Minkowski after the fact and then foisted upon Einstein. Then there's the round the world Sagnac experiment. It demonstrates an east-west bias. Hatfield Keating also demonstrates an east-west bias, and Ruyang Wang shows that all of our explanations of the Sagnac effect that were prior to present day that were based upon acceleration, rotation, etc. He completely falsifies all of those explanations. So, give me just a moment to take a drink here. So when you falsify the idea of constancy, and what I mean by this is isotropic versus anisotropic constancy, and I'm going to keep using this term, and it helps that you'll understand that there's a very subtle differentiation point. There's 100 years of confusion in the teaching, and there are, like I said, there are numerous people up until the mid 80s, apparently, with like I said, with Bell being the last scientist I know of who actually remembered this aspect of the history of physics. And that is that there is a type of constancy that is something that can occur in 3 dimensions that is exactly equivalent to 4D space-time within limits. So there are rational differences that occur when you are using the Poincare-Lorentz theory of relativity, which is based upon ether and was mathematically equivalent. This is well known as a historical, any historian of physics will tell you that they were called mathematically equivalent for a very, very good reason. And so, but one of the things that occurs when you use this anisotropic constancy instead of the isotropic constancy that Einstein repeatedly condemned, you get no twins paradox, no additional infinite 3D realities without evidence. And now I talked about this before, that Minkowski, by promoting the dimensionality of reality, gives you infinite additional 3D realities within a given moment. That is that's what promoting the dimensionality of something does. It gives you infinite possible additional versions of the previous dimension. There's no magical ideations. And what I mean by this is that there is no need to have something you simply believe but do not understand. So fields or actions without actors, such as waves, you don't need to have any of that. You can actually have fields that make sense in a very physical, mechanical way, and you can have waves that are based upon the way in which a medium behaves. In other words, a wave is a behavior, not a thing that exists necessarily. So then there's no arbitrary selection of rays from spherical emanations. There are aspects of the way in which something emanates spherically because of the ways in which we use this improper teaching of relativity. You can select rays in a somewhat arbitrary fashion that can cause problems when you're trying to do something like holography. And there's no solipsism. What I mean by this is that the constancy that we are taught, in other words, the one that I'm telling you is the false teaching of constancy, whereas there is a constancy that does actually really exist. But the one that we are taught is that you have this solipsistic sort of, everything is related to you or to your current frame that you're calculating from. And as I've brought out in previous lectures, basically remember that I am not saying that Minkowski space-time is worthless or directly wrong. It is a tool that can be useful because of the fact that there is this equivalence, this mathematical equivalence between these 2 versions of the theory, these 2 interpretations. Because there's the equivalence, you can use Minkowski and get lots of right answers, and also get something where you cannot separate an illusory answer from a correct answer. And there's a lot of other missing information that you do not get, that you do get through Poincare and Lorentz. So this then allows us to have rational mechanics. Wow, the lack of sleep is really showing. Rational mechanics for de Broglie-Bohm trajectories, as well as rational mechanics for entanglement effects and how those work in a fluid paradigm. Then there's also mechanical reasoning for a host of other various abstractions. But the thing is, you can have absolute simultaneity and different clock rates. So what I'm doing is giving you an idea of what it is, why I need to tell you a bunch of things that I'm about to tell you, and I'm giving you some sort of a preloading what it is that I need you to kind of focus on, what it is that we're explaining. So absolute simultaneity versus relative simultaneity. Relative simultaneity comes specifically from Minkowski's conjoining of space with time. Absolute simultaneity, however, is something that is some people might think gets rid of the idea of changing of time. I'm not saying that. You can have both absolute simultaneity and differing clock rates. So the interpretational difference leads to some numerical differences at extremities that are difficult to explain. I'm not going to get into it in this lecture, but basically the distances to stars can be calculated based on additional information from the CMB. Of course, it's as I said, there's 5 different quotes of Einstein saying constancy must be abandoned, and it's because one of the things that we've been taught is the idea that constancy is somewhat like the word, and it's not. Constancy is not constant. All waves in a homogeneous medium, the wave goes through at a constant speed, and whenever you're told the word constancy, you believe that is what they mean, but that is not what is meant by constancy. Constancy is an effect that is in no other way phenomenon, and for it to work in the way we are taught, you have to have a fourth dimension to warp reality around this version of constancy. Relative simultaneity is an effect that is additional clock rate differences. It is the exploitation of the fourth dimension, which gives you these additional 3D realities to use. So whenever you have a conflict within a 3D reality based upon this constancy effect, you can actually exploit the additional dimension to explain how this internal inconsistency can be consistent with an additional dimension. It's, in other words, the version of relativity we are taught today that is not like the one that Bell was talking about, and not like the one I want you to entertain and understand. It gives you this version of reality where you have to have additional 3D realities to make up for the fact that there is this conflict that a lot of people have noticed, and it's made them, whenever you're first exposed to relativity as, when you're first in college or wherever it is that you're first exposed to it, sometimes there's this feeling of wanting to reject it. Well, it's because there is this way in which people immediately recognize what appears to be a conflict within an internal inconsistency. Now, that internal inconsistency is, I will be explaining how that is illusory in 3 dimensions as well. In other words, that you do not actually require a 4th dimension. But once again, there's this subtle differentiation I'm hoping to make you understand in this lecture that, like I said, it hasn't been taught in, at least 30 years. So he required this 4th dimension to assume isotropic constancy. And so basically, you have to either choose constancy as an illusion and reality has no self-conflict, and this gives you an anisotropic illusion, and I'll explain that in a moment. And that is the type of constancy that is still functional. And then constancy is real, and 3D reality has a self-conflict that you can resolve by adding infinite additional 3D realities. And once again, as I pointed out in my previous lecture, just as Einstein was upset about Minkowski's initial meddling, and then Minkowski dropped dead, and Hilbert loved him, and basically everybody pressured Einstein about it. The thing is, you need to be able to separate Minkowski space-time from relativity. This is a very crucial thing, and everyone is taught that these two things are exactly the same. They are not. Minkowski space-time is a barnacle that was added onto relativity, wherein he makes an assumption. He assumes isotropic constancy instead of anisotropic. And what that means is that the speed of light is exactly the same in all directions, and there's no two-way effect. So let me get into this a little bit further. So, some of my thing here. This is a Gedanken experiment. Some of my words are actually missing from it, but so what I want to explain to you now is how it is that you can actually understand this whole idea of constancy and what it all means. So, well, some of the first things that you're taught is that whenever there's someone, traveling on a train that is going at 100 kilometers per hour, and they fire a bow and they can fire a bow at 100 kilometers per hour, then what's going to happen is they're going to actually shoot that arrow at 200 kilometers per hour. And so whenever there are these, these ways in which they're adding together, you're going to see that like as an arrow is shot beside you, if you're already going 100 kilometers per hour as a bow is shot beside you in that train, then what you're going to see is the arrow just kind of traveling beside you and falling to the ground. It's going to be, well, it's pretty much going to be just straight falling to the ground as you pass the fellow on the ground. However, for this idea of constancy, whenever you're shooting like a laser, everybody who sees the laser's first wavefront is going to see it passing them at the speed of light, even if you're on the train and you're traveling very near the speed of light. Now, in the bows, in the version where you're seeing someone shooting something ballistic, like a bow and arrow or a gun or what have you, what you're going to see is if you're going almost the speed of a bullet for a second, let's say, then that bullet is going to slowly pass by your window as it drops to the ground because it's going slightly faster than you. But with what we're taught about constancy is that it's going to be passing you at the speed of a bullet. So, and it doesn't matter that you would, intuitively understand that it should be traveling at a different speed. So how can we make this work in reality? And so what I've got here is a Gedanken experiment where I want you to imagine that there's a time gun, and I could alter time inside of a train. And so inside this train, if I slowed time inside the train and closed all the windows, what would you experience? Well, what you would experience is normal. Everything would be happening normal to you. You would, because your thoughts would also be altered by this change in time. And so you drop things, you have all of your typical physical effects. You wouldn't notice anything until I opened the windows. And when you looked outside, what would you see? Things would be happening outside very rapidly. In other words, people would be passing by, speaking at a very rapid rate because your time is slowed. They are fast by contrast. So now let's say that I want to trick you into believing in constancy. How could I do that? Well, all that I would need to do is if you're traveling at the speed of a bullet, and when you normally would look outside, you'd see a bullet passing by you very slowly as it falls to the ground. The fact that it is passing by you because you're not going the full speed of the bullet, I can exploit with my time gun. And what I mean by this is I can slow your time so much that the bullet going past you, when you measure the speed it goes past you, it goes as fast as a bullet. So that takes care of that weird thing where you're like, how can a person on the ground fire a bullet and see this speed, and then a person on the train see the same speed even though they're moving? That doesn't make any sense. With the addition of my time alteration gun here, I have now made it make sense, but I've only made it make sense in one direction. If you do this experiment, then any bullet traveling the other direction will still be going nearly twice the speed of a bullet. So if I instead make it where you must only measure the speed of bullets outside your window on average, then what will occur is if you find out the speed of bullets on average, what you'll end up finding is something very close to what we see with the Lorentz transform. So this is just a demonstration of alterations of time and how that this can be done in a physical environment. And wow, it is dry in here. You're gonna have to give me a moment to have something to drink here. These are old slides that I made some time ago. So I told you about that to tell you a little bit about the Michelson-Morley experiment, because everything in relativity and is based almost entirely on the Michelson-Morley experiment. I'm going to travel back to the Fizeau experiment in just a moment, but you need to understand the physics of what's happening here is that there is the presumption in the experiment that the sun is traveling through the galaxy, the Earth's traveling around it, and we're trying to measure how much light's going to have to play catch up as it goes upstream, and and then when you compare that to how fast it goes back downstream because of the flow of what it's traveling in, because a wave travels in its medium. So that is what the Michelson-Morley experiment was set up to try to determine. It's not just, we can't measure just the slowing upstream because of just some of the restraints in your experimentation. You have to have a two-way effect that you're getting. So in other words, you can only measure bullets outside your window, the average of them. You can only measure two-way effects. And so there is a way in which that would, there's a change that both upstream and downstream, and they do not cancel each other out. And now let me try to explain that a little bit further with the other slides here. So again, you have to excuse me if I'm going into some very deep basic mechanics here, but I need for you to intuitively understand how it is that we arrived at relativity and why we arrived at it and what generated these ideas, and then how that will then go into how we can look at our current experimentation and our current version of relativity in a different light. So when you have a swimmer going across a river, here he's going, if the flow is going to the left, then he's going to have to correct off to the right to actually make it across, to go directly across the river. And here, unfortunately, it's flipped. So we actually have the swimmer starting at the top and going down in this second area here. But basically, if they're going at a certain angle, you can actually have it where when the river is flowing, even though they're going at an angle to this side, they can end up on the other side over there. So just the point is that there is even the direction that you are traveling in your frame can be altered by the relationship of the water's movement to your speed through it. And that's going to determine where you end up, and it's going to determine an angle, actually. So now, one other thing that we need to talk about is the idea of a circular or spherical emanation. So if you are a runner that is running along a wall that can reflect your yell or whatever, then you're going to create a spherical emanation. But that's going to go in a lot of different directions from the point of origin, because we're assuming that the air is staying still. So there's going to be these lines that go in all different directions from our runner on the left here. And it's going to come out in a sphere in all these different directions. But there's only one of those angles that will be the reflected sound that you hear. Only one angle is actually going to return to you in your motion. And which angle that is determined by the relationship of your running speed to the speed of sound. And what you'll find is that if you're traveling at 0.5 c, there are these various angles that determine the distance that sound is going to have to travel. And what I'm explaining to you here is how we got to the solution of the Michelson-Morley experiment, and why it is all from just 1887 to 1889, Fitzgerald already had an answer, and how that answer works. Okay, so this gives you a predefined additional path length that a sound has to travel to go out away from you and back. If it seems to be reflecting on something that you're carrying with you, it would be the same thing as having a wall. So you were carrying some reflective item out to your right. It would still be that same angle, and the sound would have to travel additional distance, because instead of going straight to the wall and back, it's going through the air at an angle. And so there's additional distance that that sound has to travel. So there are two ways in which you can end up making the sound leave and come back and return to the origin, such that you that the sound that goes forward into the wind and back, and the sound that goes out sideways and has to travel that angle, can come back, and both of them can happen at exactly the same time. Now, why am I telling you this? Because this is what it was that Fitzgerald proposed that was occurring, is that there is a physical shortening of objects that is occurring as things travel through the ether that perfectly makes up the difference. Because normally what you'd find is that in the if you look at the diagram over here on the right hand side, and like I said, I'm having to use other slides that I prepared a long time ago, and so I'm just reusing them, so you have to excuse me. This is actually something that was made by my 13-year-old son. But if we look at the second truck there, the first truck is stationary. Round trip time is 20 milliseconds in either direction. And then if we don't have any shortening of objects and any in a normal experiment, what would occur is that the round trip crossways would make it before the one that has to go into the wind and back. So the round trip is 23.094 at half the speed of sound. And then the round trip, into the wind is 26.666. And what you find, however, is that if we were to have a sort of material that shortens as air passes across it, and it happens to shorten by an amount that is described by the Lorentz transform, then what will happen is the round trip going out to the side, traveling that angular path, that's additional. In other words, it's not 20 milliseconds, it's 23.094. And the path that goes into the wind and back will be exactly equal. Now, why is that important? It's because the Michelson-Morley experiment was reported as a null. And that is, they shot light up and back and out to the side and back, just like I'm showing with this truck. Now, what I've shown with this truck, however, is a description of constancy. In other words, if this truck is made out of, or the experiment is made out of material that reacts to air in the way that Fitzgerald described, and that it shortens by an amount that is relative to how fast it goes, and that you can describe it in the terms that we did describe the Lorentz transform, or basically just the change factor, then what will occur is that no matter how fast you go, it will appear as though sound travels the same speed in all frames of reference. In other words, all the speeds that you could possibly go. However, what I've just described with sound, if you were to say that sound is a constant, like light is a constant, because you could only perform this experiment, so that's the only experiment you could perform, it would be an absurdity. It would be, you would have to make reality warp around your expectation. You would have to make your idea, and that is specifically what Minkowski did. Is he warped reality around the idea that it just happens, not that it is an illusion created specifically by the shortening and these different paths. So understanding that that is what occurred is what I'm trying to get across to you here, is that we had a way in which relativity worked because of the way in which objects are shortened. And there was one of the Maxwellians, Heaviside, who actually gave us Maxwell's 4 equations instead of all of what was in the papers. There was a lot of massaging of Maxwell's papers that eventually ended up with Maxwell's equations. And Heaviside actually described exactly how it is that particles would shorten and why they would shorten in this fashion, such that we would have this shortening effect that would be exactly compensatory. So it is a compensatory illusion that hides the fact that light had to travel further in one direction than the other. Now, I've simplified a couple of things because there's also a time component, and Larmor actually proved that time component, I think it was in the 1890s. And so that you have to have both the time component, because, of course, what we're looking at here is the round trip still is increased to 23.094 instead of it being 20 milliseconds. So in other words, you've got to change to the overall experiment time, even though it's still simultaneous. And that gives us the time difference that occurs. There is an actual changing of events. So if I were to put sound clocks, in other words, I made a clock that is dependent upon signals going up and back or side to side, and that sound clock was made of material that shortens because of the effects of wind, that clock would change its timekeeping. In other words, how many revolutions, how many back and forths, that would change according to your speed, exactly as described by relativity. However, to say that sound, a mechanical wave, is constant would be an absurdity, because in the way in which we're told constancy works, with the twins paradox, with all those various paradoxes that require a fourth dimension to resolve. This can be done in 3 dimensions, and 3 dimensions alone. Of course, I mean, what I mean is one moment is 3-dimensional, and then of course you still have a fourth dimension. And the reason why Larmor, Lorentz, and all of those used a fourth dimension was as a handy notation tool to keep up with the fact that there were different timekeeping issues. In other words, they knew clocks would run slow. And so they knew that there was this change to the interaction between objects, even between the particles within an object. Even, you know, the motion of a pendulum still is requiring that there is a transfer between the different particles that make up the pendulum. And so they understood this principle that the evolution of change required that there be some sort of interaction through this electromagnetic field, or it's not just electromagnetism, but it is the etheric field. There would have to be waves that are constrained by the speed of light, and that they would have to travel further distance, and that additional distance would make it occur more slowly. So we had an entire explanation of all of the strangeness that we associate with relativity, which is time dilation and length contraction. And that was all well before Einstein, because Einstein was giving us the electrodynamical part, not the kinematical part. That's why his paper's in 2 pieces. And that is what I'm describing right now as the kinematical part that was delivered by Lorentz and all of the others beforehand. And Poincaré, when you say Lorentz Poincaré is who advanced the ether theory version to be exactly mathematically equivalent to special relativity. So now what we're going to do is travel back in time a little bit here, because what we just talked about was a compensatory illusion, and that by itself has always felt weird to people. And that goes all the way back to when we talk about some of the beginning issues in optics. And I just grabbed a page here because it was easier to make a slide that way. There were these experiments in stellar aberration. In other words, where we would see from one period of the Earth's motion to another throughout the year, the positions of the stars in the sky change, just like if you're running forward in rain that's falling straight down, or if you're driving your car forward in rain that's falling straight down, it looks like it's coming in at an angle. So in other words, the angle that the light apparently was coming in was changed throughout the year, and this is called stellar aberration. I said was changed; it is changed. It continues to happen, and so there were various experiments that they thought would be able to detect the Earth's motion through this mechanism. And to make a very long story short, Fresnel was someone who was working one of the first representations of ether theory and how it might work was given to us by Fresnel and his discussion of the way in which the index of refraction occurs. And so one of the things that he proposed is that the index of refraction was a way in which the ether was interacting with matter, and then that would impact the propagation of light. And that is why you have light being changed in direction when you have refraction in like a crystal or what have you, is that the change in speed is what causes it to deviate. So he believed that this would also be occurring, but only with respect to the index of refraction. So he predicted something in 1818 called the coefficient of ether drag, and that is that objects would drag ether along with it, and that drag would then only partially impart the speed to the light or that was traveling through it. So then in 1851, Fizeau actually did the experiment by running water through tubes, and it turns out that Fresnel's prediction was perfectly corroborated, and it's known today, of course, that he was absolutely correct, and so and by the mathematical amount. But the thing is, it also solved the issue for why it was that many of the stellar aberration experiments were not showing positive results, because it was an exact compensatory mechanism. And so this is, and you'll actually find some quotes by Einstein saying that this experiment was in a large part something that inspired him as well. So one of the reasons that people continue to talk about complete ether drag after this fact is because people just didn't like the idea of a compensatory mechanism. But by 1872, Mascart actually explains that that these illusions happen all the time in physics. There is something called the co-moving. Whenever you have co-moving objects, the Doppler effect is automatically hidden. It's a compensatory illusion. You can send signals back and forth, and if you are co-moving, the Doppler effect in sound will actually have a compensatory effect where you cannot see the Doppler effect, even though it is being inscribed in the air in a different, longer wavelength or shorter wavelength, dependent upon the direction. So it's just like seeing that it is not God being mean to you when you're out in the desert and you think you see water and you're actually seeing, a mirage. That is, illusions occur in physics as just part of physical reality. So just because there is a compensatory illusion that exists does not in any way alter its probability of being true. However, people didn't like it at the time, and so for a long time they tried to believe in full ether drag, and that of course does not work. Now we need to move on to the fact that the Michelson-Morley experiment, the 1887 experiment, is not null. So this is one that you need to understand, because of the fact that right now, some of you who've been following along are like, I thought you were saying the relativity is true. If Michelson's not null, then relativity is false. No. It's some of you should be confused and angry right now, because there are important things that you need to understand about how this experiment worked, why it worked, and how many of the replications work. So this is like I said, we're talking about the experimental evidence and what it is we need to look very careful at. So in the original Michelson, what you've got is the interferometer facing in different directions. If there is a wind, then what you should see is a sine wave of readings, a dual sine wave specifically, as it travels 360 degrees. And I've got some, visualizations over here that should show you. And then on the bottom side here, what I've got are the actual readings from the original 1887 Michelson experiment. And as you can see, they fairly closely fit the dual sine wave of readings, which were expected. But the thing is, Dayton Miller, for 20 years, did hundreds of thousands of experiments that got these same dual sine waves of readings. And so how is it, if relativity is true and there's this exact compensatory effect, how were they getting any reading at all? Well, that's because we need to use Fresnel's coefficient of ether drag in air. So the thing is, one of the things I was going to point out is only Dayton Miller ever replicated the Michelson-Morley experiment. You're not going to be told this because a lot of people don't understand the requirements of the experiment and the very delicate way in which they went about it, that only Michelson and Miller did, and the rest of the experiments that are supposed replications were not replications. One of the things, so there's three different things. They use white light interferometry, not monochromatic. There is something called lock-in that occurs in in anything that is monochromatic, where phase differences are obliterated. And we're talking about very large phase differences can be completely annihilated in, especially in systems with using lasers. This is something that they had to overcome in the design of ring laser gyroscopes and interferometric fiber optic gyroscopes, or IFOGs. And then the third component that makes Michelson and Miller different from all the rest is they did it in open air, which allows ether drag. So what I'm saying is relativistic contraction is true, and so is Fresnel's coefficient. So going back to both Miller and Michelson, there's just understanding that white light interferometry is very, very difficult because finding a single fringe, which a fringe is relative to a single wavelength of light, and attempting to tune an interferometer back then, they would spend hours tuning it, and they would use sodium light because there's a characteristic double fringe with sodium that will allow you to find a central fringe that will allow you to then use white light for the interferometry. White light is not subject to the same sort of lock-in effects that monochromatic light is. This is one of a number of optics effects that Michelson, our first American Nobel Prize winner, was attempting to eliminate purposefully to make sure that you did not have any illusions. And one of the other things that you can do is you can line up fringes very far off with monochromatic light. There's only one specific lineup. Once you have the central fringe in white light, the actual distance between your mirrors in the Michelson-Morley experiment is that exact in distance. They're exactly the same distance within a wavelength of yellow light. So now what I want to teach you about is something called coupled oscillation, or Huygens odd sympathy. And one of the things that you'll find that occurs, and this is to explain what lock-in is that when oscillators are allowed to communicate with a surface, or then what can happen is they can begin to synchronize. And we use this effect in a variety of ways. It is a coherence effect, and this would be the classical way of describing how lasing occurs, is through this coupled oscillation effect. It is a way in which you can have things that are out of phase, and then once they become in phase, then you have the way in which you can increase the actual amplitude of the wave. I've just got I searched out the first paper I could find real quick on coupled systems in optics, and I just found one last night. So that's just one you can. It's easy to find some of these phenomena. So going back to Miller. He was one of the first experimenters to do double-blinded experiments. He used artificial temperature tests, in other words, where he went and said, okay, what would it look like? What will increasing the temperature on one side versus the other, increasing it everywhere? What will the data look like? So he did that. And double blinding means that he specifically had someone helping him in one room that was only looking into a viewport to say where the fringe was, and a person in a separate room who could not be influenced by it to simply write down readings that were called out to them. And both of them were not him. And so he did, like I said, hundreds of thousands of tests at different times of the year, at different elevations, and with different interferometers. So he won the 1923 Newcomb-Cleveland Prize from the AAAS for proving the existence of ether. He blocked the Einstein's Nobel for relativity, and that's not very good, but that's actually what occurred. And a Nobel economist, Maurice Allais, he found additional effects that in Miller's data that also corroborated and correlated his effects with the sidereal day and Earth's orbital position. So we're talking about a very throughout the data, there is a systematic effect that would be absolutely obliterated by the amount of by looking at the average of hundreds of thousands of these tests. So all of them found almost exactly the same magnitude of effect found by Michelson. So it's the unfortunate problem is Miller retained the naive non-relativistic idea, and so his calculation was between 8 and 12 kilometers per second, and specifically that using that naive calculation, the original Michelson experiment detected around 8 kilometers per second. So now, if we just go and use now, there's a 1933 paper by Miller that sums up his work and goes in actually some of the drawings you saw there were from his paper. And if you just simply use Fresnel's, I still call him Fresnel, Fresnel's drag coefficient, and use that with the original 1887 Maxim-Morley data, then the speed that comes from just the drag alone, because remember, I'm saying relativity is 100% true, and there is an exact compensatory effect as things go through the ether. They are shortened. And so then the only thing that is left would be the drag of air on the light that we saw in the Fizeau experiment, and that would be occurring also in the Maxim-Morley experiment, but on a scale that has to do with the motion of the Earth through the ether. When we simply use Fresnel's calculation with the Maxim-Morley data, we get 378 kilometers per second. And you go, and I just grabbed the first thing that popped out of Google. I checked it also. And what you see is that our understanding from the cosmic microwave background is that the Earth moves at 368 kilometers per second. So now let's move on to the Sagnac effect. This is one that it just does not get more obvious that we are weirdly deluding ourselves about the idea of constancy. And that is, in the Sagnac effect, basically you just simply take a beam of light and run it 2 directions around a loop. And if the loop is moving, in other words, its frame is moving, then there is a difference in the speed of light, and then the light will not get to the same point at the same time, and you can measure this difference. Now, the argument for why that worked is it must be because of rotation, right? It must be rotation or acceleration, then there was lots of these things that persisted up into the common day. And there's no reason for them to have persisted, because there was no reason to explain it that way, because there was no reason to buy into the fourth dimension, because there was no evidence for it, because we were not using empirical science. Minkowski's space-time conjoinment is technically pseudoscience. So ring laser gyroscopes, IFOGs, and other uses of anisotropy are found in the GPS systems, in weapons guidance, and a part of the way in which I got reported to the Department of Homeland Security is because I was talking to Honeywell about their various systems when it comes to RLGs and IFOGs. But the synchronization of military jet telemetry, all of these things require knowledge of a particular bias that is occurring. And that bias has to do with the Earth's rotation. So now let's go to the Ruyong Wang's experiments, fiber optic conveyor experiments. I believe these were performed in the early aughts, or maybe it was the late 90s. I don't remember. But basically the way in which we are told that this does not violate constancy is that there is it's the rotational effect. So what he did is my favorite one is the bottom right, where because of the fact that he has taken the loops and made them go 2 different directions, the rotation should be exactly canceling out because it's rotating in 2 different directions. But what he also pointed out is that the length of what's it called? The fiber optics that it goes through, the length that the light has to travel is a crucial aspect of how much of an effect that you end up seeing in these. And so what he did is by lengthening the distance and only rotating it at the ends, what he saw is that there is a continual added effect by that straight line motion that is occurring in these experiments. And so what he showed definitively, and is now very widely accepted and understood, is that the Sagnac effect does not have to do with radians per second. And so it is not coupled with acceleration, because of course your radians per second is dependent upon the radius of whatever you're spinning around. So what this means is this. What let me check my thing here. Yes, I'll get to that. Okay. So what this means is that it is related to edge speed alone and not the curvature or anything like that. So once again, what we're seeing here is that it is an effect that shows an anisotropy to the way in which light speed is propagating. In the Hadfield-Keating experiment that you're aware of, with the atomic clocks on planes, there was an east-west bias in the data. In the round-the-world Sagnac experiment, where they basically took satellites and sent a signal between them, what they ended up having is an east-west bias in the data as well. And then also I wanted to mention the Faraday paradox, but we'll get to that some other time. So I wanted to come to this final, the round the galaxy Sagnac experiment, and by pointing out the fact that it's not based upon radians per second, but instead based upon edge speed. If an alien species had set up a Sagnac interferometer that goes all the way around the galaxy, and that ship that is measuring the light coming in from one side and the other, that happens to have made it all the way around the galaxy, what they're going to detect as they are traveling and what looks to us to be a perfectly straight line is an anisotropy in the propagation of light. So in other words, light will seem to be coming in faster in one direction than it is in the other, and it's dependent only upon their speed in an apparently straight line. So the need for this lecture is itself an absurdity. There's things like the Shapiro delay, where we have a change in time of propagation of light, that shows that light does not travel the same speed in all frames of reference at all times. That's special relativity. That was a not fully developed theory that Einstein himself specifically said does not appear anywhere in reality, is an idealization. The cosmic microwave background dipole, where there is greater heat in one direction than there is in the other, that shows us that we are moving. That shows that there is a light speed difference. There's frame dragging. There are the Sagnac devices, and what we've got is just thousands upon thousands upon thousands of experiments which have shown one-way anisotropy. In other words, that light is performing this compensatory illusion. But in the literature, you will find the most amazing cognitive acrobatics you could possibly imagine to defend a position that has no reason to exist. Because, going back to my previous lecture, there was a point in time where people got confused and believed that being for an ether theory is against relativity. And that is simply not true at all. However, it does falsify Minkowski spacetime. It does falsify the promotion of reality to a fourth dimension. And it does falsify relative simultaneity, where things are not simultaneous I'm not even going to get into that. So all of these things falsify any theory discarding a preferred frame, and they obviate any SR paradox appearance or solution while retaining relativity as a principle. But the thing is that also gives us a lot more to work with. When you understand how this version of relativity works, a lot of additional mechanics fall out of it, allowing Bohmian trajectories to make sense. There be physical mechanics behind pilot wave theory. There's a reason why things like, maybe we need to decouple time from space. There are a wide array of things that open up once you accept that there is this thread of hydrodynamics that can, at every point through the history of physics, which I've been pointing out a little bit at a time, and I don't have enough time to do it all at once, and so you'll have to bear with me that I'm doing this, one lecture at a time. They're all throughout the history of physics. We have an alternative path that we could take, and that many people are taking, but they're not being listened to, and there is a lack of unity in the understanding of what all the various principles are and how they must work together as a singular system which has no self-conflict. And that only works with understanding these specific things that I've tried to bring out to you. And hopefully this is a short enough lecture that I've tried to hit a lot of the high points, but that's basically it for me. And I'm going to have to save everything else for yet another lecture some other time.
Awesome. Shiva, thank you so much, man. Thank you so much. And when you said another lecture, another time, I'm rubbing my hands. Dude, I will beg and grovel. I have no shame. So let me add everybody to the stage here. Let me see. And Mark, I think he's away from his computer, but that's cool. Guys, please put your hands together with enormous applause for Shiva Meucci. Thank you, Shiva. Thank you so much. One of the things that excites me about APEC is bringing together people with different focus areas and different backgrounds, right? And like Drew was mentioning in chat, he's like, well, I don't understand this part of it necessarily. And I'm like, man, you guys all like make me feel lost, but like in a good way, right? Because it's like so much different focus and specialization, and then there's that cross-pollination that happens, and I think that's like truly magic. So I mean, all of you guys, thank you so much for presenting today. You are driving this community forward, and it's absolutely wonderful. Well, do you guys have any questions for Shiva?
I hope so.
I have a question, Shiva.
All right.
It's going to just be very naive. I mean, I teach physics. I'm an instructor. So in light of all that you've been explaining, would that mean that I would teach special relativity differently than I already teach it now?
Yes, it would be. Here's the thing. What I'm pushing for here is a realignment of all of our theory along hydrodynamic lines. In other words, using hydrodynamics to give us, like, for instance, one of the things that should pop out of Poincaré-Lorentz ether theory, that relativistic ether, is that you'll have this shadow calculation that's not there in Minkowski space. And that is that some observers will have time contraction and length dilation. In other words, those things will not be that are not present. That is additional information that's available. Then there is with it being a physical or a semi-physical substance, there are ways in which that I've got other lectures there, like my previous lecture, going into what will you end up coming out with. You have to use a Kosterek continuum for this to actually be functional, and what that then leads to when you've got a superfluid medium, and how that can give us additional dynamics for understanding what it is when you're doing flux pinning in superconductors, what's occurring, and how that may be relevant to unifying gravity with electromagnetism, and there's a wide variety of ways in which this gives us additional information. But the point here is not to replace. Well, the point is to replace our current teaching with something that gives us something else underneath it. In other words, what we've got is a way in which we teach relativity that eliminates one huge historical aspect of it, and that there are two interpretations. We teach that there are different interpretations of quantum physics. We do not teach that there are two interpretations of relativity, and losing that other interpretation is a huge loss.
Oh, that makes a lot of sense. So the mathematics would stay the same, but the interpretation would be introduced differently. I mean, the analogy with quantum mechanics, I was thinking about that even as you came to say it. I wondered if that was exactly analogous to what's happening here.
Yes, and it gives you all of these other ways in which you can explore relativity. In other words, like I said, time contraction and length dilation. There's the distance that you would, in other words, some of the cosmological cosmological constant problems different, but some of the crises in cosmology may be able to be explained through the fact that when we're using relativity without this additional information, we may be improperly judging. That's kind of hard to explain, but there are ways in which that changes distances because there's an illusory effect, and because when it's a compensatory illusion, there are a wide variety of things that you have to understand are illusory or virtual, is what sometimes we would call them, but they're really they're real to you. In other words, they have effects. They're actual particles that have effects, right? And there are these things that we need to be able to separate that virtual. Align the way in which we apply our method.
You know what, Shiva? Actually, we're losing your signal, but we're at the top of the hour, so the timing is. If there was any point for it to cut out, this would be the time. I'll give it just a sec. Okay. Well, again, guys, let's do this. So we are at the top of the hour, and Jarod has an enormous presentation. So let me do this, guys. Let's put our hands together one more time for Shiva Meucci. And it's on my list. Actually, I need to fly to Vegas at some point and get film with Shiva. And actually, Nader, I was thinking I need to come down to Merced too. And then I guess Ray is back in San Francisco, so I may have more travel ahead of me. But you guys you're my celebrities, so
that would be awesome. Come out
Hey,
here.
Tim.
We got a place for you.
Yeah. Drew, go for it.
Tim, we really, really need to get some of these smart people to just crank out maybe a half a page cliff notes, in simple little stick figures and stuff, so that the rest of us can enjoy the excitement of like Jarod and Mark and yourself. Because I gotta tell you, man, we're lost. We are lost. We need stick figures.
But it's lost. It's lost in a good way. I mean, it's new information and it's different perspectives. And again, that cross pollination is like amazing. And like for me, in a weird way, it kind of reminds me of like I was thinking of San Francisco. So San Francisco in the 60s, you had like artists and you had parapsychology and you had physicists and then you had all of these other cultures, and they were all like in this tiny little area. And so that led to all of these amazing outcomes, right? For all of these different disciplines, but it also influenced stuff. Like that's where the computer revolution started, right? So I mean, like I don't think you can always anticipate, it just comes out of nowhere. It's like, we're talking about the aether, right? It's like, it's in the aether. It's this diversity of knowledge and perspectives and expertise. And maybe it doesn't always fit, but then when it does, you can get something absolutely brilliant, So.
I agree. It's all awesome, but I need cliff notes. I need Dick and Jane stick figures, man, because
I am right there with you.
In.
I'm right. I am right there with you. But
yeah,
well, Shiva, let me thank you again. We have one more. So Gerald is not able to present today. He's having some technical issues with his computer. But Jarod has the mother of all UFO crash recovery presentations. He's been updating me on this all week long, and I'm already terrified. He hasn't even started yet. So let me take you guys out really quick, and then I'm going to go over to Jarod. Okay. And so Jarod, let me see. I uploaded, so we have a video file. Maybe I'll play that on the screen, or I'll try and upload that when you're ready. If I upload it now, it will, I believe it will start to, you know what? Let me upload that now, just in case.
Okay. It's best to view the video at about the halfway mark for the whole thing, though.
Okay. Yeah. See, it'll start to, okay. There. So, and then I have this also. Do you want to share your screen, or do you want to use this? If you use this, you'll have to tell me to go back or forward in it.
Yeah, if you give me one moment, I will do it from my screen.
Okay. Yeah, perfect. Yeah, and while you're getting that, so I should let the audience know, again, we were at Falcon Space Labs. You were helping him do RF tuning on the dynamic nuclear polarization. I was taking thousands of photos of both of you guys doing it as part of my promote the APEC team. And the arts parts thing just kind of showed up. And so we spent a couple of days there just going through it and doing, there we go. That one's yours. So this kind of came out of that. So we had the opportunity to examine a real verified chain of custody piece of arts parts up close. It was a small piece, but the real deal nonetheless. I don't know. I don't think anyone knows if it's actually extraterrestrial, but we kind of got bit by the bug, I guess. And then I was pestering you to do this presentation. So let me, again, sir, thank you very much. And I'm here in the background. Just let me know.
All right. Well, everybody buckle up. I'm going to talk fast because I got a lot to get through, but hopefully I'll leave enough time at the end for plenty of questions. So like Tim was saying, we were over at Mark's lab at Falcon Space. Tim had just gone with Mark down to visit Drew, and they'd driven back. I'd gone over there to do some RF stuff on Mark's equipment, and Providence smiled upon us. So we ended up getting the sample the day before I was supposed to leave. So I ended up kicking my flight back a couple of days so we could do some extra time spent with this sample. So let me next here. Oops, there we go. All right. So I'm just going to give you a quick brief outline of what we're going to go through. First, you got to know the history about this thing. The history starts around May to July of 1947. There was a bunch of UFO stuff going on in the U.S. around that time. And then we're going to get to the source for this, the person who supposedly grabbed this off of a crash in July of 1947, who eventually passed it off to his grandson in 1974. And then the source, the grandson, eventually passed it off to Art Bell and Linda Moulton Howe in 1996. And then Linda ended up selling a piece over to the Stars Academy with Tom DeLonge and Hal Putoff back in 2019. I'm going to go through all of the previous analyses that have been performed on these pieces. There's a lot of them. Linda Moulton Howe has done the majority of the informing the public on this piece for good reason. I mean, she's the owner of the pieces, and she's the one who's been paying out of pocket for all of the science work being done on them. I'm going to correlate it to some other UFO crash debris. We're going to go through some of the debunking of this, as well as some potential validation of this. Then finally, about the halfway mark, we get to the good stuff, which is the picture you see in front of you, our observations, what we saw over at Falcon Space when we were inspecting the sample. After that, what we still want to do to this thing, because this is all late breaking. This was like a week ago that we ended up seeing this, and then I crammed all of this slideshow and presentation in this week to be able to present it to you guys today. So it's a lot in a little bit of time. Then I'm going to start going into some of what other people have speculated the stuff might have been used for. And then we'll go into my personal speculations, which are a little more on the extreme side because I like to take it to the nth degree pretty quick. All right, so May of 1947. I'm not sure if you can all see my cursor, but we got two black dots on this map on the left-hand side. In May of 1947, that second inmost left dot is Horse Springs, New Mexico. That is where there was a UFO crash in May of 1947, sometime. I don't know the exact day. And then the very last day of May of 1947, there was another crash over in Socorro, right smack dab in the middle of this map. Then we get to mid to late June. That's when Kenneth Arnold over near Mount Rainier sees the 9, quote, wedge-shaped discs. Then over at Roswell, that apparently was not a single event. That was over the course of a couple of days. They had 3 different crashes. With this crash in the very center dot, we got this black rectangle called White Sands Missile Range. That's the spot where we think this sample came from. But there was also a crash up in Corona and a crash over in Roswell, all within those couple of days there. The grandfather is the one who said that it was recovered somewhere west of the Sierra Blanca mountain range, which is how we are able to establish that it was the White Sands crash. All right, so starting with the history of this thing. So you got an Army Air Sergeant. This is just prior to the Air Force being created. You got an Army Air Sergeant. He was first on scene at the White Sands crash. He gets there. The thing is still glowing for 3 hours after it crashes. So I'm going to assume that he didn't just reach up on a glowing thing. But at some point during this crash recovery process, he reaches towards the center underside of this disc and peels off a handful or two of the hull and shoves it in his pocket when nobody's looking. He holds on to them until 1974. And at that point, he tells his grandson, as well as a couple of other people, all in one sitting, like, hey, this is what went down. I wrote all of my stuff down in a journal. All of these pieces are, stored in tissue paper in a shoebox in a closet. And I'm getting ready to die. So he dies that same year. The grandson inherits the samples, and including the journal. The grandson, according to the letters that he sent to Art Bell and Linda Moulton Howe, he gave a piece of the debris to a friend of his who was air crew on a C-130. That C-130 got struck by lightning and crashed in November of 1978. I got links here if you want to follow up on these. I'll share the link to the whole presentation at the end. Anyways, so that scared the crap out of this guy, so he doesn't tell anybody. But this friend was the only person who he had like confided in about this whole thing. And the friend, who happened to be carrying one of these samples, dies in a suspicious lightning-induced plane crash. He was scared good. So he doesn't say anything for 18 years. And then in 1996, in April, he sends Art Bell a letter. In that letter, he says, hey, I got some good stuff. I'm going to send you some good stuff. A little bit later, he sends him a second letter with a package full of what you'll see on the next page, which is a bunch of aluminum samples. The third letter / package is the one that actually contained, quote, Art's parts, these layered materials. And there was 6 samples in that package. I highly recommend that anybody that's really interested in this, follow that link down there at the bottom. It says link for letters. That'll take you to the Earth Files, Linda Moulton Howe's Earth Files page, where she's got scanned copies of all of these 5 letters that the dude sent. There's some really interesting stuff in there. As a teaser, one of the things in there is the guy says that his grandpa, who is that Army Air Sergeant, the grandpa spent like weeks with the one surviving alien from the crash, and apparently the alien said, yeah, sometime around 2025, we're all going to show up and make ourselves known. That's just a good teaser for why y'all should go read these letters. Not that I would put a whole lot of credit in that. I'd put a big old bag of salt with it, but I'm a sucker for whenever you got dates for the aliens showing up. Anyways, so here's the picture on the lower right-hand side of what was in the first package. We got these aluminum little tiny disc punch-outs, as well as square punch-outs. We got one larger aluminum disc, and then we got these weird fin things, these like radiator fin things over here on the lower right-hand side. A lot of people have tried to figure out what's the deal with those radiator fins. Those look a little suspicious. One thing that somebody mentioned was maybe it's being used as photocathodes, you know, a way that you can like get a whole bunch more electron flow going off the edges of these things. It's possible, but unfortunately, Mick West, who I'm not going to say anything, but Mick West, he actually did a pretty decent job on this, I guess. In between these fins here, you can see these grooves that look kind of bent. And that right there, that is a telltale sign that these things were bent at some point. And it appears as though these things came off a radiator of some kind. Mick West claims that it came off of a radiator from some vehicle from 1925. I couldn't find which vehicle exactly it was, but he sounds pretty confident, for whatever that's worth, that this came off a radiator. I can't say one way or another. I hate to say it, but I kind of like the radiator explanation for this, but it still doesn't necessarily preclude it from doing cool stuff. Just because it looks like a radiator thing, it might not have been used as a radiator, it might have been used as a photocathode, or maybe it was being used as a radiator, but still on a craft. I feel like I'm grasping at straws here, but let's just, for the moment, continue to give the benefit of the doubt to this sample until a little bit later. So here's the actual Art's parts. We got these layered samples. Here's the shiny side from the top and the dark side from the bottom. That shiny side on the top is almost pure magnesium. The dark side on the bottom is almost pure bismuth. And then you got this layering throughout where it alternates between bismuth and a magnesium zinc alloy with very small amounts of zinc. It's like 2.4% zinc in all of these bismuth / magnesium zinc layers. You can see over here the sizes of them. The bismuth is really thin. The magnesium zinc is really large. So Linda Moulton Howe has hired over 100 different professionals, scientists and material science, like manufacturing guys, just everybody. She's throwing the kitchen sink at this thing, trying to get as much data about it as she can. So here's from her book, Glimpses of Other Realities, Volume 2, where she shares some of the earliest scanning electron microscope, SEM images, and it's inverted. So these white lines are actually the bismuth, the dark bismuth. And then in between there, you got the magnesium zinc alloys, right? Hal Puthoff has been working on this sample for quite a while, long before the Stars Academy. And he's pretty convinced that these things are waveguides. And the reason why is because he observes how, as you look at the waviness of these lines, it appears as though the waviness of the lines is correlated between these different layers, right? As it goes down here, it goes down here, it goes down here, it goes down here, right? He's seeing some kind of thing like that, and it doesn't quite seem like dislocations. It seems intentional, according to Puthoff. They also did some X-ray diffraction stuff. They've done a fair bit of isotopic ratio stuff. The XRD and the isotopic kind of leave something to be desired. They were doing it back in the 90s, and they've done more since then. Like I said, it's like 100 different professionals have analyzed it. We got a chance to see some more of those analyses that we can't quite share, but like it's not a whole lot of new stuff in there. So here's the isotopic stuff, and this is a bit saddening. So you got these solid lines here. The solid lines are from the control sample. And what we're looking at is we're looking at the amount of non-terrestrial magnesium to terrestrial magnesium, because the isotope changes, the number of subatomic parts, it changes whether it comes from off Earth or on Earth. So the control sample, you can see just how large these error bars are. And we only have 3 data points for the control sample. And then for the test sample, we only have 2 data points. And over here, this is percentage, so 13.9%, 14%, 14.1%. Well, like the actual range, when you really start getting into the numbers here, anywhere from 13.5 to 14.7%, like that's pretty prosaic, pretty earthbound, right? It'd have to be like 20%, 25%. That's where you really start raising your eyebrows. So if this thing did come from off Earth, they chose to use terrestrial magnesium. It's weird. This does not necessarily support that it came from outer space, but rather terrestrial based. Then over here, we got some more spectroscopic analysis here. Here, they're showing the elements that were involved. Very little amounts of zinc, a lot of amounts of magnesium. And then that was for the shiny side. For the dark side over here, you got a lot of magnesium and some bismuth as well. Bismuth shows up down here as well. From some of the documents I read, it seems like if you did want to get cool physicsy, propulsion-y stuff, you'd probably want to be below 40% bismuth. And I couldn't find any reference that says just what percentage the bismuth to magnesium was in these. So somebody can find that. That'd be pretty cool. Something to observe is that the Betterton-Kroll process is often given as like how these layers were created. The Betterton-Kroll process is how you take molten lead, you pour in a bunch of other stuff, especially bismuth, and that kind of collects all the stuff in a dross, and you scrape that dross off, and that's how you get these layers, is from this lead refinement process. Yes and no. It definitely seems like it's some kind of similar process that was creating this for a lot of reasons I'll get into. But one little weird thing that I haven't been able to quite get a good answer yet is if indeed it was a lead refinement process, you would think we'd find lead, and especially lead oxide. There was no lead oxide found in one of the studies that I can't share. Lead was found, but it was found at like extremely small. We're talking like small parts per millions, like below the threshold that the thing could reasonably detect, like at the margin of error. So like, where's the lead? Here's another cool test they did. They took 90 milligram sample of this thing. They dropped it in just some distilled water, and they watched what happens. Well, they had already observed that the magnesium in this was like ionized magnesium. It was magnesium ions, magnesium 2+, and that it was at, quote, 60 times the concentration of normal. I have no idea what that means. Maybe it was really oxidized. I mean, who knows? Whatever it is that Linda is referring to when she says that the magnesium was at 60 times the concentration of normal magnesium ions, that it seems like it did some weird stuff when you dropped it in water. So drop this thing in water. They let it sit there for 40 days. They take the cellophane out, and this is in one of the videos that I'll link to that Linda shares. They take the little cellophane wrapper off of the beaker that they had this thing in, and they light a lighter, and poof, and they're getting hydrogen off of this thing. All these little bubbles, that's all this hydrogen. and it's leaving these little nucleation sites. It's kind of weird. So I follow up on that with Wikipedia of all places. Now, this sample did not have aluminum in it, so take this with a grain of salt. But magnesium and zinc, you throw them in water, if there's an oxide layer, it's going to really slowly react to the water. So not really sure what this tells us, but somebody that's smarter at material science than me can probably figure something useful out from that. It's an interesting test. All right, so 2019 rolls around and Linda starts getting some flack. So what happened was Hal Puthoff, who'd been working on this sample for like at least a decade or more, I guess, like prior to this, like he'd been a big part of this for a long time. He joins To the Stars Academy. He's gung-ho that this is a terahertz waveguide thing with those small bismuth layers, and he really wants to test with the terahertz. Problem is, with this specific frequency of terahertz radiation, not easy to come by. There are very few places that actually can make that specific wavelength. So he ends up finding out that the Army has these terahertz sources. So respectfully, he comes to Linda and he's like, hey, look, I finally can test my hypothesis, but I know how you feel about giving UFO parts to the military. It means that you're probably not going to get the sample back. It's 50-50 whether or not they'll even tell you the results. What do you want to do here? I mean, we have to test this angle. And so Linda said, let me get back to you. So she goes and thinks about it. She comes back next day. She's like, look, I tell you what, I got 2 samples left. I will give you one of the 2 samples for the cost that I have incurred thus far to do all of this testing that I've done. She's hired a lot of people. She's done a lot of testing. She's built up quite the bill on this pieces of metal that she's holding on to. So for 35 grand, 2019, she sells it to Puthoff, who then put it in with the Army terahertz lasers. And a bunch of people are saying, well, why haven't we heard anything from this? Well, it's the Army. It's To the Stars. I don't know. I don't know why we haven't heard anything, but it's not hard to guess. Either they found something or they didn't find something. Either way, we're not going to probably hear about it. All right. Now we're getting into some better stuff. So there's similar cases where pieces were recovered that had somewhat similar characteristics of this sample. So some of the ufologists in the group might recognize that back in July and August of 1952, there was 2 incidents where the White House was dive bombed for UFOs like crazy. Like it was 60 different UFOs were like dive bombing the White House. It made the news. The 4-star general had to come out and like talk to the press about it. It was a big deal. Well, in one of those 2 incidents, they scrambled an interceptor aircraft. The aircraft chases one of these 2-foot diameter discs, 2 feet in diameter, and he shoots at the thing, and he manages to knock off a piece of this thing, glowing piece, about a 1-pound piece, a chunk of this 2-foot diameter disc. He knocks off, so he immediately radios in, says, hey, here's my location, go retrieve the sample. So they go to retrieve the sample. It's glowing for 1 hour after it had hit the ground. Unlike the 1947 saucer samples that we're looking at that supposedly glowed for 3 hours from a much larger craft. Here's where it gets interesting. Apparently, Sarbacher, who is someone that Jeremy Reese has mentioned a time or two, Sarbacher was like this insider DoD scientist guy. Apparently, there's a MUFON case where it's described that he was the one who analyzed this. Supposedly, this sample from the 1952 White House flap had a matrix of magnesium orthosilicate, and that matrix had thousands of, the MUFON case says 10 micron spheres, so I'm going to split different. I'm going to say 10 to 15 micron spheres scattered through it. The MUFON case says that they were spheres of bismuth. I haven't been able to follow up anywhere where it says that Sarbacher said that it was bismuth, other than that one specific MUFON case that somebody wrote up in 2015, and the only reference that they gave to it was this book, Flying Saucers, Serious Business. So if anybody else can find where Sarbacher was actually the guy who analyzed this, that would be super helpful. Moving on. All right. So here's a picture of the sample that we had. We're talking about these little tiny micron spheres in a matrix alignment. I'm going to get to it here pretty soon, where these little colored dots, they seem like they have a certain ordering to them that might suggest that they are in some kind of matrix, as well as their sizes. But let's keep going with other similar samples. So Ubatuba, Brazil. Now, I thought I saw some source that said that the Ubatuba thing was a crash that occurred in the 30s that wasn't until 1957 when the samples from that crash actually started getting analyzed. either way, we'll just stick with 1957. So Ubatuba, it was a craft that like exploded over the water next to a beach, and some fisherman saw some pieces fly onto the beach that didn't hit the water. He collected them. He hands them off to some scientist, academic guy. The academic guy ends up channeling them up the food chain to get tested. There's actually been a couple of really good white papers written on the Ubatuba stuff. That one, though, was like almost pure magnesium. And its magnesium ratios seemed, once again, fairly terrestrial. So this graph in the lower right-hand side, this green dot here, that's nominal values for magnesium isotopes. The letter C down here in the corner, this is the Ubatuba sample test. The rest of these are all like Dow chemical and, you know, other materials like control samples. So the test sample is this C right down here. So if anything, it's more terrestrial than the stuff that is being used by as the control samples. So that's kind of weird. Now, another one thing to mention about this, you can follow up with these links for the ResearchGate paper on it. But the Condon Committee back in the 60s, which a fair number of people recognize the Condon Committee was kind of like Arrow. They're not necessarily perfectly genuine in their efforts. The person in this paper is suggesting that there might have been a major error in the Condon experiment that was establishing the magnesium ratios of these, that they misrepresented the mass of the sample. So instead of being 14.3%, which is way up here, it could have actually been as high as 23.1%. So the jury is still out. There's still a hope that the Ubatuba could actually have been like extraterrestrial, because that's enough to raise an eyebrow. But I don't know if, I think Gary Nolan might have tested the Ubatuba. Don't quote me on that. Anyways, there were 37 trace elements detected in this. And these trace elements, these are the things that really convinced me that we're looking at some kind of refining process. All right, first I'm going to compare side by side, though, the Ubatuba on the left and the ARTS parts on the right. And you can look at these percentages that we're looking at. ARTS parts is like 14 to 14.1. This one down here from the Ubatuba is like 13.7, 13.75. Not up in the 20s, unless we say the Condon was mistaken, which they very well might have been. Oh, there we go. All right, trace elements. So when you look through the Betterton-Kroll process, there's a lot of different recipes for it. One of the recipes says you can use strontium to do the process. One of the weird things, though, is that I want to say the isotope for strontium they use is this one, strontium-88, which has, you know, really high abundance level in the crust, right? But down here, we see that strontium-84 has a very low abundance level, and that in this sample, the amount of strontium-84 was 32% above what it is in the crust. Well, that's kind of weird. That's not just Betterton-Kroll. That's leaving room for the weird. Then over here, now we're going back to less weird, more Betterton-Kroll. So in Betterton-Kroll, you use calcium, you use strontium, you use barium, and of course, you'll find lead in it. Well, for these first three, calcium, strontium, barium, there's a fairly decent high parts per million of those three, which that's what you would expect from a refinement process to find those. But once again, the lead is really pure. There's very little lead. We got 7 to 15 parts per million for what's going on here. I don't know what's going on there. I'm gonna say that it's very possible that I don't understand the Betterton-Kroll process well enough to speak intelligently on it. Maybe the Betterton-Kroll, you are able to get super pure lead-free and lead oxide-free stuff. But one of the reports on ARTS parts that I read said that the lack of lead oxide was one of the weirdnesses of it. All right, so getting to our sample. Now we're getting into the goodies. So here's a picture of it on a penny. A lot of people have been asking, what's this white stuff? That white stuff is the glue from the previous owner who was putting it on the tip of like a rod to do testing on it. So yeah, it's not like quartz crystal or nothing else, just glue. We don't want to try to peel it off because it's so small. We'll probably snap the thing in half if we try to do that. And you can see it's very, very small. How we got this, the worst answer in all of ufology. We can't tell you. So the donor for this thing has requested not to be revealed, and we respect that, and we respect this person. However, this person was able to give chain of custody for the thing, which is nice. So we're able to have multiple layers of validation that this thing is indeed what is claimed. Also, additional scientific reports for arts parts was provided. Once again, non-disclosable. And for those who are saying that, how much did you pay? We didn't pay for the sample. Sample was freely given. All right, so here's some interesting stuff. So it was Tim, Mark, and myself who did the majority of the inspection on this thing. Tim took a look at this thing. Within a few minutes, he said, hey, it looks like it's got hexagons on it. And boy, did that pique my interest. So I start looking for the 120-degree angles that are like obviously apparent in hexagons, and I'm just finding them all over the place. They're all over the place on the shiny side here. And I got these green lines here that you may or may not be able to see that kind of indicate some of these 120-degree angles all over the place. You flip it over, so instead of the bubbled side, it's the like concave side here, the bismuth side, and you can kind of see this purple is because we had UV testing. This was a UV light, and I'm just using this picture because it makes the shadows easier to see. You can kind of see we got these offset hexagonal cells here, right? And some of these hexagonal cells seem like they're somewhat different sizes. Yeah, also there's another image we can't share of the larger sample that seems like it has a big old hexagon like cut on the thing. Yeah, so hexagons are a thing. The thing that I spent the majority of my 16 hours worth of looking at this thing was these little colored spheres that crop up all over the place. And I have a video that I'm going to play for you here in just a second after I show you a couple more pictures. So Mark and Tim have released some really high-res photos, and even better photos are coming. Remember, this is all super late breaking. This is like within the last week. So be assured we're going to have a lot better quality stuff coming out here in the very near-term future as we get better and better equipment to be able to analyze this and upload, 8K photos and like 20,000x microscope photos, and all the goody stuff is coming. So for those who might be a little impatient, tough luck. Just wait a little bit. We're going to have a lot better stuff as we have more time to do stuff with this sample. Anyways, I got some of these orange arrows pointing at some of these colored dots. I got some more pictures. I'm going to show you these colored dots. I took this blurry grainy one just because it kind of blooms some of these colors that you can see. I got another one here. I drew these little red lines here so you can kind of see some of these dots. Once again, I apologize that these are so blurry. I got some less blurry ones coming up. Here's some different lighting. In the very near field here, you can kind of see some of these colors that I'm observing. You got kind of like this blue and this copper green, this yellow and this like pinkish colors, some white colors. Got all these different colors all over the place. And what's really cool is right here, you kind of see like this circle of colors with a single color in the center. Another little one over there. So and then you got other ones where the colors are all running along a ridge line. I don't know. I think the colors are weird. I think they might indicate either something extremely prosaic or something extraordinarily revolutionary. It's hard to say yet until we do X-ray diffraction. Here's a zoomed in of that same one so that you can kind of see these colors again. All right, so here's the video. I'm going to try to play this video. It's like 4 minutes long. I'm going to play it a little bit fast-forwarded, hopefully, if it will let me. Oh, no, it's not letting me. Uno momento, and I will get this thing playing. Okay, well, maybe I'll play the video at the end after I'm done with it. Basically, this video is a 4-minute video, which I have links in the presentation I'm going to share anyways. So you can go back and watch
Jared,
it
let me you know what? Here, let me add it to stage. Let me remove yours, and I will add this one. There we go.
There we go. So as we're watching this thing, it's a 4-minute long video, so a little bit long-winded here, but I just want you guys to like try to see some of the stuff that I was seeing. Look for all those colored little dots. You're probably going to want to go back through and watch this again a couple of times, and do some frame by frame to be able to see where these dots show up and where they disappear. They become very apparent, especially when the light turns right onto the very edge, and so you get the best shadows. Warning, this is going to flash the screen bright white here a couple of times, so epilepsy warning. Just the nature of doing business with a flashlight. on a 2 millimeter sized thing. Slightly zoomed in. Here's that bright turquoise one in the largest hexagonal divot. Some also bright pink ones. There's some bright yellow ones. Some of them are much brighter than others. I don't know what caused them bright or not bright. There was also some interesting things where as I removed the light source altogether for just a second, they remain lit. So like that's kind of weird. We did some green laser tests as well. And from some of the green laser tests, like the green laser, as it shines underneath the thing, like it's somewhat translucent, like you can see the green laser peeking through the sample from beneath. That was kind of interesting. So some of these bismuth colored balls, some folks have said, well, that just happens when bismuth gets hot. It can bead up like that. That's a pretty decent prosaic explanation. And I would give it a lot more credit if we had like bunches of the same colors, but instead it seems like you don't see a whole lot of the same colors next to each other. And you see some of these circles and lines of these colors. And then it's not in this video, but when I looked at the thing edge on, you could see the colors kind of go on diagonally. Now you could see the iridescent bismuth, you know, gasoline on water or soap bubble type thing. Like you could see that on the edge on as well. But in addition to that, you could follow a line of these beads of colors and you could watch it go at an angle across the thing through the layers. Yeah, these beads are super interesting to me. Once again, they might be totally prosaic. We don't know yet. Not until we do the X-ray diffraction, which hopefully will be happening somewhat soon. I do want to reiterate that this is on the underside layer of the inner layer of the craft. So the outer layer of the craft was aluminum with some atomically placed iridium, supposedly. And then the inner layer was this layered magnesium, zinc, bismuth layer. So, yeah, I don't know. There might be melt. You might be able to see a little bit of melt on this thing, on the outermost edges of this thing. But yeah. All right, Tim, I think the video is done. If you can go back.
Yeah, sorry, I put the slideshow back up, but it looks like it went back to the first slide. Can you tell me which one you were on, or did you run through them all?
Oh, let me stop sharing and I'll share again. Maybe that'll work.
Oh, maybe you took it down. Okay.
Here we go. Yeah, I took it down, put it back up.
Nah, no worries, man. Okay.
All right, there we go.
So this is your video. Okay.
Yep. So now, there we go.
Oh, perfect. Thank you, sir.
All right. So we have some other testing we did. We didn't just shine a light at it for 16 hours. I put it on the scale. I put some calipers on it. The sample that we got weighs about 7 milligrams, give or take a half a milligram. There's a little bit of airflow on the super sensitive scale, so call it 7 milligrams. The calipers, the long end here is about 4 millimeters. The shorter end here at the widest mark is about 2.5 millimeters. We did some magnetic tests on it. I ran a magnet around this thing to see if it would move because, hey, bismuth, diamagnetic, maybe it'll respond somehow. It didn't respond to the magnet. I put a Geiger counter on the thing, didn't get any radiation. Put a trifield next to the thing. I didn't get anything from the trifield. Not to say that it wasn't producing EM, but just not EM in the range that trifield was able to measure. And we did multiple wavelengths of light. We had UV light, we had green laser, and we had a LED flashlight. And LED flashlights have red, green, blue LEDs in them. So, multiple wavelengths going on. So here's some more non-destructive testing that we want to do to it. We don't really want to do any destructive testing on it because it's so small and we can't really separate enough from the sample to do decent destructive tests on it. But the very first one, the highest priority here, X-ray diffraction. Now, we have better access to a scanning electron microscope, so that might happen first. But the one that I keep screaming from the rooftops we need to do is the X-ray diffraction, because that'll show us if indeed those bismuth-colored spheres, or whatever shape they are, if indeed they have a regular lattice structure, or even an aperiodic lattice structure like quasicrystals. Another thing that's been suggested is something called radon transform. Don't ask me what that is because I don't know, but another one of the scientists from the group said, hey, we should do this. It's non-destructive. You can tell us some stuff. So we're possibly going to do that. The main goal with this sample, though, is Mark is going to be testing the sample in his Alzaphon experiment, which is dynamic nuclear polarization, where you put a special sample into a RF cavity that has a specific magnetic gradient applied to it, and at certain magnetic gradients, at certain RF pulses, the thing will lose weight. It's a super awesome idea for anti-gravity. All right, now I got some notes. So despite the fact that there's very low lead in it, some kind of better control process seems extremely likely because there's other trace elements. And in Art's Parts, it's got some calcium in it as well. That's screaming some kind of better control something. Oh, whoops. Sorry about that. There we go. So I'm not going to say that aliens are off the table. Maybe the aliens are using better control, but that really feels like you're reaching at that point. It was also totally possible for the methods that were available at the time for this to have been made terrestrially. That's something that a lot of folks don't realize, myself included, that material science was actually pretty impressive back in the 40s and 30s and 20s. So these colored microspheres, like I keep saying, they could be totally prosaic. They could just be an artifact of heating. They could be a whole bunch of things. But the irregularity of the colors combined with the arrangements and circles and lines and stuff, I don't know, it's piquing my interest. I'm keeping my fingers crossed, my hopes high and my expectations low that we'll find some quasi-crystal stuff going on with that, because that would be super cool and would be total evidence that this thing was not made by people, because quasi-crystals weren't even a thing until the 80s, and weren't even really making them until much later after that. Also, as an aside, there's been some alien implants that have been analyzed with similar scrutiny that have also shown some similarities to this with chemical makeup, isotopic makeup, and nanostructures that are present. So for all that's worth. Something that's interesting about that is you couldn't find anything where anyone who done any tests on Art's Parts ever mentioned anything about hexagonal structuring. And on the larger samples, you don't really see that hexagonal structuring much. So maybe that's why. It could just be an artifact. Maybe that hexagonal structuring is like nothing to do with anything, and it just so happens the piece we have is small enough that like you see what you want to see, and the 6 or 7 little hexagon things we see on there is totally arbitrary. Who knows? But if not, that could be a new discovery. It's important to note that magnesium and zinc, each of those individually have hexagonal crystal structures, but when you combine the two, you get icosahedral structure. By the way, in case this thing does have quasi-crystal nature to it, that magnesium zinc would indicate icosahedral symmetries, which are important for quasi-crystals, and I'll go into that a little bit later, but just keep that in your back pocket. All right, let's talk about some thermoelectric generation. This is how you convert heat into electricity. Well, bismuth magnesium and bismuth zinc, there's a lot of research out there on how you can use those to create electricity from heat. Those radiator fins that we saw at the beginning, maybe whoever made this thing was using heat somehow to create electricity, but they needed a way to create a thermal gradient, so thus the fins. The iridium angle that Linda mentions, that came, she was at some conference talking about the thing, and after the conference, some guy comes up to her and says, hey, I'm from S4, here's my credentials. She was convinced of his credentials. He claimed to work on a 3-foot by 6-foot section of the hull of this same craft. And he said what was special about it was that the aluminum outer hull had atomically placed iridium in it. And it was the combination of those two things working together it actually made the thing able to lift. For radioactive thermal generators, like those used in satellites, they also use some heat fins, and they also have iridium present in them. So maybe there's some kind of there. So the 1947 UFO, that glowed for 3 hours after it crashed. The White House 1952 one glowed for 1 hour. Well, in the mid-50s, the Norwegian Air Force observed a bunch of UFOs coming and landing and taking off on the ice sheets. And like this Air Force general said, yeah, it seems like the intensity or the luminosity of the light coming off these things is directly related to how fast they're taking off or how fast they're decelerating. So that's interesting. I think that might indicate that there may be some relationship to the amount of light coming off of these things to lift, but not necessarily, solely that's what's responsible for it, because, these things kept glowing for a couple hours, but they weren't lifting. So, who knows? So there could be thermoelectric properties of the bismuth. Since we're talking about light, there might be thermoluminescence at play. The magnesium ions and the zinc seems like there might be electrical at play, because those are kind of used in some battery applications together. So Canada was their inside group was inspecting an electrogravitic model, but after the 1952 flap, when they got that sample, they stopped looking at the electrogravitic and they started looking at the gravitomagnetic. They abandoned the charge for the magnetic side of things. So that's an interesting side note. Colonel Corso, who wrote the book Day After Roswell, right? He said that the entire vehicle functioned like a giant capacitor, somewhat similar to what the alien reproduction vehicle, the ARV from McCandlish, kind of like that angle. Anyways, he says the entire vehicle functioned like a giant capacitor. The whole craft stored a bunch of energy, and somehow it used that energy to propagate a magnetic wave that let the thing defy gravity. And yeah, some crazy stuff going on there. All right, here's speculation what other people have been saying about this. They've been saying that since bismuth is so diamagnetic, that it might have been used as magnetic shielding. Actually, that's what one of the original source, the grandfather who originally got the sample, that's what he said in his diary, was that he had spent 6 weeks with the recovered alien and the recovered craft after the fact. This is one of the things that he relayed, was that bismuth was being used to repel external magnetic fields. It's important to note that diamagnetism, negative susceptibility, bismuth has the highest negative susceptibility, meaning it expels the most magnetic fields short of going into superconducting territory. Sarbacher, once again, he claimed that it had bismuth nanospheres of 10 microns. Here's that MUFON case for you. If you have a MUFON, $5 a month registration, you can go look up this case number and see what somebody wrote about that. Sarbacher was talking to Stanton Friedman in 1983 and started talking about bismuth's gravitational irregularities. Coincidentally or synchronistically enough, just 2 hours before I found that out, I found out about those gravitational irregularities from a different paper. So I saw this thing about Stanton Friedman and Sarbacher. I'm like, wait a minute, I know exactly what it was Sarbacher was referring to. It was called the brush kinetic theory. And this was some scientist back in the late teens and early 20s, 19 teens and 1920s. He was doing these pendulum tests with 5 different kinds of metals, like iron and aluminum and zinc and bismuth. He was doing all these different, really good pendulum tests. And he was noting, do all of the different metals, when you account for all the variables, do they all swing at the same period? Or do any of them, change, how fast they swing, indicating they have a different relationship to gravity? And he put zinc as his control sample. So he says, okay, this one is the most perfect gravitational one. Aluminum was way faster. It oscillated way faster than zinc. And then bismuth swung way slower than zinc. And so it seems like this guy 100 years ago figured out that bismuth doesn't obey gravity all that well. And he reproduced the test in 1922 or 23 instead of just doing pendulums. I think he was doing drop tests or other momentum tests. And he, once again, validated his original experiment. Quite interesting. Let's get into some of my more favorite out there stuff about quasi-crystals, because these are the things that have just captivated me for the majority of the time that I've been researching this. So it turns out that the Trinity nuclear test back in 1945, that created quasi-crystals from the nuclear explosion. What? We didn't know about that until 2010 or 2020 or something, when somebody went back out there and knew to look for them. But yeah, the earliest human created quasi-crystals that we can find came from the nuclear tests, which seemed to attract attention of all the aliens or all the flying saucers. So, just put that in your back pocket. Quasicrystals have this really cool thing about non-locality because they're a non-normal crystal. They're not like a cubic, three-dimensional cube crystal. They're like aperiodic like this. That means that when you push or you dislocate one cell of those, it actually has like downstream effects on the other side of the crystal. It can like do action at a distance type stuff. Super interesting applications there. Information processing, whole field. Like I could have a whole talk just on the information processing side of quasicrystals. Oh my God, that's amazing and could completely revolutionize literally everything. I'm getting a little too excited about that one, but like so much on the information processing. So instead of phonons, which are like oscillations in a normal lattice or like sound waves or mechanical waves, that's a phonon. Well, when you're operating with a weird lattice like a quasicrystal, it's called a phazon instead of a phonon. Who cares what you call it? But the cool thing is that you can have this coupling between those two things, because when you look at quasicrystals in higher dimensions, you end up seeing a whole bunch of normality to this crystal, but you slice it down and you go into our dimension, and now it looks all wonky like this, right? Well, there's ways that you can make coherent phonons from quasicrystals, which if you can make coherent phonons and you can couple those to the phazons in the quasicrystal, there might be a whole other angle of alternative propulsion just waiting to be devised from this phonon coherent phonon coupling stuff. Obviously, I don't know nearly enough about this to talk intelligently about it, but that will probably eventually come. I would love to do a presentation at some point just about quasicrystals. I know Jeremy Reese has already done a good amount of work. So has David Chester. They've done a lot of work on quasicrystals. So I would reference you to them far before myself. Anyways, there was a Russian meteorite. So the only other naturally occurring quasicrystal that has been found came from a Russian meteorite back in like the early 2000s. And that thing had a icosahedral symmetry to it, which is interesting because magnesium zinc of the arts parts would mean that it must also have fivefold symmetry, icosahedral symmetry, if it does have quasicrystalline nature to it. So the information processing, one last thing on the information processing. These new computational methods that you could devise from that, like just jumping right into the deep end of the Kool-Aid pool, like you can describe certain different kinds of consciousness. You can describe plant consciousness as well as human consciousness, all the microtubule stuff. You can describe that using quasicrystals. So it's interesting to start looking at the overlaps between information processing using quasicrystals and consciousness using quasicrystals, as well as maybe some higher dimensional information processing that the universe might be operating upon if the universe is computational in nature. All right, we're just about done here. So here's what we still need. This is what I would suggest that anyone else that's really interested and wants to spend some time looking into this, here's what I would suggest. Can anybody find a special use case for this bismuth, magnesium, zinc? Can you find a paper that was written prior to 1947 that talks about these three things being used together? Because that would be really interesting. Especially if it was with regards to some kind of thermoelectric, thermoluminescent models. Here's a little something that most folks don't know. So I am okay at being able to track down people from time to time, and I started trying to track down this original grandson source. Here's what I was able to find. He was from South Carolina. He was going to South Carolina to mail these letters off. And in the letters, he says, like, I actually live in Virginia, but I take these military hops out of Pope Air Force Base in North Carolina down to South Carolina, which is why all these letters are postmarked from South Carolina. After the last letter, he called Linda up on the phone. This is the only time Linda ever talked to him. He mentioned, Linda says this in one of her things, he mentioned that he was going over to Iraq in 1996, later summer of 1996. So I wasn't able to talk long, but that was like the last correspondence he was going to have with them. Well, I did the digging, and sure enough, the South Carolina Air National Guard went over there. Also, that C-130 pilot friend that he had suggests he might be C-130 crew. The weird thing is he uses some words that suggest this guy is not a pilot. He claims to be like a commissioned officer of some kind, but if you really wanted to like inflate your title, you could say you're a non-commissioned officer as a commissioned officer. So he might have just been a striper rather than a brasser. And some of the words he uses makes me think he might have worked in logistics. I was picking the brain of another veteran who was a veteran in the Air Force from that time. And I read all the letters out to him, and he's like, yeah, no, this guy is not a pilot. This guy's probably not even air crew. He might have gotten his wings from like being active duty and then palace chasing over to the National Guard. But this guy talks like a logistics guy. So interesting. I think that with enough gumption and like 1 or 2 FOIA requests, it'd be pretty easy to figure out who this guy was, which would be good because then we might be able to track down the journal, hopefully, whether or not this guy's even still alive. But we might be able to track down the journal from the grandfather, which would be huge. There's a lot of stuff in there that we didn't know about. Yeah, that would be interesting. Anyways, RTG and TEG research prior to 1950. And then anybody that wants to look into how quasicrystals can be related to thrust, highly encourage that as well. Here's the last slide I got for you before the bibliography. Right now, as it stands, this is my analysis of it, combined with the analysis of a bunch of other material scientists I've talked to. This thing seems like it was made terrestrially, and it could have been made prior to 1947. That said, the materials here, it looks like it could be used for thermoelectric type stuff. And if this thing has quasicrystal structure in it, that is the smoking gun that this thing is like either not human made or was made by somebody that knew a lot more than anybody else at the time for the next like half a century. Here we go. So here's the bibliography. Anybody that wants to check this out, here's the long address for it. I got the short address, which is a tiny URL, parts Falcon Space. Here's the Linda Moulton Howe interviews. I highly recommend checking those out, especially this first one, because Travis Taylor tested this thing way back when, and he tested the sample at 500,000 volts and 1.2 million volts. He got the thing to kind of dance around, whatever that's worth. It was a little bit hokey, I thought, but you know, it is what it is. He did a good test on it. We got more links. Highly recommend going through whichever one of these seems interesting to you. I think they were all interesting, but the Ubatuba, that white paper, if you're interested in learning more about like the process that should be done for going through and testing recovered materials, that paper goes into great detail. Also this book, you don't have to read the whole thing, but I highly recommend at least reading pages 43 to 50. That'll teach you a lot about what I was saying with the White House flap and the Norwegian Air Force. Highly recommend that. Going down here, here's a paper, like 8-10 page paper that some material scientists shared with me that kind of helped give me an idea on the fact that this was indeed a process that was possible. There's some phase diagrams for magnesium bismuth. Here's an extremely recent paper on how this stuff might actually be used for thermoelectrics. Highly recommend everybody checking out Tim Ventura's shared pictures of the samples that we took. I did a Reddit post this week talking a lot more about the quasicrystalline stuff of this. Jeremy Reese did some good quasicrystal research. And then I got this working document that is messy as all get out, but I had to cut out a ton of stuff. As you can see, I'm running out of time. This working research document, if you're interested in learning a bunch more that I didn't share, I suggest following that link and torturing yourself by trying to make sense of the disorganized, semi-organized pattern that I got for that research doc. That's all I got.
Awesome. Jarod, that is amazing. That is absolutely amazing. So let me bring everybody back in. Let me see. And guys, put your hands together for an incredible presentation by Jarod Yates. Jarod, thank you.
There it is.
And you know, so I should mention also, Jarod pulled that together in 1 week. That was only 1 week.
4
You know
days.
Four days.
Actually, Jarod was going crazy about it ever since we found it. It was unexpected, to say the least. There it is. Yeah.
So yeah, this is, I just wanted to put this up really quick. This would go along with Jarod's presentation. So I was filming during this entire thing. So there's Mark and Jarod and Tom Butler from Falcon Space. And this is when they were doing the investigation on it. So I've got literally over 2 hours of 4K footage. So this is as high res as it gets. So I've got that. And then the other part, and let me paste this link in here, is, and I'm very proud of this. Let me see, I'll scroll up quickly. This is, again, photos that I took of the entire process. And again, you could see Mark, Jarod, Tom Butler, Eric Rivera. That was everybody who was there. And then obviously I'm the one holding the camera. I tried to basically get as much as I could of this to kind of show you guys what they were doing. There's Jarod doing extra measurements on it. And then they shot a ton of still frames using a 4K digital microscope. And we did that under different lighting. And so I've got over 100 still frames in here just to kind of show you guys. And since we're recording, I'll scroll all the way down to the bottom. My material.
I actually have some digital SLR photos that I took last night.
Did you, Mark, do you want to upload those or do you want to share your screen real quick?
I'll share my screen. I have it off to the side. Their better resolution was 30 megapixel camera with a macro lens. My brother actually had.
Oh, yeah. Please share, sir.
I drove down to Tom's River just for this. Let's do share screen. And there it is.
Hey, Jarod, how thick was that sample again? The actual thickness?
Can you guys see that?
I can. Are you able to zoom in a little bit, Mark? It's a little on the small side. The picture itself. There we go. Wow.
Oh,
I didn't measure the thickness with the calipers because I was afraid of crushing it, but I have plenty of pictures where it's sitting on top of a penny. So you can use the thickness of the penny kind of as a guide. And it was about 1/3 to 1/2 as thick as the penny. It's very, very thin.
It's like comparable to a grain of rice. This is a very small sample, but you can definitely see that the layers are there. Some of these pictures were taken in broad daylight. We went outside in the 100-degree heat, and we had to do it in 5-minute shifts because it was so hot outside.
Your brother did an amazing job, man.
Yeah, I think these were taken in artificial light. We have some of them that are overexposed, underexposed. We just tried to get every kind of angle. This is a really nice one. So I found that with the lower f-stops, where you just have one part in focus, you get actually a better cross-section of it. So this is probably only 2 layers of the magnesium, zinc, and bismuth. So it's not even the full thickness of the original sample. And that's evident. This is probably a chip that was taken off one of the edges of one of the larger pieces that Linda had. You can see the glue on the right there. Looks like a strand of hair. That is foreign debris. That's not part of the sample.
And I feel like iridium? No, this did not have iridium. I also feel like it's important to mention, a lot of people on Reddit were saying, why aren't you testing this in a clean room? Why are you testing it in such a dirty place? Just, railing against our test methods. It's important to note that, we weren't expecting to have this. As soon as we got this, within 2 minutes, we were all just so excited. We're like, get it under the microscope. Let's see if it actually is what it's claimed to be. So
what you're seeing right now,
area.
Yeah, we did. What you're seeing right now is actually sunlight. So when it's the previous pictures, these are under artificial light. This is in sunlight, and the bismuth starts going crazy with all these different colors, but only under sunlight. And the exposure is a bit low, but you can still see all the craziness of the bismuth there. Yeah, I think all the pictures from now on are taken in direct sunlight.
Yeah, that's amazing, Mark. Thank you so much for driving that down there.
And I think that's the last picture. This was placed on top of a piece of
really
glass.
Good pictures, Mark. Really good.
Thank you. I'm going to stop sharing right now.
Yeah. Well, so, and again, it's I think it's also worth pointing out that Jarod and myself were not at Falcon Space for this. We were there for Mark's apparatus. When we do lab time here in just a moment, hopefully Mark can kind of walk us through some of the equipment that he's using there, because what we were there for is, I mean, amazing. He is building some amazing stuff, and that's what we were there for. So, but
Yeah, I was just cleaning up and just found it on the table. I didn't know that it was sent to us.
Do you guys have any questions for Jarod? Yeah, Shiva, go for it, sir.
I was trying to understand. So, I'd heard about the version of this that where did the iridium come in? Because last time we were talking, that's what I was talking about, is using it as a type of voltaic pile, and then that they were somehow using the anomalous Hall effect as like a feedback loop. And so that's was the iridium in a different sample, or because you're saying it wasn't in this sample?
Okay, so here's the iridium thing. First off, the Hall effect angle on this, I'm a huge fan of. It seems really likely that is in the top running for possibilities on the use case for this. The iridium is hearsay. We do not have any testing for iridium, so we don't have conclusive one way or another. The iridium hearsay came from one of the conferences that Linda did, I think prior to 2004, where she was talking about this thing, and a guy comes up and he says, "Hey, I work at S4 on a 3 foot by 6 foot sample of this." She says that he provided conclusive evidence of his identity and who he was, so she trusted him for what that's worth. But what he said was the aluminum, that first package with all the aluminum cutouts and punches and stuff, that aluminum was the outer hull, and that aluminum had atomically placed iridium, so doped iridium or something. And he was saying that it was that outer hull aluminum, mostly tiny bit of iridium, that works with the inner layer, which is the arts parts layered material layer. And when those two work in concert together, that's when you get some kind of lift effect. So the iridium could be a red herring for all we know. It could be a total red herring. It could be a disinfo thing. We don't know, but that's the information we have.
Yeah, I was thinking that it would could replace the electrolyte as iridium oxide, and that would still make a voltaic pile at that point. And so it was, it was interesting. That's really cool stuff.
The one thing that didn't show up that I really hoped was going to show up was antimony, and I couldn't find any of the tests that show the antimony showing up, and that would indicate that it was being used as some kind of electric generator, thermoelectric generator.
Also, if you'd like to talk about quasicrystals in 3 dimensions, this is something I 3D printed myself and placed all the magnets in it, et cetera, to be able to trace how poles, et cetera, would work. Because you probably know there's a rhombic tricontahedron, which is a polyhedral dual of the dodecahedron and icosahedron. And I'm actually working on a program right now where there's papers on how spherical harmonics actually produce the platonic solids, and understanding how these polyhedral duals work within that is part of what I'm producing this program to show.
You and I got to talk later at some point, Shiva. I suspect we could have a great quasicrystal combo.
This is that cross-pollination right here. This is that cross-pollination. So,
Yeah, this is, by the way, I have a good reason to believe that getting down near the Planck scale, if you're going to have a particulate ether, it would be a quasicrystal. These both of these shapes, which are just your two, these are basically what are they called? Golden rhombohedrons. There's this sort and this sort. Both of them are space filling, and that's how you produce a 3-dimensional quasicrystal that is space filling.
Hey guys, it looks like iridium doped aluminum has a dielectric permittivity based on its frequency.
Oh, what range? We talking megahertz, gigahertz, terahertz?
I don't know. I'm just looking at papers, kind of the titles of them. But you're talking about something that's part of a propulsion system that's got variable dielectric permittivity.
Can you upload a link to that?
I gotta tell you, I can do amazing things by changing the permittivity of materials.
Share a link to the paper, Drew.
Interesting.
Yeah, see, we're coming up with stuff.
Just throw it out there.
And you know, there is no, I mean, just for the audience, and I've tried to put this out there also. I mean, there is no guarantee that this is from a UFO. There is no guarantee that it is extraterrestrial. There's no guarantee that it does anything special. You know, what we have verified chain of custody that this does belong to the arts parts sample collection. So I would say it is as valid as those parts are, but past that, who can tell, you know?
For all we know, those parts were made in 1996 when they were given to Linda. For all we know, that's the first actual chain of custody we have is 1996. Because we don't know who had them before that. We don't know who had them before that, right? So if we can track down that guy or his surviving relatives, and we can get a hold of that journal, that would be huge. And I think that's possible, but it's probably going to require one FOIA request. So let's get Black Vault in on this. Let's get our one FOIA request, and let's find that journal.
Wasn't
on
there
that note,
an isotopic ratio test done on it and found that the magnesium was non-terrestrial based on the isotopes?
Nope, that was part of the thing I went through, was showing how there's been multiple isotope tests done on it, and on Art's part sample, the magnesium is not like in any way extraterrestrial looking. Like on that graph, it looks like, oh, it's outside the norm. No, it's 2 data points, right?
Yeah, it's within the error bars.
It's totally within the error bars. I talked to a couple different material scientists about this during this week. I was like, hey, help me out here. How doable, how likely, all that jazz. And they're like, oh yeah, no, this is definitely like something that would have been done around that time within these ranges of isotopes. Like, for example, the Linda Moulton Howe graph with those 2 data points, like the control sample, that's not even actually accurate to what is the accepted values. The accepted values are actually above that. So once again, here's one way that it could still be weird, is if it has an abnormally like normal amount of earthly terrestrial magnesium, almost like they were purposely trying to make it look like, no, this came from Earth, which is one argument that I came across was, oh, the aliens make sure that they make all their stuff using only Earth stuff so that we can't figure it out, which is a big old reach.
I mean, they're just to play the devil's advocate here, right? Maybe it is being reproduced. Maybe these craft or something like that are being created here on Earth. So
one of the going theories is from a 4chan whistleblower, for all that's worth. And that guy says that there's like this gigantic mothership under the ocean.
I've heard that.
Yeah, it's the factory where they make all those. And like, if you look at the different kinds of saucers out there, there's like 50 or 100 different kinds of saucers that have been like observed and witnessed. So like, they're made for specific missions, specific use cases, and it doesn't seem like they have, you know, interstellar travel capability. Probably not. So yeah, terrestrial made, maybe ultra terrestrial. Who knows? But yeah, the whistleblower thing about the mothership under the ocean, that's a fun trip.
Well, guys, why don't we do this? Why don't we put our hands together one more time, and then we'll go to lab time. So, Mr. Jarod Yates, thank you so much. Thank you. I genuinely mean that. I've been pressuring Jarod, and so, you know, thank you for bringing this together. Yes, I will quit bugging you for a while. But okay, well, guys, so let me, you know what? I guess I'll leave. Who wants to go first for lab time? Mark, do you want to do lab time?
I don't really have much prepared. You guys kind of covered everything that we actually did already.
Do you want to walk us through the DNO machine? Are you able to kind of drag the camera over there? Or? You've got some pretty, dude, you have some pretty amazing stuff. Mark has been scouring the East Coast for equipment and modifying it.
That's about as close as we can get right now. You know what? I'm gonna add an extension to this camera, and I'll be right back.
Okay. Well, yeah. I mean, for lab time, Drew, do you want to go? Why don't you go, Drew?
Sure. Well, thanks to Tim, there's a video up there which kind of I walked through an entire test that I ran while Tim was here, and we had some friends here from. Well, it doesn't matter where they're from. We had some friends here, so we were showing off our toys to some disbelievers who left believing. So So there's a lot of really coolness going on in that video. If you want to go take a look at it, you know, I don't know, leave a comment maybe or not. I don't know exactly if comments turned on or not. But the testing I was doing was basically I had 2 plates in the chamber, and we were running them to negative 9,500 volts. We're generating about 1 millinewton of thrust. It was instant on, instant off, and right after Tim left and Mark left, I pulled it out of the chamber, flipped it around 180, put it back in, and ran the same test. And of course, it generated thrust in the opposite direction. Not quite as much as it did while it was in the one direction, but the problems were from charging. This was an instant on, instant off thruster test that I'd run like 38 times. And after you run these things enough times, you can pack up charge in that plastic. So I turned it into a an absorber. And once it absorbs charge, it takes weeks to discharge. So that's about all I've been up to. I have been removing that test article. I built another one, put it in there, ran the same test. Then I've been slowly changing the distance spacing between the plates because we are getting ready to produce a 100 millinewton thruster, which is going to be based on this. This is just a little prototype of the printed frame, but we're going to be doing a printed frame. There's going to be about 20 of these, 25 of these stacked up like that. And this is going to be a 100 millinewton thruster. And it's going to look something like this. Very coolness. But that's about it. We're headed toward a couple different major builds, but I'm not going to talk about them until I actually have something to show. But there's a lot of coolness going on here in Florida. It's extraordinarily hot out in that shop. It was 105 degrees in the hangar today. So y'all talk about being warm somewhere else. You ought to try down here. That's it. That's all I got.
Awesome. Drew, thank you so much. So let me, you know what, if it's okay, let me share one more time here. So I want to share, let me see if I can. I'll stop sharing. So I was just I flew into Florida, and so I want to show folks, just if they haven't seen them yet, I got a bunch of photos in your lab. And thank you, Drew. Thank you so much for letting me come down and get photos. So vacuum chambers, lots of components, layout of the hangar where you do testing. I mean, tons and tons and tons of stuff. This is just amazing photos. Drew has, this is the vapor depth machine that he has. And we just kind of went through the whole thing. This is an old vacuum chamber that's no longer used. Just tons of stuff. I mean, Drew, it is absolutely amazing. And then the other thing that I wanted to show people, and I'll at least show them the link in a moment. So that's all the photos that I got. And let me see. I'm going to put this since I'm sharing that.
And
link.
yes, that's me, the pudgy guy in the blue shirt.
There we go. Okay. And is that displaying correctly? Yeah, perfect. Mm-hmm. Okay. And so I just put this up yesterday. So even for folks who have seen the photo gallery, Drew was kind enough to shoot a ton of video for me. And so I put up basically an engineering test. We went through a test run of the system. And then he showed me the results, and then we just discussed various applications and how it all worked. And so this is like an hour of, again, 4K video footage. I tried to do the highest quality I was capable of. I am not a professional film and media person, but you know, I'm doing my best. So again, Drew, thank you so much. And I can attest to the heat. It was definitely warm, definitely warm. Okay, so let me see. I'll bring everybody back in. Mark, did you want to do? Are you able to drag it over closer now? Oops, I can't hear you, my friend.
I think you're muted, Mark.
Yeah,
I actually, he's not. Oh, there we go.
Yeah, he may be
No,
physically muted.
He does. Yeah, you don't have any sound.
His webcam is the microphone. It's got issues on that.
How about now?
There we go.
Now it's working.
Oh, okay. Yeah, I was playing with the settings, trying to get it to work. I added extension cables. It's not going to get any closer than this. So let's just try it in this form, and I'll get as close as I can. That's about as close as we can get. So yeah, this is our latest S-band EPR machine. Jarod came down, and we were working primarily on this machine, getting it set up. We have the RF amplifier from Sandia National Labs over there, along with its extra computer CPU cooler. I keep it nice and cool, so we loaded that up. We got our signal generator hooked up. The probe, this is the Gauss meter probe, has been wired up. It still needs to be installed. There was a thermal gravimetric analyzer scale balance on the head of, as a measuring device to give us our signal. And Jarod and I worked diligently trying to get that thing running. Jarod did a freaking pinout of the controller for it. He spent like a whole day doing this. And as he was doing it, I just decided to have a plan B. So we ordered a 10-gram super sensitive scale probe. And when that arrived, and we still hadn't gotten the thermogravimetric analyzer scale to work, we just went ahead and installed that. It's already hooked up to an amplifier. There is a little bit of noise in it, but there's a wire that runs all the way back to the computer up there, and that's hooked up to LabVIEW, and it's already been programmed in. So we're pretty much ready to go. I'm going to have to change out some of the cables, and we're also going to be inserting some RF absorption material inside the vacuum chamber to stop RF from hitting the scale. The scale being the little 10-gram force sensor. And the force sensor is also going to be surrounded by, like a little aluminum foil cage or something to help protect it. But of course, there needs to be an opening in that for the sample to stick on. So it's not going to be 100%, but we're going to do our best to shield that very sensitive force gauge from the powerful RF that's going to be bouncing around inside the chamber and get us the most noise-free signal we can possibly get. So we're probably like a week or two away from finishing this project. The RF absorption foam is in the mail. What's his name? Drew, you probably recognize the Welsh vacuum pump inlet. That's a vacuum meter that I pulled off out of Drew's lab, and it's been repurposed here for our S-band EPR machine. And I think I got another one over there that was also donated by Drew. Actually, we have two of them identical now. So, yep, that's pretty much it.
Awesome, Mark. Thank you so much. Thank you for walking us through that. Again, it has been absolutely insane, just the progress that is being made. So I'll bring everybody back in who's with us here. And guys, I guess why don't we go to let's go to open discussion. Curtis Horn, I should mention, he is doing some family activities, so he's not going to be with us today. I am going to be flying down, visiting Curtis and Jim probably at the end of the month, and then I have a couple more short trips scheduled, and at some point I need to fly down and get some photos for Shiva as well. So I'll figure it all out.
Yeah,
Some Vegas heat here. In up north, they take water, throw it up in the air to show it like freeze. Before it hits the ground. Here, you throw it up in the air, it never hits the ground.
Yeah. Well, I lived in Phoenix for a year, so yeah, but it's been a while. It'll be,
I'll take 100 degrees heat with no humidity over 90 degrees heat with humidity any day.
I lived in Memphis. I know all about how, you get to like 105 and it's just killing you. It's crazy.
We had 95 degrees, 95% humidity today in the shop.
Wow.
There's nothing you can do. It doesn't matter whether you turn a fan on or not. It's nothing. It does. There's no swamp cooler effect.
Yeah. Oh, yeah. That's a
Your
good
shirt
point.
doesn't dry even with hot air blowing on it.
That was what I liked about Phoenix. Is it's so dry that the swamp coolers and stuff really do work. So. Okay, well, yeah, I would say, guys, open discussion. This has been one heck of a presentation. Thank you so much. I mean, all of you.
So, Drew, you were mentioning a couple of times to me what you would do if you finally got your hands on a low molten hell sample. Now, we have it right here. So what was your idea?
I still have access to a very nice SEM with backscatter capability.
How much zoom can you get on that?
I don't know. But they spent about $40 million on that toy.
That's probably more than the one that Mark's group has access to. That's a university one, right, Mark?
I have no idea what it is.
Yeah, well, and that beats. Jared and I were looking at microscopes on Alibaba. We found one for $100, so it probably beats that too.
20,000x, $100.
I should probably get a microscope for the lab.
Yeah, I've got access to an amazing Keyence microscope. And I don't know if you played around with high-end microscopes, but they go very high-end.
Well, there's a limit to what optical can do.
Mm-hmm. Spend enough money, and that limit's really close to what an SEM can do.
You know, one thing I should mention though is, you know, we in the space of a day, I mean, we took, I don't know, probably, well, in terms of actual photos, we had over 200 photos, and we did several hours of high-res video. And since then, Mark has done, you know, another set of super high-res photos. The original Arts Parts, I mean, there's like a dearth of photos out there for it, you know? You've got like 1 or 2 photos. That's all I've ever seen.
You know, I'm kind of curious if I was thinking, you know, you said that Taylor guy, he put a couple of million volts or 500,000 volts on that. Voltage doesn't mean anything. That stuff is all going to be field driven. I would love to throw 10 to the 8th field on it just to see what happens.
It would short out. It's metal.
Taylor used a Van de Graaff, I think.
I didn't say put 10 to the 8th through it. I was thinking like a metallized Kapton, put it in the middle.
Yeah.
And put 10 to the 8th across it so that it polarizes up to 10 to the 8th.
That's a cool idea.
That's a very interesting idea. I think it would take more voltage. I don't know. I gotta think. I gotta think about that. That's why I wonder how thick it is, so I could like put a little piece of something in there.
Let me pull up.
Crank up the voltage and find out just how much field I can generate.
Let me show you a picture. So there's a problem with the sample, and 1 second. It's mostly this crap on the right. You see that stuff there? The glue. It makes it very ununiform. It's not a flat piece.
That's all right. I would put it between 2 pieces of Kapton and put the metallization on the outside of the Kapton. It'd have to be like 5 mil thick Kapton because we're going to have to jack this up. We're going to have to put 100,000 volts on that Kapton.
Yeah, those are amazing photos, Mark. Your brother did a great job.
There might be a way where you could very carefully cut off some of that glue or remove some of that glue without potentially risking the sample in order to make it a little more flat. Because, yeah, like Mark's saying, if you try to put that thing in between Kapton with that glue on there, you're going to put tension in the very center of the thing. Even, you know, if it's loose Kapton, like there'll be tension on, and then you put that field gradient across it. Now you got some force on the thing, and the thing is really small and really brittle.
I mean, what I'm thinking is, what if we just called up Linda and asked her for some more? Said, hey, can we have a sample?
So she has 1 piece left, right? And that one piece left is sitting in her safety deposit box. And I think she's gotten more and more hesitant over the years to let people test it, because according to her, she's found out more and more weird things about it. So she was actually saying in her most recent interviews, like, yeah, I sold it for the price of doing business, but like the value of what's in this box, it's probably worth around 3 million now. That's her number. But this idea that some of the other stuff that she's got like 3 big folders of like all of the tests and the data on it. And from what she's seen in those, she thinks that it's got enough weirdness to it that it makes it pretty daggone valuable.
Yeah, I was thinking that they're talking about the idea of it being a waveguide, et cetera. It may have been heated so much that a lot of that deformation is from it being damaged by the heat, so it may no longer function the way it would have functioned if it were still very uniform and hadn't been heat damaged, because that's kind of what it's looking like to me.
Or maybe the thing was supercharged, and when it hit the ground, it discharged very rapidly, and so all the charge that was in there created an overcurrent, and so maybe those things got
Yeah, it's also I think the primary value of this really is, I mean, there's historical value, but it also just provides insights and ideas, right? Spurs the imagination. And again, it's worth mentioning that Mark has scoured the country for samples. He is testing a ton of stuff in this. So this is just one of the samples he's testing. Now, as far as I know, the rest of them are pretty, I don't want to say normal, but I mean, they don't have the mystique that this has, right? But he's testing tons of different arrangements of chemistry.
That's right. That's right. I mean, we could make something like this if we really wanted to. But the question is, why would we want to?
Yeah. Yeah, you're reproducing something, you have no idea what it does. You're better off just starting with something, one layer of whatever it is.
Well, if it does anything on its own, that indicates various possible uses for it. In other words, like if it's actually doing something, with a charge that's, either I don't know, if it's doing something that you would not expect of just layering a few materials, like with the like I was talking about with the voltaic pile idea. If it's doing something special like that, then that's not a use that anybody, that we know of or heard of has ever, developed a material like this for. So it kind of, I think reproduction of it at a larger scale would probably prove something about the fact that it isn't just some random piece of trash that has been with too much attention, which a lot of people who are skeptics, that's kind of their first, because they're not looking at it deeply. And if you've got some sort of replication of it that shows some sort of effect that is more than one would necessarily expect, I think that kind of is something you can put out that's very simple, straightforward, that people can understand, that they'll start to look a little deeper.
I wonder if this might bring other people with samples kind of out of the woodwork, so to speak, also. And I guess that would depend if we're doing a quality job with it, right? I mean, if we're presenting it well, if we're describing it well. But, again, by taking this information and getting it out there to people, the vast majority of people are never going to see a sample of this in real life. That doesn't necessarily mean that it's real or valid or helpful, but at least we're getting them a little more to work with. And my hope would be, if we do a good job with this, maybe folks who have other samples, right? Like the Utabawa, I think that was the other one that Jarod mentioned. Gary Nolan had worked on that. Jacques Vallée had a few samples that he gave to Nolan. Man, I would love to be able to do analysis on those too.
I think a lot of samples also came from Russia. So Russia has had a lot of crashes as well, but those ones are much less well known in the Western world. Also, there might be some remaining samples over in the South Africa Kalahari crash of like '89. It seems like that area may not have been perfectly scoured, so that might be another area worth going and looking at with a metal detector to find your own samples.
This is going to sound silly, but did y'all pass a metal detector over this thing? Does it register as metallic?
I said that I ran a magnet over it.
Yeah, but I mean like an actual, whoop, whoop, whoop,
No,
That was
although
my thing.
we didn't. Although this was a test I was going to suggest to Mark. Mark, you should get your most sensitive RF probe and hook it up to your spectrum analyzer, like both spectrum analyzers for the widest frequency, right? And just like tape the thing down, upside down, and just set the sample on the metal tip and see if the sample has any specific frequencies that it's putting out. The reason why I say that is because I found something from one of the alien implant things was saying that it gave off like a very specific like wavelength RF at a certain frequency. So it might be worth just seeing if this thing naturally puts off, and then while it's sitting on that, you can like shine different lights at it, or lasers or whatever, and see if like that changes, if it has some kind of photoelectric response to that. It would be very interesting to see if this has noticeable megahertz to gigahertz frequency response.
So you're saying that excite it with like a broadband RF and see what it's pinging back?
First I would just like take a baseline noise measurement without the probe touching anything. And then I would, with very careful like tweezers or something, set the sample on the tip of the probe. And I would just see how that waveform changes and see if you get any little spike. The spike amplitude will probably be really small. So you have to like look really close. But it's possible that this thing might reveal additional qualities from RF measurements.
It's also worth pointing out that this might not, even if this is from a UFO, right? As they, as they've speculated, this might not be propulsion related. So potentially this could be some kind of sensor or. Jared and I went through this in the video because I always ask lots of dumb questions, and one of the things I'd ask was, could it be structural? Jared said no, it's far too brittle for that, but it's possible that it could be some kind of sensor or something.
If we go off of what the grandfather said, supposedly, it was for the propulsion. But once again, you got to take all that with a grain of salt. Maybe this thing did indeed come from a UFO, and maybe the whole story behind it is bunk. Maybe it came from a totally terrestrial UFO, and there's a bunch of misinformation in it to throw people off the trail, and this guy still managed to get his hands on it, but he came up with a story. There's so many possibilities for this sample that retain the weirdness, awesomeness, but also you got to throw out some of the story because it's sus.
Yeah.
I love that rainbow effect you caught with the camera. That's really cool looking. Looks like opal.
Yeah, that only happens in direct sunlight. With the artificial light, we weren't getting that.
Yeah, full spectrum.
We tried a variety of different focal lengths, and we tried different different settings on the camera. I'm picking out a few of them. There's more pictures that I haven't had a time to crop out yet.
Something else worth observing in these pictures that Mark is showing is the outermost edge and the break off shape of that. So zoom out just a little right there. So on the lower left-hand side, you can see you got that bulge outwards, and then just to the right of that, you got that concave cut inwards. I would be interested in taking measurements on that and seeing if, that's a hexagonal structure there, right? That's a hexagonal cut. It seemed like the outermost edge of it had like basalt-like vertical columns, right? So it's got some weirdness to its physical makeup in those regards. That's worth much closer inspection with much higher resolution images.
Yeah, and that's what I worry that some of it is like bubble. You just put bubbles together and they create hexagons and things like that. But at the same time, there was also looking like there might even be pentagonal structures in there as well that I was noticing. So it's interesting, because it could go either way. It could just be
I think Jared mentioned pentagonal. Jared, didn't you mention pentagonal structures?
So the angle that gets me super excited is the possibility, and this is huge speculation, but the possibility that it's using hexagonal physical structures and it's got 5-fold pentagonal quasicrystals inside those hexagons. I think
you could see it kind of broke off like a pentagon or I don't know what, but the cracks. It seems like the sample was broken off of a larger sample, and there is these. I think those are octagon, 120-degree sides, just like in the cuts. Like you can see how the cuts were made. It follows that pattern that you're seeing on the other side, on the regular top.
It's also worth mentioning. There's some good UFO lore out there from people who claim to have written on UFOs. There was one story, I think it might have been more than one story, but there's a story coming to mind where people say they're riding on the UFO, right? And like one of the beings has to like get something from the lower level, right? And so to get to the lower level, what they do is they just stick their finger down into the floor, which turns out it's a hexagonal mesh. They put their finger in and they just kind of pull it away, and the whole mesh floor kind of opens up a hole. They reach down and grab what they need, and then let go, and the thing goes whoop and comes back together. Just another, hexagonal UFO thing.
Yeah, it's fun stuff. Sometimes the speculation gets the creative juices flowing, if nothing else.
Another hexagonal angle is aerospace. So there's certain parts of aircraft which demonstrate a similar hexagonal structure, and it's killing me that I can't remember exactly which one. I thought it was the air filter. I was asking a military pilot, I was like, isn't it one of the air filters? No, those are square. The hexagonal one is from like, fuel filters or some part of the engine, you thought. But pretty good authority that airframes utilize hexagonal mesh things for something somewhere.
Yeah. Well, and again, I'm so happy that we were able to. I'm happy that we had the opportunity. I'm happy that we're able to get this out there. And one of the things that crossed my mind when we were looking at this was I was like, wow, we're actually spending time up close and personal with Art's parts, and I think a lot of people would probably want that as well. But like one thing I would put out there is the actual size of this thing. Like Mark said, this is like a grain of rice. So even if you were looking at this thing directly, you're gonna end up seeing what you're seeing right here. You'll see it in a microscope because there's not much that's there for the visible eye.
Really good stuff there. Yeah, I was happy to see the show. You guys got I know you guys would get access. What was the story again? How did you guys end up getting access to it? It seems like it was
an anonymous donor who gave it to Mark, and they swore us to secrecy on it. And the reason it wasn't anything nefarious, they just don't want to get mobbed by UFO buffs, right? And unfortunately, with stuff like this, when they said that, I'm like, yeah, okay, that would happen.
Yeah, I mean, we got a bunch of samples, and it was kind of just sitting in a pile for a while. It was just sitting in a pile for a while on my desk. And I got samples all the time. I got boxes of samples over here. People are like, yeah, try this, try that. And I was going through this sample pile because Jarod and Tim were there, and I wanted to clean up the lab so that Tim could take professional pictures. And I'm like, holy shit, what is this? And I show it to Jarod, and he starts screaming like a little girl. And then Tim wakes up. He was sleeping on the couch. Tim wakes up.
You didn't even know you've got it? Holy crap. That must have been
I had no clue that I had it. It was just handed a pile of samples.
Well, again, Mark has tons and tons of samples. He's got tons. I mean, Mark, do you want to run through some of the other samples that you're working on?
I mean, I have way too many. Stuff that I'd be proud of. Check this. I got a piece of what is this from an X-ray machine? I mean, there's boxes of samples over here.
Oh, that's the tungsten, right?
Yeah. This is solid tungsten I got. So this is for just a heavy material to stick in inside of some experiment. It's non-ferrous, so that's good. And also, if you hit it with high voltage, it'll make lots of X-rays for us.
Yeah. I mean, the larger picture is there's so much moving forward so rapidly right now. It's really exciting for this community. This is like, I mean, and in terms of theory and in terms of concepts, I think that there's massive convergence and there's things coming together. And then in terms of experimentation, there are a ton of people who are building stuff, I mean, it's truly, it's exciting and it's humbling, right? So, you know, as a moderator, I just look at this and I'm like blown away every time we do one of these.
William says that I'm going to beat him to the finish. Well, where's he at? William, where are you at? What you got going on?
One other fun story about when Mark found this thing. So he had, you know, now that he's cleaned up and now he's found this thing, he's like, we got to clean up more. We're going to find, you know, see what else we got. Right. So right as I've come down and my blood pressure has like finally gotten to safe levels, then he's like, oh, wait, I think we got more UFO samples. I started hyperventilating. I may have run a lap or two. I was just out of my gourd with excitement. It was too much. It was too much. Thankfully, he did not have other UFO samples, or else I would have totally lost my mind.
Yeah, they were just weird melted glass from, I'm not really sure what it was. It was a box full of really weird samples. It was like, there was glass from South America, nuclear test samples. Like, it was really weird shit.
Oh, maybe, Mark, maybe one of those samples, if any of them came from nuclear stuff, kind of like the Trinity site had a quasi-crystal. I wonder if any of those nuclear stuff is quasi-crystalline.
Oh,
yeah, you know, speaking of which, so that thing that Jarod is holding is from Jeremy Reese. That is a printout of a quasi-crystal, right? 3D print.
Okay, what is this quasi-crystal thing?
So you see how this is not a cubic lattice or a square lattice, right? This is like a weird lattice. See if I can get closer. So this has 5.
You need to turn off the spaceship, man.
It's so messy behind me.
I'll do but you're phasing it out.
I'm doing it.
Uh-oh. There's Bernie. Wait. So Bernie came in. He disappeared. Come on, Bernie. Come on in.
Okay, so it's what? Just a non... What is that? Just a bunch of...
It's a bunch of icosahedrons all stuck together, right? And icosahedrons, like, if I turn it this way, you can see, like, that's threefold. It looks like a peace sign, right? Mm-hmm. But if I turn it just a little bit more, if I can, there we go. If I turn a little bit more, now you can kind of see, like, over here.
I see Star David.
This is what happens.
There's 5-fold symmetry.
Look like tricantahedrons, actually.
When you let the alien scientists go crazy with the 3D printer, this is what you get.
It's not an easy thing to print. Like, I've been printing for a little while. I don't think I could ever get this thing to print. Like, this is very impressive 3D printing. And yeah, Jeremy was nice enough to give me a sample of this when we went and visited him.
So is it all the... Let's say it was, I don't know, let's say it's glass or whatever. Let's say it's carbon. Would it all be carbon atoms or would it all be aluminum atoms? Is it like a great big weird crystal of some material?
I think Jarod's is plastic.
This is plastic, but so a quasi-crystal, you can make them out of a lot of different things, but, well, not a lot, a few different things. One of the links that I shared is a link that will let you look at all the different quasi-crystals that people have managed to make and what they've made it out of. There's only a specific like set of things that will like clump together in the right way to give you this quasi-crystal thing. And the thing that makes quasi-crystal special, have you ever heard of Penrose tiling?
No.
So Penrose tiling is this idea that you can take these two different shapes and you stick these two shapes together and you can like tiling a floor, right? You can make a big old tile of this and it makes these patterns that are really cool. There's like regularities, but irregularities. And it looks kind of like a pattern, but not quite. And if you took if you take that two-dimensional floor tile that you've made, and you look at it through a higher dimension, right? So instead of a 2x2 matrix on this piece goes in square 1, this piece goes in square 2, right? Instead of looking at it like that, you look at it in a 3x3 matrix. All of a sudden, now you see it looks like a square lattice again. So
that's like a Penrose tile right there.
It's like a higher dimensional thing that you take just a single slice out of that thing, and now you're looking at a single slice, and that single slice is what Tim just showed on the screen. It's a weird looking thing. But if you looked at the whole larger three-dimensional thing of that, you can see it looks like a regular lattice. It looks like a regular crystal. So it's super...
Yeah,
What's that?
quasi-crystal has a diffraction pattern that is very regular as well. You could probably look up quasi-crystal diffraction, and there's some very interesting things there, which is and it's all, by the way, related to the golden mean. In other words, like all of this is you can produce a three-dimensional all of those various three-dimensional quasi-crystals with just these two shapes, and they're also semi-periodic. Just like this is basically the three-dimensional version of Penrose tiling. So yeah, if you want to see what it looks like, these are golden rhombohedra, which means that each of these faces is exactly the same on all of them. There's two ways to construct a golden rhombohedra with those exact same faces and have a golden ratio between the faces, and they're obviously also, if you look at it for just a moment, you can tell it's a deformation of a cube. And so, you can talk about something that is perhaps like one of the things that has interested me for a long period of time is why does space, why do we have the right hand rule, for instance? Why would space have chirality in any way? And one of the things that you find is that for chirality to appear in something that has that is made up of smaller components, there's two ways you can do it. Either the components themselves are chiral, in other words, they're handed, they have a shape that is in a particular way, or it can be made up of multiple shapes, and that will often, depending upon the way in which those shapes interact, can create chirality in a substance that is allowed to tumble or whatever that's made of these larger shapes. So there's some interesting things going with that as well. But yeah, this is the what you have there looked like that's the rhombic tricontahedron. So that's one of the easy to recognize shapes, but this can of course continue to go out just like like I said, three-dimensional version of the Penrose tile you're seeing there, and then this can of course tile the three-dimensional tile. So yeah, that's it's a very interesting the way in which it works. He was talking about when it comes to the way in which the crystalline lattice behaves when it's either perturbed in different ways, or if the way in which it shears. There's a lot of very interesting effects that you wouldn't necessarily expect. And when it comes to coherence effects, we talked about it in the previous episode of the conference. We talked about the possibilities of various types of coherent effects occurring because of this difference of where it's non-periodic or semi-periodic at one scale, it's periodic at a different scale. So the scale-based periodicity means that there are harmonic effects that are non-standard and may basically at one scale, it's you may have one frequency that can harmonize with a different frequency because that other frequency follows a different path within when you're talking about scale-based things. So there's a lot of different ways in which quasi-crystals and the way in which they behave with and the way in which they interact with the waves propagating through them that are very much not like a typical periodic lattice of just like cubes, for instance.
Shia, if there's one thing I could add to that, the Fibonacci part to quasi-crystals, the fact that quasi-crystals all seem to be related to Fibonacci sequences, that's the part that gets me super excited, because I'm of the mind that the universe uses the same algorithms or the same codes over and over in all these different spots, right? And one of the spots that seems to use that code over and over is the Fibonacci sequence, the golden ratio. It uses that whenever it has to scale something up or down. If it's going to scale it up, it's going to use the 1.618. It's going to scale it down, it uses the 0.618, right? It's the scaling function for the universe we live in. So when you're talking about being able to affect things at the very, very small Planck level, it makes sense that you would have to use something that is in somewhat related to the golden ratio to be able to scale your thing all the way down to that itty bitty little scale. Or conversely, if you wanted to operate on something that's larger than the universe, extra dimensional than the universe, once again, you're going to use something Fibonacci-esque, a golden ratio Wu-esque. So quasi-crystals being able to allow you to affect things in higher dimensions or in different dimensions than your own, that's the part that gets me super excited. Yet it's just icing on the cake that they're finding out that it seems like consciousness, the microtubules associated with consciousness, seem to also obey quasi-crystalline things. So if we got the same quasi-crystal, and it's almost drinking games. Take a drink every time you say quasi-crystal, but every time you use one of these things, right? It seems like the universe, using the same rule over and over, you can apply that idea to other areas. So if it uses Fibonacci all over the place, maybe it uses quasi-crystals all over the place. Maybe it uses those for consciousness as well as for building of space-time, as well as for higher dimensional processing, even above space.
Well,
Maybe space is a computer and you can hack it with a quasi-crystal computer.
Yeah, part of my the paper I've been working on with when it comes to a basis for entropy and basically like a new basis for entropy that gives you a determinism with entropy actually relies on coupled oscillation, leading to these types of I will just say they're resonance-like effects, and basically finding a new way to define exactly what information is. Because, like, for instance, how do you define the way in which we currently define information is based upon stochastic treatments. In other words, it has to do with randomness and things of that nature. But at some point, there is a one-to-one relationship in the way in which our neurons and all of the structures within the brain function to information, and then that had to have arisen spontaneously by itself. In other words, without design. And whenever we are talking about the way in which we use information systems, there's always an arbitrary key that we define beforehand. So the arbitrary key, like, is not just a Rosetta Stone, but like one of the things I like to talk about is the ASCII code. There was the what does this number means this letter, and we set that. But the thing is, the brain didn't have some person setting this set of circumstances represents this information. So what is it that is causing that code, where you can actually define information? What is it in the universe, the way in which physics functions, that gives you an emergent method for encoding information? And so I've actually got a very long lecture on how coupled oscillation actually leads to structures in the brain that are basically encoding information directly. And so there's a lot of that research that I've been putting together with the neoclassical interpretation, because of course there's this possibility that that microtubules may be doing some room temperature superconducting and therefore flux pinning. And so looking at the way in which electromagnetism in the brain is interacting with a phaptic coupling, where different areas of the brain are coupled, and so you've actually got fields impacting the neurons. So normally in neural networks you have back propagation, for instance, but that requires all this hardware to deal with back propagation. There's all this stuff going on, all these algorithms running to go and move the data around. You don't have that in the brain, so there has to be a natural process by which error propagation occurs. And so that's where there's both the linear way in which our neural networks function, but then there's also the from the sides, this is probably the best way to put it, way in which back propagation and all of those other, the ways in which we can make a neural network function in the brain organically, without all of this other structure of computer systems, managing a neural network that we have in the computers. And so I have a full description of how that works with coupled oscillation, et cetera. And it all links right back down to defining entropy based upon deterministic mechanics, which relies upon the neoclassical interpretation and leads to Bohm and Pribram. And I don't know if you're aware that Bohm and Pribram gave us holonomic brain or the holographic brain theory. So yeah, I tie all of that together, and there's a lecture on that I could show you guys at some point.
Holographic universe.
Yeah,
Yep.
I was just thinking of that Michael Talbot book. I wanted to interview him, but he passed many years ago, which was a shame, because that's for some reason that's like the book that everybody has read, right? So
Yep, that was an amazing book.
That and Gerald Papineau.
Every time I lend it out, it disappears. So I bought a whole bunch of copies of it.
Watch
Yeah,
from Gödel Escher Bach, the Hofstadter butterfly in that shows like the electron resonances and stuff. Watch, that's going to be related to quasicrystals in some way. They're going to find that's just a slice. That's a projection.
Does he not talk about quasicrystals? I know he talks about multi-layered information, which is really
Gödel Escher was like 86 or something.
Yeah. I don't believe anybody who says they've read it cover to cover. There's a whole middle section where he's asking you to like completely buy into his entire, methodology and memorize it to understand what the hell he's talking about. The middle section is like, nah. Great beginning, great ending. I'm not happy with the middle.
It was written in 79. There's no way he was writing about quasicrystals.
Huh. Yeah, okay.
That almost reminds me of the movie Contact, right? When they received the plans and remember you put the plane in the movie, at least you put the plans into a cube, and then depending on how you view the cube, you get different information out of it from the same symbology.
Yeah.
Watch,
Yeah.
DNA is going to be described by quasicrystals. We're going to find some kind of alien like manual written in there. Hey, this is how you make a spaceship, by the way.
Actually, there's a guy who cited one of my articles. He's part of he's at some of the Russian universities. Tukov, I think was his name, and he cited one of my articles when it comes to basically showing that there is a holographic principle that can be demonstrated in DNA as well. So there's
Petrokov's work is amazing. I like because he's able to associate octonions to DNA. And that was like one of the big pegs for me that says, wait a minute, the universe is reusing parts because it uses octonions for DNA. It uses octonions for particle physics. But wait, octonions also describe music theory at like the most fundamental level. So whatever programmed this universe decided it was going to reuse the same like math Lego block to make stuff, to make music, and then to make life.
Mm-hmm. Now, is that because 8 comes from 2 cubed, so it would be 2 in 3 dimensions? Or am I just shooting randomly there?
Octonians are more than just the number 8. So the lesser thing, the 4-dimensional quaternion thing, that's what airplanes use to be able to describe pitch, roll, yaw, and like the acceleration, right? So rather than just 3-dimensional translation, you now have rotation, right? You use quaternions to describe that. Well, then if you include octonians, and I'm going to be way wrong on this, but if you include octonians, you can now describe stochastic events, which when you're talking about stochastics, that gets like into all sorts of things. That's all the permutations. That's all the possibilities of those rotations rather than just where it's at in that rotation. So when you're talking about DNA that has all these possibilities and permutations and folds and everything, or you're talking about particle physics, you have all these different ways things can come together. You have music, all these different like polyphones and polytones and all that stuff. That's how I understand, most likely incorrectly, the magic of octonians. And they can go into higher dimensional space for information processing. James Sylvester Gates, he talks about how there's a quantum error correcting code in the universe. And when you dial that back and boil that back, it ties back into octonians yet again.
Yeah.
Y'all worry me. Y'all worry me greatly.
Yeah, Drew, I knew there was going to be. Drew's going to ask for a project he can build now. And
No,
I'm just lost. But just lost is fine. So
you just worry me greatly.
Did I ever tell you guys about the article I wrote about the linguistic characteristics of non-coding DNA, where basically non-coding DNA conforms to 2 different tests of spoken word language. One of them is Zipf's law. I've forgotten what the second one is. But yeah, and the coding DNA does not conform to this sort of test of spoken word information. So yeah, it's very interesting. But of course, Zipf's law does come up in other situations as well, and more naturally. But it does indicate the possibility of non-coding DNA being multidimensional. Storage of information. So, hey, where does the genetic memory come from? Because like they've proven recently that genetic memory works. In other words, where you're talking about within a single generation, they did this test with mice and the foot shock association with cherry blossoms, and then those were that were naive to cherry blossom scent would be avoidant to it, even down to like I think it was the 3rd generation. So it's like there isn't some way in which information is being encoded in DNA and passed on to the offspring. So why not the non-coding sections? It's just sort of a spitball.
Shiva, I just had an interesting thought. So when we take light from the sun or a star, we split it up, you get all the spectrum of the rainbow, right? And if you were to take the full light and run it through the double slit experiment and then stick the observer past the slits, you'd have the time paradox because it decided to become a particle all the way back at the star. But what if you split off the light and you're only using the red part of the spectrum in one system, and then you had the violet going to another one, to another double slit? What do you think would happen?
Well, see, there's some assumptions there that go back to Bell inequalities, and whenever you read about Bell's own commentary on how Bell inequalities is taught today, it's an absurdity. And he wrote an entire book called Speakable and Unspeakable in Quantum Mechanics. It should be laying around here somewhere, in which he talks about the superiority of the de Broglie-Bohm approach in pilot wave, and how it is that the way in which his work was interpreted gives basically magical ideations, where the way in which entanglement we're said to function in like a spooky action at a distance. And basically what I'm saying here is Einstein was right that we are wrong about spooky action at a distance. There are ways in which we have actually modeled entanglement in fluid dynamics, where basically it is a extension of prior or in other words, shared causal influences. Because a lot of times one of the problems is we think of causality as this leads to that, instead of understanding there are a huge variety of things that lead to an event. And when two things are actually reliant upon information from elsewhere, and then they both get that shared information, then the outcome itself can be correlated in a certain way. And so this is basically the idea is non-local hidden variables. And that's a long discussion about how pilot wave has been advanced tremendously by John Bell at MIT, and understanding how that functions. So whenever you're talking about this idea that the wave function collapsed in a lot of those interpretations, that's part of Copenhagen interpretation. And even those ones that are many worlds, all of those are not actually necessary when you consider.
You're not going to answer the question. You're just going to disagree with the question.
Well, okay. So to answer the question,
to answer the question, you're saying that the question is wrong because it's an interpretation.
Right. And so if you were to send light through different different wavelengths of light through it, I mean, you can break.
Are you sure? Are you sure you're not Jewish? You didn't go to yeshiva?
Yeah.
They say two rabbis in a room. You have three opinions.
Well, Mark, maybe set it up as an experiment.
Yeah.
I'm not doing double slit, but I started. I don't know. I was just having these thoughts of.
I was talking about white light interferometry in my, in other words, the initial Michelson and Miller experiments were both done with white light. So in other words, it required that you have to consider the fact that whenever the various angles of incidence are changed, which is the way in which you produce the fringe patterns, then there's the diffraction patterns can end up going off. And so you no longer have, just all of the different.
I have another version of the double slit that I really want to try. So you have the regular double slit, two slits, and then there's your diffraction pattern. But what if we had we took one of the bright lines from the double slit from the pattern and made another double slit from that, and then put the sensor at the end of it. So now you have a conundrum, because if the sensor makes everything become a particle, it will never make it to that bright line, and it'll never make it to that point.
Well, I got to work with this one.
Yeah,
okay.
There's a lot of different discussions about this, like Wigner's friend. There's like there's a whole variety of, and Nathan looked like he was entertained by this conversation. I was hoping he'd jump in at some point there, man.
Well, okay, so
sorry, my camera.
We're about doing a double slit and then having the diffraction. So you have the regular double slit. You don't put the receiver in, so it doesn't become a particle. It's still a wave. Then you take one of the bright lines, the ones that don't line up with the slit, and you use that light to make another double slit experiment down the line using optics, and then you put a receiver there. So if the light decides to become a particle at that point, it would never make it to that point, because it would have hit the side of the wall, never made it to the second double slit.
It seems like you're not considering the fact that, you know, as the light travels through the slit. So you start with a planar wave, and then it comes out as two circular or spherical waves, and then the angles of incidence as they are going across each other are what create your fringe pattern. Okay.
Right. So you're taking one of the bright spots of the fringe pattern
So
that don't line up with the straight line,
so
and you're using that to create another double slit experiment past the reader.
Okay, so in other words, so there's a convergence of the two waves coming from the original two slits, and they're additively, they're constructively interfering instead of destructively interfering, and you want to place a slit at the point at which there's constructive interference, and like where perhaps two of the fringes are showing up, so that you've got constructive interference at both of your two new fringes. And then what is it that you believe will be the value of these two new slits?
So if you can run that into another double slit experiment, that same light,
okay,
and then put a sensor at the end of that, the light will be in a conundrum, because if it becomes a particle, it would have never reached that point, because it needed to have the diffraction. It would needed to have the destructive and positive interference to make it there.
In the current, okay, so there's two different things. In other words, I have to deal with what mainstream current philosophy is about it when it comes to like Copenhagen and et cetera. And then there's, you know, a de Broglie-Bohm approach, which would be
I'm talking about something experimental that I don't believe has ever been tried.
Right. There are multiple like double slit experiments that have been tried in a variety of different configurations. So, yeah,
maybe it has been tried.
Well, hold on just a sec. So you don't necessarily need a sensor. All you need to do is, if you have any kind of camera, right, like your iPhone, you could probably do this. If you're starting with white light, you basically measure out your double slit. So you do your first double slit, and that's going to project onto like a second piece of paper. Just figure out where those white lines are, cut your second slit. You could probably test this in about 10 minutes.
Yeah, but
you have to fire electrons.
When
you have to
when
fire
you put
electrons
a sensor in to see whether it's a particle or a wave, it decides to become a particle. When it's being observed,
the collapse of what you're talking about is the collapse event that makes a change, and it's like that is, like I said, that's very relevant to which interpretation. But specifically, most people would believe that it's still in wave form at that point, because you don't have a sensor yet. And so once you get to the other side, once you have placed a sensor, that is the point at which the collapse event will happen. So normal interference will happen at that second set of slits, and there shouldn't be anything very significant about that. But there will be a problem of angle of incidence. In other words, the approach, if you've got two sets of waves approaching, you know, your slits have to be, they're dependent upon the wavelength of light that you're using, if you're using monochromatic light. And so, you know, the width of the slits to whether or not they will create an appropriately shaped wave out the other side is part of the consideration. But in general, it probably would not do anything other than simply create another, you know, fringe pattern on the other side. That's how most people would interpret it, and there wouldn't be the collapse event. You wouldn't be able to argue that from current theory necessarily.
Well, because if there would be a collapse event, the light would never make it there.
Right. But and that's how some of these experiments work, where they say, oh well, it's collapsed here, so it's retroactively, you know, collapsed. And so there's these backwards in time effects, and there's all these things in those experiments. But all of that comes down to understanding that the idea of a collapse event and the way in which it is currently taught has very much to do with which interpretation of quantum mechanics that you're using. And so, you know, when you believe that there is a collapse event, what exactly does that mean? What exactly is an observation? All of these things were like dramatically fleshed out and talked about during Bell's era. In other words, John Stuart Bell is who, you know, gave us the Bell inequalities, which is part of this idea that, you know, we can't have just a particulate idea of light. It has to be a wave. And then when we also see that there is this particulate you know, event when you're like shooting electron beams through them, that where single electrons seem to be appearing on a screen in the fringe pattern. So it's looking at these two things in combination. That Bell inequalities shows us this idea that, well, it has to be both behaving as a particle and a wave. That is what it's saying. It has to be doing both. Now, it does not necessarily say that the collapse event can't be simply a change of threshold at the surface, where basically there is a threshold energy. Like, one of the things I like to describe is if you have a bunch of statues, Moai statues from Easter Island, half submerged in the ocean, and waves come up, they can be just enough. If those statues are all right next to each other, the wave can be just enough that it just bounces off and doesn't knock any of them over. But that same wave at that same amount of energy, if it is then funneled towards a single statue that ends up in the back, that can cause an interference event, which will make the amplitude of the wave high enough to knock over one and only one of those Moai statues. And so the point is that there can be the same thing can happen at light's interaction with individual atoms, such that there is a threshold, a requirement of energy that is giving us the idea of a particle that is not necessarily particulate. Now, that being said, I also do believe that electrons appear in mid-ether through the interaction of waves and vortices, causing what people call crystalline dislocations or things of that matter. Though I prefer to call it a cavitation event for an electron. But the point is that it doesn't necessarily have to exist as its own ball-like thing. And there are rational ways using de Broglie-Bohm pilot wave theory with the insights that we've seen from the Silicon Walker experiments in fluid dynamics that have shown us that there's a way we can rationally look at these dynamics where it can behave as both a particle and a wave, and it's completely mechanical in nature and doesn't have anything mysterious, and there's no spooky action at a distance.
So who's knocking over the Moai again?
This would be a wave of water coming in. And so in other words, that'd be like a wave of light coming in against the surface. And the surface is not perfectly flat, right? It's, it's flipping out. If you look at something at any given surface at atomic level.
The Moai like buried 50 feet below the ground or something like that? And
I'm just giving you something to think about, that something can either be knocked over or not knocked over by waves. And I'm giving you physical objects you can think of in your own mind, so that you understand the concept of whether that there are thresholds where energy can come up, bounce off, and not actually do the thing. But then there is this significant change to a system that occurs when the circumstances are right. In other words, the aiming of the waves coming in causes them to interfere constructively. That takes the total energy of the wave that was spread out and would bounce off, and instead concentrates it in a certain place, and then that overcomes with the statue's ability to remain standing. So in other words, it makes the wave high enough to knock over one of the statues, whereas the wave would not have been high enough to knock over any of the statues had the circumstances not been exactly correct. And so this is one way of understanding a threshold crossing event where something can go from being a wave to a particle at the interface of the screen of the detector. So it's just an understanding.
Yeah, that reminds me of scalar wave overlap, right? And that goes back to Tesla's illustrations, or like I hate to say it, Tom Bearden's illustrations, where you have scalar waves and where they intersect.
You mentioned the Tom.
I know.
Tim.
I know. I do remember seeing illustrations, right, with those scalar waves where you would have two waves that would cross, and where they meet, you get the peak, and maybe that is enough to do something, and where they where the troughs cross, you get an even greater dip. I think that's kind of what you're talking about.
Well, see, it's like I've got a couple of papers right up in my tabs right now dealing with that. You can actually stress a fluid beyond its a critical threshold, and then it will open up. You'll either have ways in which it will dislocate, or it will open up into vacuum cavities. And one of the ways that this always occurs in fluids is through rotation. So in other words, like a vortex, once it is pumped to a high enough speed, which has to do with the wave speed of that medium, the air, for instance, if you're doing it with air, then once it goes beyond the elastic threshold, then there are these voids that can open up, just the same as cavitation as you see in a liquid, and so that it's stressing something beyond a threshold can cause it to have a phase change. Now, I'm not talking about the phase of a wave. I'm talking about where it appears to go, from a liquid to a solid or to a gas, et cetera. Whereas this would be a type of phase change when a substance is stressed beyond its ability to react and then opens up a void or dislocates or in some way breaks, basically. And that's what we see in cavitation of liquids. The same thing also happens in air, and especially high-speed jets around. It is something that they study a lot, where there are these voids that open up that are very much like cavitation. And so what I'm saying is that whenever a wave is crossing a vortex, it actually does pump the speed of the vortex. And so the combination of wave and vortex can then cause a what is occurring to be only because of the combination of those two things, because the wave lends its energy to the rotation of the vortex at the point of the peak of the wave, and then that crosses the threshold and creates what is an event of something that is like a ball. In other words, an opening up, a ripping of the material, and that is the cavitation model of particle production in the ether model.
Yeah, yeah. I'm just looking at the chat notes. Somebody's saying they'll take an experiment over a theoretical, or they mean a theory any day. But what I want to point out there is these things require each other, right? I mean, you have to test theory with experiments, and you use experiments to guide theory, right? And so it's not mutually exclusive. And in terms of science, it never has been mutually exclusive. And one of the things that excites me about our community is that we have a really healthy mix of both theory and experiment, And I think that one of the challenges is when you have communities that are too far one way or the other, and we see those online, right? When you have too much, when you have too much experiment, you have basically you have people doing the same experiment over and over, doing variations on it. They never move it to the next level because they don't know what the next level is supposed to be. And when you have too much theory, then we've all seen that online. You just have people arguing.
That's called schizophrenia.
In email. Yeah.
I wonder if you could look at the manufacturing sector to get a good idea for this, because there's probably a sweet spot ratio for the two, right? It's probably not a 50-50 balance is the ideal, because, one of those things requires different resources than the other one, right? So when you look at manufacturing, you'll have like one senior engineer who's the one writing up the design, and then he'll have a couple other engineers below him that those people are like taking that design and starting to run with it. And then below them, they have the technicians that are doing, the ground level work, right? And at each of those tiers, you have more and more people lower and lower down the tier.
Well, but
structure of scientific revolution.
Even just today, like Shiva is doing basically, he's looking at geometries and conceptualization, and then Nathan is looking primarily at mathematical formalism, right? And they both have very, very different backgrounds and areas of like knowledge and focus and all of that. And then you have, you have Drew and Mark, who are very, very practical, hands-on, doing experiments, right? And then you have, yourself, you're kind of in that middle ground, and you're also doing like a lot of history and research. So, the only useless person here today is me, right? Everybody else actually.
You're the glue, Tim.
Right.
The
CEO right here.
Say, hey, look, all the parts to an engine does not an engine make. It has to be assembled right. You're doing the assembly. So if somebody just hands you a pile of engine parts, all of them individually can work. They do nothing until somebody assembles them.
Well, yeah, I appreciate you saying that. I just think that it's what I've seen is this additive effect. I've really seen an additive effect over the last few years, just bringing people together from different backgrounds, and it doesn't happen all the time, but like it happens enough that it's it's the sum of the parts is greater,
Mm-hmm. Yeah, I would say that when it comes to theory, a lot of times it's a tremendous amount of work for one thing that we hope for, and that is in Kuhn's structure of scientific revolutions. Basically, the normal science, that's what gets you your engineering. People taking something and once you've discovered a few things, building and throwing stuff to the wall, see what hits. You don't have to understand every little bit about it because you discover with practical application. But that after a while, you can develop beyond your capability of understanding what it is that you're doing. you're doing something and it's fucking cool. Excuse my language, but it's but you don't know why it works. So there's a limit to your extension. And that's what I believe is the revolution that theory is supposed to bring. In other words, having theory where you take what you believe that and you rearrange it to the point where it's like, hey, maybe if we look at it from this other angle, we can now take what everybody has developed all this time and revolutionize and start towards the next plateau. And I think that's basically it is. I think it's kind of an exception, and that the hard work of going out there and doing the experimentation. Honestly, I think that is the most of the work that it's probably the dominant. Because he was bringing up, is there a balance between those two? It's probably balanced tremendously towards just the hands-on engineering and and making changes like that, and then it's the exceptional times through the loop where you keep hitting that revolution, where every time you hit a dead end in something, you need some sort of revolution to get to the next plateau. And so I think that's where theory actually is valuable.
Absolutely. Well, guys, it's 5:23 now. Normally, I'd go probably until around 6, but we were light on lab updates today, and again, Gerald was having tech issues. Should we close things down at 5:30? Do you think today?
Sure.
We can blame the holidays on the short day. We'll blame the 4th of July. So, although I was inside sneezing and coughing all 4th. So,
something.
Hey Tim, can you let me present for just a second?
Sure, go for it.
Can y'all
never
give up? That was 55 years ago, gentlemen.
Nice.
I take no responsibility for the way my mother dressed me because I was only 4. But that is the Saturn V that went to the moon.
Wow.
And I was standing in the exact same spot about 2 years ago, and there was a Artemis right behind me. So I have a picture of an Artemis replacement for that rocket on pretty much the same crawler. So,
and in another 55 years, that Artemis will also go to the moon.
Yes, it'll take them that long to get that piece of junk off the ground. So, never give up.
Never surrender.
Quit. Never surrender. Never give up. Never surrender. That's it. All I want to show you.
That's cool.
Thank you.
How did you get so close?
Back then, Family Day meant everyone went out to the Space Center. It was open to the whole Space Center was open to the families.
Oh man, that's so cool.
And that was just where you were allowed to stand to take pictures.
Wow.
Because nobody thought twice about it. It was just growing up with rockets.
Right.
Anyhow.
That's super cool, Drew. Super cool.
Yeah. Well, guys, again, I want to thank all of you for amazing, absolutely amazing discussion and presentations and just everything. I mean, this has been an amazing session. We covered so much, and it's absolutely wonderful.
Yeah, thanks so much for putting this on, man. It's been fantastic.
Yeah, we rock. We're awesome.
Well, and we're doing so. The next ones that we have are, and I'm following. I'm going to blame this on Mark because this is based around his schedule to some degree. I think August 3rd, August 31st, and then September 28th. Those are the ones that are coming up. And then I'm going to be juggling airline trips in between that, and I'm going to get some more photos and video. What I'm trying to do is just get as much information out there as I can to try and make it more real for people. So. Oh, Drew has another one for us. Okay, we got a couple of minutes left here.
SLS.
Yeah, piece of crap. But that was the same exact spot for the most part.
Oh, that is sad. They put up that fence.
A recycled piece of crap.
Yeah, it is. I can say that because I spent 11 years on that program. So. It is a piece of junk. $40 billion worth of junk, by the way. You should demand your money back from your government.
How much of that went to salaries versus hardware?
It's probably 90% salary.
That's. I thought it was more like 98 or.
It's probably 90% salary. They spend
How
a lot
much
of
of it
money
went
on.
to removing UFOs from photos?
Trust me, there is nothing exotic out there in NASA land. They are not
They've scared them
hiding
away.
anything from you. They simply don't know what they're doing.
Yeah, they've scared them away.
Yeah, the aliens do not go to NASA for advice or information.
It would be pointless at this point.
Isn't
So-
the NRO still with NASA, or did they switch over to Space Force?
Do what now?
The NRO, National Reconnaissance Office, they're the ones with all the super cool spy satellites. For the longest time,
Yeah.
they were associated to NASA, but I want to say they switched over to Space Force like in the 90s.
They
Not
don't
the-
exist. There's a great big
NRO?
building out there with no address, no road name. It doesn't exist. Every time you drive by it, you just don't see it. It's over on the Space Force side, though. That's where it's always been. It's always been over on the Space
William
Force
says
side.
that I'm so cool. My last name is actually so cool.
Well, Dr. Nathan over here is actually my favorite Martian, as you can tell from his background.
Oh, yeah. Well, it's an atom, but it does every now and then it does line up interestingly.
It's like a black hole atom thing,
I think it's
Yeah.
cool.
and it's
Yeah, I think
colorful.
it's cool.
Yeah. No, hey,
It
I
works.
grew up watching My Favorite Martian. Okay, you know,
It was
I don't
great.
know if that dates me or what, but yeah,
Yeah. Well, guys, I think
All
we're
right,
just
gentlemen.
about there in terms of time. So why don't I close things down for today? This has been APEC for July 6th, 2024. Thank you to all of you guys for amazing presentations. And thank you to everybody who's watched and participated in this. This is an open forum, and our goal is to try and provide as best we can in terms of alt propulsion. So thank you again, everybody.